Section 35 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 16, Part 2. Mineral and Thermal Springs. Almost all springs, even those which we consider the purest, are impregnated with some foreign ingredients, which, being in a state of chemical solution, are so intimately blended with the water as not to affect its clearness, while they render it, in general, more agreeable to our taste, and more nutritious than simple rainwater. But the springs called mineral contain an unusual abundance of earthly matter in solution, and the substances with which they are impregnated correspond remarkably with those evolved in a gaseous form by volcanoes. Many of these springs are thermal, that is, their temperature is above the mean temperature of the place, and they rise up through all kinds of rock, as, for example, through granite, gneiss, limestone, or lava, but are most frequent in volcanic regions, or where violent earthquakes have occurred at eras comparatively modern. The water given out by hot springs is generally more voluminous and less variable in quantity at different seasons than that proceeding from any others. In many volcanic regions, jets of steam, called by the Italians stufas, issue from fissures at a temperature high above the boiling point, as in the neighborhood of Naples and in the Lipari Isles, and are disengaged unceasingly for ages. Now, if such columns of steam, which are often mixed with other gases, should be condensed before reaching the surface by coming in contact with strata filled with cold water, they may give rise to thermal and mineral springs of every degree of temperature. It is indeed by this means only, and not by hydrostatic pressure, that we can account for the rise of such bodies of water from great depths. Nor can we hesitate to admit the adequacy of the cause, if we suppose the expansion of the same elastic fluids to be sufficient to raise columns of lava to the lofty summits of volcanic mountains. Several gases, the carbonic acid in particular, are disengaged in a free state from the soil in many districts, especially in the regions of active or extinct volcanoes, and the same are found more or less intimately combined with the waters of all mineral springs, both cold and thermal. Dr. Daubeny and other writers have remarked not only that these springs are most abundant in volcanic regions, but that when remote from them, their site usually coincides with the position of some great derangement in the strata. A fault, for example, or great fissure, indicating that a channel of communication has been opened with the interior of the earth at some former period of local convulsion. It is also ascertained that at great heights in the Pyrenees and Himalaya mountains, hot springs burst out from granitic rocks, and they are abundant in the Alps also, these chains having all been disturbed and dislocated at times comparatively modern, as can be shown by independent geological evidence. The small area of volcanic regions may appear, at first view, to present an objection to these views, but not so when we include earthquakes among the effects of igneous agency. A large proportion of the land hitherto explored by geologists can be shown to have been rent or shaken by subterranean movements since the oldest tertiary strata were formed. It will also be seen in the sequel that new springs have burst out, and others have had the volume of their waters augmented, and their temperature suddenly raised after earthquakes, so that the description of these springs might almost with equal propriety have been given under the head of igneous causes, as they are agents of a mixed nature, being at once igneous and aqueous. But how, it will be asked, can the regions of volcanic heat send forth such inexhaustible supplies of water? The difficulty of solving this problem would, in truth, be insurmountable if we believed that all the atmospheric waters found their way into the basin of the ocean. But in boring near the shore, we often meet with streams of fresh water at the depth of several hundred feet below the sea level, and these probably descend, in many cases, far beneath the bottom of the sea, when not artificially intercepted in their course. Yet how much greater may be the quantity of salt water which sinks beneath the floor of the ocean, through the porous strata of which it is often composed, or through fissures rent in it by earthquakes. After penetrating to a considerable depth, this water may encounter a heat of sufficient intensity to convert it into vapor, even under the high pressure to which it would then be subjected. This heat would probably be nearest the surface in volcanic countries, and farthest from it in those districts which have been longest free from eruptions or earthquakes. It would follow from the views above explained that there must be a twofold circulation of terrestrial waters, one caused by solar heat, and the other by heat generated in the interior of our planet. We know that the land would be unfit for vegetation if deprived of the waters raised into the atmosphere by the sun. But it is also true that mineral springs are powerful instruments in rendering the surface subservient to the support of animal and vegetable life. Their heat is said to promote the development of the aquatic tribes in many parts of the ocean, and the substances which they carry up from the bowels of the earth to the habitable surface are of a nature and in a form which adapts them peculiarly for the nutrition of animals and plants. As these springs derive their chief importance to the geologist from the quantity and quality of the earthy materials which, like volcanoes, they convey from below upwards, they may properly be considered in reference to the ingredients which they hold in solution. These consist of a great variety of substances, but chiefly salts, with bases of lime, magnesia, alumen, and iron, combined with carbonic, sulfuric, and muriatic acids. Muriate of soda, silica, and free carbonic acid are frequently present. Also springs of petroleum, or liquid bitumen, and of naphtha. Calcareous springs. Our first attention is naturally directed to springs which are highly charged with calcareous matter, for these produce a variety of phenomena of much interest in geology. It is known that rainwater collecting carbonic acid from the atmosphere has the property of dissolving the calcareous rocks over which it flows, and thus in the smallest ponds and rivulets matter is often supplied for the earthly secretions of testacea and for the growth of certain plants on which they feed. But many springs hold so much carbonic acid in solution that they are enabled to dissolve a much larger quantity of calcareous matter than rainwater, and when the acid is dissipated in the atmosphere, the mineral ingredients are thrown down in the form of porous tufa or of more compact travertine. Auvergne. Calcareous springs, although most abundant in limestone districts, are by no means confined to them, but flow out indiscriminately from all rock formations. In central France, a district where the primary rocks are unusually destitute of limestone, springs copiously charged with carbonate of lime rise up through the granite and gneiss. Some of these are thermal, and probably derive their origin from the deep source of volcanic heat once so active in that region. One of these springs, at the northern base of the hill upon which Clermont is built, issues from volcanic peperino, which rests on granite. It has formed, by its incrustations, an elevated mound of travertine, or white concretionary limestone, 240 feet in length, and at its termination 16 feet high and 12 wide. Another encrusting spring in the same department, situated at Chaillouzet, near Pont Gibaud, rises in a gneiss country, at the foot of a regular volcanic cone, at least 20 miles from any calcareous rock. Some masses of tufaceous deposit produced by this spring have an oolitic texture. Valley of the Elsa. If we pass from the volcanic district of France to that which skirts the Apennines in the Italian peninsula, we meet with innumerable springs which have precipitated so much calcareous matter that the whole ground in some parts of Tuscany is coated over with tufa and travertine, and sounds hollow beneath the foot. In other places in the same country, compact rocks are seen descending the slanting sides of hills, very much in the manner of lava currents, except that they are of a white colour and terminate abruptly when they reach the course of a river. These consist of a calcareous precipitate from springs, some of which are still flowing, while others have disappeared or changed their position. Such masses are frequent on the slope of the hills which bound the valley of the Elsa, one of the tributaries of the Arno, which flows near Colla through a valley several hundred feet deep, shaped out of a lacustrine formation, containing fossil shells of existing species. I observed here that the travertine was unconformable to the lacustrine beds, its inclination according with the slope of the sides of the valley. One of the finest examples which I saw was at the Molino della Caldane, near Colla. The Senna and several other small rivulets which feed the Elsa have the property of encrusting wood and herbs with calcareous stone. In the bed of the Elsa itself, aquatic plants, such as Carrier, which absorb large quantities of carbonate of lime, are very abundant. Baths of Saint Vignon. Those persons who have merely seen the action of petrifying waters in England will not easily form an adequate conception of the scale on which the same process is exhibited in those regions which lie nearer to the active centres of volcanic disturbance. One of the most striking examples of the rapid precipitation of carbonate of lime from thermal waters occurs in the hill of San Vignon in Tuscany, at a short distance from Radicofani, and only a few hundred yards from the high road between Siena and Rome. The spring issues from near the summit of a rocky hill about 100 feet in height. The top of the hill stretches in a gently inclined platform to the foot of Mount Amiata, a lofty eminence which consists in great part of volcanic products. The fundamental rock from which the spring issues is a black slate with serpentine belonging to the older Apennine formation. The water is hot, has a strong taste, and when in not very small quantity is of a bright green color. So rapid is the depositation near the source that in the bottom of a conduit pipe for carrying off the water to the baths, and which is inclined at an angle of 30 degrees, half a foot of solid travertine is formed every year. A more compact rock is produced where the water flows slowly, and the precipitation in winter, when there is least evaporation, is said to be more solid, but less in quantity by 1/4 than in summer. The rock is generally white. Some parts of it are compact and ring to the hammer. Others are cellular, and with such cavities as are seen in the carious part of bone, or the siliceous millstone of the Paris basin. A portion of it, also below the village of Saint Vignon, consists of incrustations of long vegetable tubes, and may be called tufa. Sometimes the travertin assumes precisely the botryoidal and mammillary forms common to similar deposits in Auvergne, of a much older date, and like them it often scales off in thin, slightly undulating layers. A large mass of travertin descends the hill from the point where the spring issues, and reaches to the distance of about half a mile east of Saint Vignon. The beds take the slope of the hill at about an angle of 6 degrees, and the planes of stratification are perfectly parallel. One stratum, composed of many layers, is of a compact nature, and 15 feet thick. It serves as an excellent building stone, and a mass of 15 feet in length was in 1828 cut out for the new bridge over the Orsea. Another branch of it descends to the west for 250 feet in length, of varying thickness, but sometimes 200 feet deep. It is then cut off by the small river Orsea, as some glaciers in Switzerland descend into a valley till their progress is suddenly arrested by a transverse stream of water. The abrupt termination of the mass of rock at the river, where its thickness is undiminished, clearly shows that it would proceed much farther, if not arrested by the stream, over which it impends slightly. But it cannot encroach upon the channel of the Orsea, being constantly undermined, so that its solid fragments are seen strewed amongst the alluvial gravel. However enormous, therefore, the mass of solid rock may appear, which has been given out by this single spring, we may feel assured that it is insignificant in volume, when compared to that which has been carried to the sea since the time when it began to flow. What may have been the length of that period of time, we have no data for conjecturing. In quarrying the travertin, Roman tiles have been sometimes found at the depth of 5 or 6 feet. Baths of San Filippo. On another hill, not many miles from that last mentioned, and also connected with Mount Amiata, the summit of which is about 3 miles distant, are the celebrated baths of San Filippo. The subjacent rocks consist of alternations of black slate, limestone, and serpentine. There are 3 warm springs containing carbonate and sulphate of lime, and sulphate of magnesia. The water which supplies the baths falls into a pond, where it has been known to deposit a solid mass 30 feet thick in about 20 years. A manufactory of medallions in basso relievo is carried on at these baths. The water is conducted by canals into several pits, in which it deposits travertin and crystals of sulphate of lime. After being thus freed from its grosser parts, it is conveyed by a tube to the summit of a small chamber, and made to fall through a space of 10 or 12 feet. The current is broken in its descent by numerous crossed sticks, by which the spray is dispersed around upon certain moulds, which are rubbed lightly over with a solution of soap, and a deposition of solid matter like marble is the result, yielding a beautiful cast of the figures formed in the mould. The geologist may derive from these experiments considerable light in regard to the high slope of the strata at which some semi-crystalline precipitations can be formed, for some of the moulds are disposed almost perpendicularly, yet the deposition is nearly equal in all parts. A hard stratum of stone, about a foot in thickness, is obtained from the waters of San Filippo in 4 months, and as the springs are powerful and almost uniform in the quantity given out, we are at no loss to comprehend the magnitude of the mass which descends the hill, which is 1.25 miles in length, and the third of a mile in breadth, in some places attaining a thickness of 250 feet at least. To what length it might have reached, it is impossible to conjecture, as it is cut off, like the travertin of San Vignon, by a small stream, where it terminates abruptly. The remainder of the matter held in solution is carried on probably to the sea. Spheroidal structure in travertin. But what renders this recent limestone of peculiar interest to the geologist is the spheroidal form which it assumes, analogous to that of the cascade of Tivoli, afterwards to be described. The lamination of some of the concentric masses is so minute that 60 may be counted in the thickness of an inch, yet notwithstanding these marks of gradual and successive deposition, sections are sometimes exhibited of what might seem to be perfect spheres. This tendency to a mammillary and globular structure arises from the facility with which the calcareous matter is precipitated in nearly equal quantities on all sides of any fragment of shell or wood, or any inequality of the surface over which the mineral water flows, the form of the nucleus being readily transmitted through any number of successive envelopes. But these masses can never be perfect spheres, although they often appear such when a transverse section is made in any line not in the direction of the point of attachment. There are indeed occasionally seen small oolitic and pisolytic grains, of which the form is globular, for the nucleus, having been for a time in motion in the water, has received fresh accessions of matter on all sides. In the same manner, I have seen on the vertical walls of large steam boilers the heads of nails or rivets covered by a series of enveloping crusts of calcareous matter, usually sulphate of lime, so that a concretionary nodule is formed, preserving a nearly globular shape, when increased to a mass several inches in diameter. In these, as in many travertins, there is often a combination of the concentric and radiated structure. Campagna de Roma. The country around Rome, like many parts of the Tuscan states already referred to, has been at some former period the site of numerous volcanic eruptions, and the springs are still copiously impregnated with lime, carbonic acid, and sulphuretted hydrogen. A hot spring was discovered about 1827 near Civita Vecchia by Signor Riccioli, which deposits alternate beds of a yellowish travertin and a white granular rock, not distinguishable in hand specimens, either in grain, color, or composition, from statuary marble. There is a passage between this and ordinary travertin. The mass accumulated near the spring is in some places about 6 feet thick. End of chapter 16, part 2.
Chapter 36 of Principle of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Emanuela. Principle of Geology by Charles Lyell. whether species have a real existence in nature. Continued. Phenomena of hybrids. Hunter's opinions. Mews not strictly intermediate between parent species. Hybrid plants. Experiments of Kölreuter and Bigman. Vegetable hybrids, prolific throughout several generations. Why rare in a wild state? De Candolle on hybrid plants. The phenomena of hybrids confirm the distinctness of species. Theory of degradation in the intelligence of animals as indicated by the facial angle. Doctrine that certain organs of the fetus in mammalia assume successively the form of fish, reptile, and bird. Recapitulation. Phenomena of hybrids. We have yet to consider another class of phenomena, those relating to the production of hybrids, which have been regarded in a very different light with reference to their bearing to the question of the permanent distinctness of species. Some naturalists considering them as affording the strongest of all proofs in favor of the reality of species, others, on the contrary, appealing to them as countenancing the opposite doctrine, that all the varieties of organization and instinct now exhibited in the animal and vegetable kingdoms may have been propagated from a small number of original types. In regard to the mammifers and birds, it is found that no sexual union will take place between races which are remote from each other in the habits and organization, and it is only in species that are very nearly allied that such unions produce offspring. It may be laid down as a general rule, admitting of very few exceptions among quadrupeds, that the hybrid progeny is sterile, and there seem to be no well authenticated examples of the continuance of the mule race beyond one generation. The principal number of observations and experiments relate to the mixed offsprings of the horse and the ass, and in this case it is well established that the he-mule can generate and the she-mule produce. Such cases occur in Spain and Italy, and much more frequently in the West Indies and New Holland. But these mules have never bred in cold climates, seldom in warm regions, and still more rarely in temperate countries. The hybrid offspring of the she-ass and the stallion, the Enosh of Aristotle and the Hymnus of Pliny, differs from the mule, or the offsprings of the ass and mare. In both cases, says Buffon, these animals retain more of the dam than of the sire, not only in the magnitude, but in the figure of the body, whereas in the form of the head, limbs, and tail, they bear a greater resemblance to the sire. The same naturalist infers, from various experiments respecting crossbreeds between the he-goat and the ewe, the dog and she-wolf, the goldfinch and canary bird, that the male transmits his sex to the greatest number, and that the preponderance of males over females exceeds that which prevails where the parents are of the same species. Hunter's opinion. The celebrated John Hunter has observed that the true distinction of species must ultimately be gathered from their incapacity of propagating with each other, and producing offspring capable of again continuing itself. He was unwilling, however, to admit that the horse and the ass were of the same species, because some rare instances had been adduced of the breeding of mules, although he maintained that the wolf, the dog, and the jackal were all of one species, because he had found, by 2 experiments, that the dog would breed both with the wolf and the jackal, and that the mule, in each case, would breed again with the dog. In these cases, however, it may be observed that there was always one parent at least of pure breed, and no proof was obtained that the true hybrid race could be perpetuated, a fact of which, I believe, no examples are yet recorded, either in regard to mixtures of the horse and ass, or any other of the mammalia. should the fact be hereafter ascertained that two mules can propagate their kind, we must still enquire whether the offspring may not be regarded in the light of a monstrous birth, proceeding from some accidental cause, or, rather, to speak more philosophically, from some general law not yet understood, but which may not be permitted permanently to interfere with those laws of generation by which species may, in general, be prevented from becoming blended. If, for example, we discovered that the progeny of a mule race degenerated greatly in the first generation, in force, sagacity, or any attribute necessary for its preservation in a state of nature, we might infer that, like a monster, it is a mere temporary and fortuitous variety. Nor does it seem probable that the greater number of such monsters could ever occur unless obtained by art, for, in hunters' experiments, stratagem or force was, in most instances, employed to bring about the irregular connection. Mules not strictly intermediate between the parent species. It seems rarely to happen that a mule offspring is truly intermediate in character between the two parents. Thus, Hunter mentions that, in his experiments, one of the hybrid pups resembled the wolf much more than the rest of the litter, and we are informed by Wigman that, in a litter lately obtained in the Royal Menagerie at Berlin, from a white pointer and a she-wolf, two of the cubs resembled the common wolf dog, but the third was like a pointer with hanging ears. There is, undoubtedly, a very close analogy between these phenomena and those presented by the intermixture of distinct races of the same species, both in the inferior animals and in man. Dr. Pritchard, in his Physical History of Mankind, cites examples where the peculiarities of the parents have been transmitted very unequally to the offspring, as where children entirely white or perfectly black have sprung from the union of the European and the Negro. Sometimes the color or other peculiarities of one parent, after having failed to show themselves in the immediate progeny, reappear in a subsequent generation, as where a white child is born of two black parents, the grandfather having been a white. The same author judiciously observes that, if different species mixed their breed, and hybrid races were often propagated, the animal world would soon present a scene of confusion. Its tribes would be everywhere blended together, and we should perhaps find more hybrid creatures than genuine and uncorrupted races. Hybrid plants. Killreuter's experiments. The history of the vegetable kingdom has been thought to afford more decisive evidence in favor of the theory of the formation of new and permanent species from hybrid stocks. The first accurate experiments in illustration of this curious subject appear to have been made by Killreuter, who obtained a hybrid from two species of tobacco, Nicotiana rustica and Nicotiana paniculata, which differ greatly in the shape of their leaves, the color of the corolla, and the height of the stem. The stigma of a plant of Nicotiana rustica was impregnated with the pollen of a plant of Nicotiana paniculata. The seed ripened and produced a hybrid which was intermediate between the two parents, and which, like all the hybrids which this botanist brought up, had imperfect stamens. He afterwards impregnated this hybrid with the pollen of Nicotiana paniculata, and obtained plants which much more resembled the last. This he continued through several generations, until, by due perseverance, he actually changed the Nicotiana rustica into the Nicotiana paniculata. The plan of impregnation adopted was the cutting off of the anthers of the plants intended for fructification before they had shed pollen, and then laying on foreign pollen upon the stigma. Wickman's experiments. The same experiment has since been repeated with success by Wickman, who found that he could bring back the hybrids to the exact likeness of their parent by crossing them a sufficient number of times. The blending of the characters of the parent stocks in many other of Wickman's experiments was complete. The color and shape of the leaves and flowers, and even the scent, being intermediate, as in the offspring of the two species of verbascum, an intermarriage also between the common onion and the leek, Allium cepa and Allium porrum, gave a mule plant, which, in the character of its leaves and flowers, approached most nearly to the garden onion, but had the elongated bulbous root and smell of the leek. The same botanist remarks that vegetable hybrids, when not strictly intermediate, more frequently approach the female than the male parent species, but they never exhibit characters foreign to both. A recross with one of the original stocks generally causes the mule plant to revert towards that stock, but it is not always the case, the offspring sometimes continuing to exhibit the character of a full hybrid. In general, the success attending the production and perpetuity of hybrids among plants depends, as in the animal kingdom, on the degree of proximity between the species intermarried. If their organization be very remote, impregnation never takes place. If somewhat less distant, seeds are formed, but always imperfect and sterile. The next degree of relationship yields hybrid seedlings, but these are barren. And it is only when the parent species are very nearly allied that the hybrid race may be perpetuated for several generations. Even in this case, the best authenticated examples seem confined to the crossing of hybrids with individuals of pure breed. In none of the experiments most accurately detailed does it appear that both the parents were mules. Wickman diversified as much as possible his mode of bringing about these irregular unions among plants. He often saw with parallel rows, near to each other, of the species from which he desired to breed, and, instead of mutilating, after Koroiter's fashion, the plants of one of the parent stocks, he merely washed the pollen off their anthers. The branches of the plants in each row were then gently bent towards each other and intertwined, so that the wind and numerous insects, as they passed from the flowers of one to those of the other species, carried the pollen and produced fecundation. Vegetable hybrids were rare in a wild state. The same observer saw a good exemplification of the manner in which hybrids may be formed in a state of nature. Some wallflowers and pinks had been growing in a garden, in a dry sunny situation, and their stigmas had been ripened so as to be moist, and to absorb pollen with avidity, although their anthers were not yet developed. These stigmas became impregnated by pollen blown from some other adjacent plants of the same species, but had they been of different species, and not too remote in their organization, mule races must have resulted. When, indeed, we consider how busily some insects have been shown to be engaged in conveying anther dust from flower to flower, especially bees, flower-eating beetles, and the like, it seems a most enigmatical problem how it can happen that promiscuous alliances between distinct species are not perpetually occurring. How continually do we observe the bees diligently employed in collecting the red and yellow powder by which the stamens of flowers are covered, loading it on their hind legs, and carrying it to their hive for the purpose of feeding their young. In thus providing for their own progeny, these insects assist materially the process of fructification. Few persons need be reminded that the stamens in certain plants grow on different blossoms from the pistils, and unless the summit of the pistil be touched with the fertilizing dust, the fruit does not swell, nor the seed arrive at maturity. It is by the help of bees chiefly that the development of the fruit of many such species is secured, the powder which they have collected from the stamens being unconsciously left by them in visiting the pistils. How often, during the heat of a summer's day, do we see the males of the issues plants, such as the U3, standing separate from the females and sending off into the air, upon the slightest breath of wind, clouds of buoyant pollen. That the zephyr should so rarely intervene to fecundate the plants of one species with the anther dust of others seems almost to realize the converse of the miracle believed by the credulous herdsmen of the Lusitanian mares. Ore omnes verse in zephyrum, stant rupibus altis, exceptanque leves auras, et sepes in eullis, coniugis vento gravide, mirabile dictu. But, in the first place, it appears that there is a natural aversion in plant, as well as in animals, to regular sexual unions. And in most of the successful experiments in the animal and vegetable world, some violence has been used in order to procure impregnation. The stigma imbibes, slowly and reluctantly, the granules of the pollen of another species, even when it is abundantly covered with it, and if it happen that, during this period, ever so slightly a quantity of the anther dust of its own species alight upon it, this is instantly absorbed, and the effect of the foreign pollen destroyed. Besides, it does not often happen that the male and female organs of fructification in different species arrive at the state of maturity at precisely the same time. Even where such synchronism does prevail, so that a cross-impregnation is effected, the chances are very numerous against the establishment of a hybrid race. If we consider the vegetable kingdom generally, it must be recollected that even of the seeds which are well ripened, a great part are either eaten by insects, birds, and other animals, or decay for want of room and opportunity to germinate. Unearthly plants are the first which are cut off by causes prejudicial to the species, being usually stifled by more vigorous individuals of their own kind. If, therefore, the relative fecundity or hardiness of hybrids be in the least degree inferior, they cannot maintain their footing for many generations, even if they were ever produced beyond one generation in a wild state. In the universal struggle for existence, the right of the strongest eventually prevails, and the strength and durability of a race depend mainly on its prolificness, in which hybrids are acknowledged to be deficient. Centaurea hybrida, a plant which never bears seed, and is supposed to be produced by the frequent intermixture of two well-known species of Centaurea, grows wild upon a hill near Turin. Ranunculus lacerus, also sterile, has been produced accidentally at Grenoble, and near Paris by the union of two ranunculi, but this occurred in gardens. Mr. Herbert's experiments. Mr. Herbert, in one of his ingenious papers on new plants, endeavours to account for their non-occurrence in a state of nature, from the circumstance that all the combinations that were likely to occur have already been made many centuries ago, and have formed the various species of botanists. But in our gardens, he says, whenever species having a certain degree of affinity to each other are transported from different countries and brought for the first time into contact, they give rise to hybrid species. But we have no data, as yet, to warrant the conclusion that a single permanent hybrid race has ever been formed, even in gardens, by the intermarriage of two allied species brought from distant habitations. Until some fact of this kind is fairly established, and a new species capable of perpetuating itself in a state of perfect independence of man, can be pointed out, it seems reasonable to call in question entirely this hypothetical source of new species. That varieties do sometimes spring up from crossbreeds in a natural way can hardly be doubted, but they probably die out even more rapidly than races propagated by grafts or layers. Opinion of de Candolle. De Candolle, whose opinion on a philosophical question of this kind deserves the greatest attention, has observed in his Essay on Botanical Geography that the varieties of plants range themselves under two general heads, those produced by external circumstances and those formed by hybridity. After adducing various arguments to show that neither of these causes can explain the permanent diversity of plants indigenous in different regions, he says, in regard to the crossing of races, I can perfectly comprehend, without altogether sharing the opinion, that, where many species of the same genera occur near together, hybrid species may be formed, and I am aware that the great number of species of certain genera which are found in particular region may be explained in this manner, but I am unable to conceive how anyone can regard the same explanation as applicable to species which live naturally at great distances. If the 3 larches, for example, now known in the world, lived in the same localities, I might then believe that one of them was the produce of the crossing of the 2 others, but I never could admit that the Siberian species has been produced by the crossing of those of Europe and America. I see, then, that there exist in organized beings permanent differences, which cannot be referred to any one of the actual causes of variation, and these differences are what constitutes species. Reality of species confirmed by the phenomena of hybrids. The most decisive arguments, perhaps, amongst many others, against the probability of the derivation of permanent species from crossbreeds, are to be drawn from the fact alluded to by de Candolle, of species having a close affinity to each other, occurring in distinct botanical provinces, or countries inhabited by groups of distinct species of indigenous plants. For in this case, naturalists, who are not prepared to go the whole length of the transmutationists, are under the necessity of admitting that, in some cases, species which approach very near to each other in their characters were so created from their origin, an admission fatal to the idea of its being a general law of nature that a few original types only should be formed, and that all intermediate races should spring from the intermixture of those stocks. This notion, indeed, is wholly at variance with all that we know of hybrid generation, for the phenomena entitle us to affirm that had the types been at first somewhat distinct, no cross-breeds would ever have been produced, much less those prolific races which we now recognize as distinct species. In regard, moreover, to the permanent propagation of hybrid races among animals, insuperable difficulties present themselves when we endeavor to conceive the blending together of the different instincts and properties of 2 species, so as to ensure that preservation of the intermediate race. The common mule, when obtained by human art, may be protected by the power of man, but, in a wild state, it would not have precisely the same wants either as the horse or the ass, and if in consequence of some difference of this kind it strayed from the herd, it would soon be hunted down by beasts for prey and destroyed. If we take some genus of insects, such as the bee, we find that each of the numerous species have some difference in its habits, its mode of collecting honey, or constructing its dwelling, or providing for its young, and other particulars. In the case of the common hive bee, the workers are described, by Kirby and Spence, as being endowed with no less than 30 distinct instincts. So, also, we find that amongst a most numerous class of spiders, there are nearly as many different modes of spinning their webs as there are species. When we recollect how complicated are the relations of these instincts with coexisting species, both of the animals and vegetable kingdoms, it is scarcely possible to imagine that a bastard race could spring from the union of two of these species, and retain just so much of the qualities of each parent stock as to preserve its ground in spite of the dangers which surround it. We might also ask if a few generic types alone have been created among insects, and the intermediate species have proceeded from hybridity. Where are those original types combining, as they ought to do, the elements of all the instincts which have made their appearance in the numerous derivative races? So, also in regard to animals of all classes and of plants, if species are in general of hybrid origin, where are the stocks which combine in themselves the habits, properties, and organs of which all the intervening species ought to afford us mere modifications? A recapitulation of the arguments from hybrids. I shall now conclude this subject by summing up, in a few words, the result to which I have been led by the consideration of the phenomena of hybrids. It appears that the aversion of individuals of distinct species to the sexual union is common to animals and plants, and that it is only when the species approach near to each other in their organization and habits that any offspring are produced from their connection. Mews are of extremely rare occurrence in a state of nature, and no examples are yet known of their having procreated in a wild state. But it has been proved that hybrids are not universally sterile, provided the parent stocks have a near affinity to each other, although the continuation of the mixed race for several generations appears hitherto to have been obtained only by crossing the hybrids with individuals of pure species, an experiment which by no means bears out the hypothesis that a true hybrid race could ever be permanently established. Hence, we may infer that aversion to sexual intercourse is, in general, a good test of the distinctness of original stocks, or of a species, and the procreation of hybrids is a proof of the near affinity of species. Perhaps, hereafter, the number of generations for which hybrids may be continued, before the race dies out, for it seems usually to generate rapidly, may afford the zoologist and botanist an experimental test of the difference in the degree of affinity of allied species. I may also remark that if it could have been shown that a single permanent species had ever been produced by hybridity, of which there is no satisfactory proof, it might certainly have lent some countenance to the notions of the ancients respecting the gradual deterioration of created things, but none whatever to Lamarck's theory of their progressive perfectibility, for observations have hitherto shown that there is a tendency in mule animals and plants to degenerate in organization. It was before remarked that the theory of progressive development arose partly from an attempt to engraft the doctrines of the transmutationists upon one of the most popular generalizations in geology. But we have seen in the 9th chapter that the modern researches of geologists have broken at many points the chain of evidence once supposed to exist in favor of the doctrine that, at each successive period in the earth's history, animals and plants of a higher grade or more complex organization have been created. The recent origin of man and the absence of all signs of any rational being holding an analogous relation to former states of the animate world affords one, and perhaps in the present state of science, the only argument of much weight in support of the hypothesis of a progressive scheme, but none whatever in favor of the fancied evolution of one species out of another. Theory of the gradation of intellect as shown by the facial angle. When the celebrated anatomist Kemper first attempted to estimate the degrees of sagacity of different animals and of the races of man by the measurement of the facial angle, some speculators were bold enough to affirm that certain simiae, or apes, differed as little from the more savage races of man as those do from the human race in general, and that a scale might be traced from apes with foreheads villanous low to the African variety of the human species, and from that to the European. The facial angle was measured by drawing a line from the prominent center of the forehead to the most advanced part of the lower jawbone, and observing the angle which it made with the horizontal line, and it was affirmed that there was a regular series of such angles from birds to the mammalia. The gradation from the dog to the monkey was said to be perfect, and from that again to man. One of the ape tribe has a facial angle of 42 degrees, and another, which approximated the nearest to man in figure, an angle of 50 degrees. To this succeeds, longo sed proximus intervallo, the head of the African Negro, which, as well as that of the Kalmuk, forms an angle of 70 degrees, while that of the European contains 80 degrees. The Roman painters preferred the angle of 95 degrees, and the character of beauty and sublimity so striking in some works of Grecian sculpture, as in the head of the Apollo and in the Medusa of Sophocles, is given by an angle which amounts to 100 degrees. A great number of valuable facts and curious analogies in comparative anatomy were brought to light during the investigations which were made by Kemper, John Hunter, and others to illustrate the scale of organization, and their facts and generalizations must not be confounded with the fanciful systems which White and others deduced from them. That there is some connection between an elevated and capacious forehead in certain races of men and the large development of the intellectual faculties seems highly probable, and that a low facial angle is frequently accompanied with inferiority of mental powers is certain, but the attempt to trace a gradual scale of intelligence through the different species of animals accompanying the modifications of the form of the skull is a mere visionary speculation. It has been found necessary to exaggerate the sagacity of the ape tribe at the expense of the dog, and strange contradictions have arisen in the conclusions deduced from the structure of the elephant, some anatomists being disposed to deny the quadruped the intelligence which he really possesses, because they found that the volume of his brain was small in comparison to that of the other mammalia, while others were inclined to magnify extravagantly the superiority of his intellect, because the vertical height of his skull is so great when compared to its horizontal length. Different races of men are all of one species. It would be irrelevant to our subject if we were to enter into a further discussion on these topics, because even if a graduated scale of organization and intelligence could have been established, it would prove nothing in favor of a tendency in each species to attain a higher state of perfection. I may refer the reader to the writings of Blumenbach, Pritchard, Lawrence, and more recently Latham, for convincing proofs that the variety of form, color, and organization of different races of men are perfectly consistent with the general received opinion that all the individuals of the species have originated from a single pair, and, while they exhibit in man as many diversities of a physiological nature as appear in any other species, they confirm also the opinion of the slight deviation from a common standard of which species are capable. The power of existing and multiplying in every latitude, and in every variety of situation and climate, which has enabled the great human family to extend itself over the habitable globe, is partly, says Lawrence, the result of physical constitution and partly of the mental prerogative of man. If he did not possess the most enduring and flexible corporeal frame, his arts would not enable him to be the inhabitant of all climates, and to brave the extremes of heat and cold, and the other destructive influences of local situation. Yet, notwithstanding the flexibility of bodily frame, we find no signs of indefinite departure from a common standard, and the intermarriages of individuals of the most remote varieties are not less fruitful than between those of the same tribe. Tiedemann on the brain of the fetus in vertebrated animals. There is yet another department of anatomical discovery to which I must allude, because it has appeared to some persons to afford a distant analogy, at least, to that progressive development by which some of the inferior species may have been gradually perfected into those of more complex organization. Tiedemann found, and his discoveries have been most fully confirmed and elucidated by Serre, that the brain of the fetus, in the highest class of vertebrated animals, assumes, in succession, forms bearing a certain degree of resemblance to those which belong to fishes, reptiles, and birds, before it acquires the additions and modifications which are peculiar to the mammiferous tribe, so that, in the passage from the embryo to the perfect mammifer, there is a typical representation, it is said, of all those transformations which the primitive species are supposed to have undergone during a long series of generations between the present period and the remotest geological era. If you examine the brain of the mammalia, says Serre, at an early stage of uterine life, you perceive the cerebral hemispheres consolidated, as in fish, in two vesicles isolated one from the other. At a later period, you see them affect the configuration of the cerebral hemispheres of reptiles. Still later again, they present you with the forms of those of birds. Finally, they acquire, at the era of birth, and sometimes later, the permanent forms which the adult mammalia present. The cerebral hemispheres, then, arrive at the state which we observe in the higher animals only by a series of successive metamorphoses. If we reduce the whole of these evolutions to 4 periods, we shall see that the first are born the cerebral lobes of the fishes, and this takes place homogeneously in all classes. The second period will give us the organization of reptiles, the third, the brain of birds, and the fourth, the complex hemispheres of mammalia. If we could develop the different parts of the brain in the inferior classes, we should make in succession a reptile out of a fish, a bird out of a reptile, and a mammiferous quadruped out of a bird. If, on the contrary, we could starve this organ in the mammalia, we might reduce it successively to the condition of the brain of the 3 inferior classes. Nature often presents us with this last phenomenon in monsters, but never exhibits the first. Among the various deformities which organized beings may experience, they never pass the limits of their own classes to put on the forms of the class above them. Never does a fish elevate itself so as to assume the form of the brain of a reptile, nor does the latter even attain that of birds, nor the bird that of the mammifer. It may happen that a monster may have 2 heads, but the conformation of the brain always remains circumscribed narrowly within the limits of its class. Dr. Clark of Cambridge, in a memoir on fetal development, 1845, has shown that the current labors of Valentin, Rathke, and Bischoff disprove the reality of the supposed anatomical analogy between the embryo condition of certain organs in the higher orders and the perfect structure of the same organs in animals of an inferior class. The hearts and brains, for example, of birds and mammals do not pass through forms which are permanent in fishes and reptiles. there is only just so much resemblance as may point to a unity of plan running through the organization of the whole series of vertebrate animals, but which lends no support whatever to the notion of a gradual transmutation of one species into another, least of all of the passage, in the course of many generations, from an animal of a more simple to one of a more complex structure. Recapitulation. For the reasons, therefore, detailed in this and the two preceding chapters, we may draw the following inferences in regard to the reality of species in nature. First, that there is a capability in all species to accommodate themselves, to a certain extent, to a change of external circumstances, this extent varying greatly according to the species. Secondly, when the change of situation which they can endure is great, it is usually attended by some modifications of the form, color, size, structure, or other particulars, but the mutations thus superinducted are governed by constant laws, and the capability of so varying forms part of the permanent specific character. Thirdly, some acquired peculiarities of form, structure, and instinct are transmissible to the offspring, but these consist of such qualities and attributes only as are intimately related to the natural wants and propensities of the species. Fourthly, the entire variation from the original type which any given kind of change can produce may usually be effected in a brief period of time, after which no further deviation can be obtained by continuing to alter the circumstances, though ever so gradually. Indefinite divergence, either in the way of improvement or deterioration, being prevented, and the least possible excess beyond the defined limits being fatal to the existence of the individual. Fifthly, the intermixture of distinct species is guarded against by the aversion of the individuals composing them to sexual union, or by the sterility of the male offspring. It does not appear that true hybrid races have ever been perpetuated for several generations, even by the assistance of man, for the cases usually cited relate to the crossing of mules with individuals of pure species, and not to the intermixture of hybrid with hybrid. Sixthly, from the above considerations, it appears that species have a real existence in nature, and that each was endowed, at the time of its creation, with the attributes and organization by which it is now distinguished. End of chapter 36. Recording by Emanuela. Chapter 17, Part 1 of Principle of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Emanuela. Principle of Geology by Charles Lyell. Chapter 17, Part 1. Reproductive effects of rivers. Lake deltas. Growth of the delta of the Upper Rhine in the Lake of Geneva. Computation of the age of deltas. Recent deposits in Lake Superior. Deltas of inland seas. Course of the Po. Artificial embankments of the Po and Adige. Delta of the Po and other rivers entering the Adriatic. Rapid conversion of that gulf into land. Mineral characters of the new deposits. Marine delta of the Rhone. Various proof of its increase. Stony nature of its deposits. Coasts of Asia Minor. Delta of the Nile. Deltas in lakes. I have already spoken in the 14th chapter of the action of running water and of the denuding power of rivers, but we can only form a just conception of the excavating and removing force exerted by such bodies of water when we have the advantage of examining the reproductive effects of the same agents. In other words, of beholding in a palpable form the aggregate amount of matter which they have thrown down at certain points in the alluvial plains or in the basin of lakes and seas. Yet it will appear, when we consider the action of currents, that the growth of delta affords a very inadequate standard by which to measure the entire carrying power of running water, since a considerable portion of fluviatile sediment is swept far out to sea. Deltas may be divided into, first, those which are formed in lakes, secondly, those in inland seas, where the tides are almost imperceptible, and thirdly, those on the borders of the ocean. The most characteristic distinction between the lacustrine and marine deltas consists in the nature of the organic remains which become embedded in their deposits. For, in the case of a lake, it is obvious that this must consist exclusively of such genera of animals as inhabits the land or the waters of a river or a lake, whereas, in the other case, there will be an admixture, and most frequently a predominance, of animals which inhabit salt water. In regard, however, to the distribution of inorganic matter, the deposits of lakes and seas are formed under very analogous circumstances. Lake of Geneva. Lakes exemplify the first reproductive operations in which rivers are engaged when they convey the detritus of rocks and the aggregates of mineral springs from mountainous regions. The accession of new land at the mouth of the Rhone, at the upper end of the Lake of Geneva or the Leman Lake, presents us with an example of a considerable thickness of strata which have accumulated since the historical era. This sheet of water is about 37 miles long, and its breadth is from 2 to 8 miles. The shape of the bottom is very regular, the depth having been found by late measurement to vary from 20 to 160 fathoms. The Rhone, where it enters at the upper end, is turbid and discolored, but its waters, where it issues at the town of Geneva, are beautifully clear and transparent. An ancient town called Port Valae, Portus Valesiae of the Romans, once situated at the water's edge, at the upper end, is now more than a mile and a half inland, this intervening alluvial tract having been acquired in about 8 centuries. The remainder of the delta consists of a flat alluvial plain, about 5 or 6 miles in length, composed of sand and mud, a little raised above the level of the river, and full of marshes. Sireri de la Beach found, after numerous soundings in all parts of the lake, that there was a pretty uniform depth of from 120 to 160 fathoms throughout the central region, and on approaching the delta, the shallowing of the bottom began to be very sensible at a distance of about 1.75 miles from the mouth of the Rhone. From a line drawn from St. Gingolf to Vevey gives a mean depth of somewhat less than 600 feet, and from that part of the Rhone the fluviatile mud is always found along the bottom. We may state, therefore, that the new strata annually produced are thrown down upon a slope about 2 miles in length, so that, notwithstanding the great depth of the lake, the new deposits are inclined at so slight an angle that the dip of the beds would be termed, in ordinary geological language, horizontal. The strata probably consist of alternation of finer and coarser particles, for, during the hotter months, from April to August, when the snows melt, the volume and velocity of the river are greatest, and large quantities of sand, mud, vegetable matter, and driftwood are introduced, but during the rest of the year the influx is comparatively feeble, so much so that the whole lake, according to Saussure, stands 6 feet lower, If, then, we could obtain a section of the accumulation formed in the last 8 centuries, we should see a great series of strata, probably from 600 to 900 feet thick, the supposed original depth of the head of the lake, and nearly 2 miles in length, inclined at a very slight angle. In the meantime, a great number of small deltas are growing around the borders of the lake, at the mouths of rapid torrents, which pour in large masses of sand and pebbles. The body of water in this torrent is too small to enable them to spread out the transported matter over so extensive an area as the Rhone does. Thus, for example, there is a depth of 80 fathoms within half a mile of the shore, immediately opposite the great torrent which enters east of Ripoll, so that the depth of the strata is that minor delta must be about 4 times as great as those deposited by the main river at the upper extremity of the lake. Chronological computations of the age of deltas. The capacity of this basin being now ascertained, it would be an interesting subject of inquiry to determine in what number of years the Leman Lake will be converted into a dry land. It would not be very difficult to obtain the elements for such a calculation, so as to approximate at least to the quantity of time required for the accomplishment of the result. The number of cubic feet of water annually discharged by the river into the lake being estimated, experiments might be made in the winter and summer months to determine the proportion of matter held in suspension or in chemical solution by the Rhone. It would be also necessary to allow for the heavier matter drift along at the bottom, which might be estimated on hydrostatical principle when the average size of the gravel and the volume and velocity of the stream at different seasons were known. Supposing all these observations to have been made, it would be more easy to calculate the future than the former progress of the delta, because it would be a laborious task to ascertain, with any degree of precision, the original depth and extent of that part of the lake which is already filled up. Even if this information were actually obtained by borings, it would only enable us to approximate within a certain number of centuries to the time when the Rhone began to form its present delta. But it would not give us the date of the origin of the Leman Lake in its present form, because the river may have flowed into it for thousands of years without importing any sediment whatever. Such would have been the case if the waters had first passed through a chain of upper lakes, and that this was actually the fact seems indicated by the course of the Rhone between Martigny and the Lake of Geneva, and still more decidedly by the channels of many of its principal feeders. If we ascend, for example, the valley through which the Drance flows, we find that it consists of a succession of basins, one above the other, in each of which there is a wide expanse of flat alluvial lands, separated from the next basin by a rocky gorge, once perhaps the barrier of a lake. The river seems to have filled these lakes, one after the other, and to have partially cut through the barriers, some of which it is still gradually eroding to a greater depth. Before, therefore, we can pretend even to hazard a conjecture as to the era at which the principal delta of Lake Leman or any other delta commenced, we must be thoroughly acquainted with geographical features and geological history of the whole system of higher valleys which communicate with the main stream, and all the changes which they have undergone since the last series of convulsions which agitated and altered the face of the country. Lake Superior. Lake Superior is the largest body of fresh water in the world, being above 1,700 geographical miles in circumference when we follow the sinuosities of its coasts, and its length, on a curved line drawn through its center, being more than 400, and in extreme breadth above 150 geographical miles. Its surface is nearly as large as the whole of England. Its average depth varies from 80 to 150 fathoms, but according to Captain Bayfield, there is a reason to think that its greatest depth would not be overrated at 200 fathoms, so that its bottom is, in some parts, nearly 600 feet below the level of the Atlantic, its surface being about as much above it. There are appearances in different parts of this, as of the other Canadian lakes, leading us to infer that its water formerly occupied a higher level than they reached at the present, for at a considerable distance from the present shores, parallel lines of rolled stones and shells are seen rising one above the other, like the seats of an amphitheatre. These ancient lines of shingle are exactly similar to the present beaches in most bays, and they often attain an elevation of 40 or 50 feet above the present level. As the heaviest gales of wind do not raise the waters more than 3 or 4 feet, the elevated beaches have, by some, been referred to the subsidence of the lake at former periods, in consequence of the wearing down of its barrier, by others to the upraising of the shores by earthquakes, like those which have produced similar phenomena on the coast of Chile. The streams which discharge their waters into Lake Superior are several hundred in number, without reckoning those of smaller size, and the quantity of water supplied by them is many times greater than that discharged at the Falls of St. Mary, the only outlet. The evaporation, therefore, is very great, and such as might be expected from so vast an extent of surface. On the northern side, which is encircled by primary mountains, the rivers sweep in many large boulders, with smaller gravel and sand, chiefly composed of granitic and trap rocks. There are also currents in the lake in various directions, caused by the continued prevalence of strong winds, and to their influence we may attribute the diffusion of finer mud far and wide over great areas, for, by numerous soundings made during Captain Bayfield's survey, it was ascertained that the bottom consists generally of a very adhesive clay, containing shells of the species at present existing in the lake. When exposed to the air, this clay immediately becomes indurated in so great a degree as to require a smart blow to break it. It effervesces slightly with diluted nitric acid, and is of different colors in different parts of the lake. In one district blue, in another red, and in a third white, hardening into a substance resembling pipe clay. From these statements, the geologist will not fail to remark how closely these recent lacustrine formations in America resemble the tertiary argillaceous and calcareous marls of lacustrine origin in central France. In both cases, many of the genera of shells most abundant, as Limnea and Planorbis, are the same, and in regard to other classes of organic remains, there must be the closest analogy, as I shall endeavour more fully to explain when speaking of the embedding of plants and animals in recent deposits. Deltas of inland seas. Having thus briefly considered some of the lacustrine deltas now in progress, we may next turn our attention to those of inland seas. Course of the Po. The Po affords an instructive example of the manner in which a great river bears down to the sea the matter poured into it by a multitude of tributaries, descending from lofty chains of mountains. The changes gradually effected in the great plain of northern Italy, since the time of the Roman Republic, are considerable. Extensive lakes and marshes have been gradually filled up, as those near Placentia, Parma, and Cremona, and many have been drained naturally by the deepening of the beds of rivers. Deserted river courses are not unfrequent, as that of the Serio Morto, which formerly fell into the Adda in Lombardy. The Po also itself has often deviated from its course, having, after the year 1390, deserted part of the territory of Cremona and invaded that of Parma, its sole channel being still recognizable and bearing the name of Po Morto. There is also an old channel of the Po in the territory of Parma called Po Vecchio, which was abandoned in the 12th century when a great number of towns were destroyed. Artificial embankments of Italian rivers. To check these and similar aberrations, a general system of embankment has been adopted, and the Po, Adige, and almost all their tributaries are now confined between high artificial banks. The increased velocity acquired by streams thus closed in enabled them to convey a much larger portion of foreign matter to the sea, and, consequently, the deltas of the Po and Adige have gained far more rapidly on the Adriatic since the practice of embankment became almost universal. But, although more sediment is borne to the sea, part of the sand and mud, which in the natural state of things would be spread out by annual inundations over the plain, now subsides in the bottom of the river channels, and their capacity being thereby diminished, it is necessary, in order to prevent inundation in the following spring, to extract the matter from the bed and to add it to the banks of the river. Hence it happens that these streams now traverse the plain on the top of high mounds, like the waters of aqueducts, and at Ferrara the surface of the Po has become more elevated than the roofs of the houses. The magnitude of these barriers is a subject of increasing expense and anxiety, it having been sometimes found necessary to give an additional height of nearly 1 foot to the banks of the Adige and Po in a single season. The practice of embankment was adopted in some of the Italian rivers as early as the 13th century, and Dante, writing in the beginning of the 14th, describes in the 7th circle of hell a rivulet of tears separated from a burning sandy desert by embankments like those which, between Ghent and Bruges, were raised against the ocean, or those which the Paduans has erected along the Brenta to defend their villas on the melting of the alpine snows. Quali fiamminghi tra guzzante e bruggia, temendo il fiotto che inver lor s'avventa, fanno lo schermo perché il mar si fuggia, e quali padovan lungo la Brenta per difender lor ville e lor castelli, anzi che Carentana il caldo senta. Inferno, canto 15. In the Adriatic, from the northern part of the Gulf of Trieste, where this also enters, down to the south of Ravenna, there is an uninterrupted series of recent accessions of land, more than 100 miles in length, which, within the last 2,000 years, have increased from 2 to 20 miles in breadth. A line of sandbars of great length has been formed nearly all along the western coast of this gulf, inside of which are lagoons, such as those of Venice, and the large lagoon of Comacchio, 20 miles in diameter. Newly deposited mud, brought down by the streams, is continually lessening the depth of the lagoons, and converting part of them into meadows. These also, Tagliamento, Piave, Brenta, Adige, and Po, beside many other inferior rivers, contribute to this advantage of the coastline and to the shallowing of the lagoons and the gulf. Delta of the Po. The Po and the Adige may now be considered as entering by one common delta, for 2 branches of the Adige are connected with arms of the Po, and thus the principal delta has been pushed out beyond those bars which separate the lagoons from the sea. The rate of the advance of this new land has been accelerated, as before stated, since the system of embarking the rivers became general, especially at that point where the Po and Adige enter. The waters are no longer permitted to spread themselves far and wide over the plains, and to leave behind them the larger portion of their sediment. Mountain torrents also have become more turbid since the clearing away of the forests, which once clothed the southern flanks of the Alps. It is calculated that the mean rate of advance of the delta of the Po on the Adriatic between the years 1200 and 1600 was 25 yards or meters a year, whereas the mean annual gain from 1600 to 1804 was 70 meters. Adria was a seaport in the time of Augustus and had, in ancient times, given its name to the Gulf. It is now about 20 Italian miles inland. Ravenna was also a seaport, and is now about 4 miles from the main sea. Yet, even before the practice of embankment was introduced, the alluvium of the Po advanced with rapidity on the Adriatic, for Spina, a very ancient city, originally built in the district of Ravenna at the mouth of the great arm of the Po, was, so early as the commencement of our era, 11 miles distant from the sea. But, although so many rivers are rapidly converting the Adriatic into land, it appears, by the observation of M. Morlot, that since the time of the Romans there has been a general subsidence of the coast and bed of the sea in the same region to the amount of 5 feet, so that the advance of the new-made land has not been so fast as it would have been had the level of the coast remained unaltered. The signs of a much greater depression anterior to the historical period have also been brought to light by an artesian well, bored in 1847 to the depth of more than 400 feet, which still failed to penetrate through the modern fluviatile deposit. The auger passed chiefly through beds of sand and clay, but at 4 several depths, one of them very near the bottom of the excavation, it pierced beds of turf or accumulations of vegetable matter, precisely similar to those now formed superficially on the extreme borders of the Adriatic. Hence, we learn that a considerable area of what was once land has sunk down 400 feet in the course of ages. The greatest depth of the Adriatic, between Dalmatia and the mouth of the Po, is 22 fathoms, but a large part of the Gulf of Trieste and the Adriatic, opposite Venice, is less than 12 fathoms deep. Farther to the south, where it is less affected by the influx of great rivers, the gulf deepens considerably. Donati, after dredging the bottom, discovered the new deposits to consist partly of mud and partly of rock, the rock being formed of calcareous matter and crusting shells. He also ascertained that particular species of testacea were grouped together in certain places, and were becoming slowly incorporated with the mud or calcareous precipitates. Olivi, also, found some deposits of sand and others of mud, extending halfway across the gulf, and he states that their distribution along the bottom was evidently determined by the prevailing current. It is probable, therefore, that the final sediment of all the rivers at the head of the Adriatic may be intermingled by the influence of the current, and all the central parts of the gulf may be considered as slowly filling up with horizontal deposits, similar to those of the Subapennine hills, and containing many of the same species of shells. The Po merely introduced at present fine sand and mud, for it carries no pebbles farther than the spot where it joins the Trebbia, west of Piacenza. Near the northern borders of the basin, the Isonzo, Tagliamento, and many other streams are forming immense beds of sand and some conglomerate, for here some high mountains of alpine limestone approach within a few miles of the sea. In the time of the Romans, the hot baths of Monfalcone were on one of several islands of alpine limestone, between which and the mainland, on the north, was a channel of the sea, about a mile broad. This channel is now converted into a grassy plain, which surrounds the islands on all sides. Among the numerous changes on this coast, we find that the present channel of the Isonzo is several miles to the west of its ancient bed, in part of which, at Ronchi, the old Roman bridge which crossed the Via Appia was lately found buried in fluviatile silt. End of Chapter 17, Part 1. Recording by Emanuela. Chapter 17, Part 2 of Principle of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. ToddHW. Recording by Emanuela. Principle of Geology by Charles Lyell. Marine Delta of the Rhone. The lacustrine delta of the Rhone in Switzerland has already been considered. Its contemporaneous marine delta may not be described. Scarcely has the river passed out of the Lake of Geneva before its pure waters are again filled with sand and sediment by the impetuous Arve, descending from the highest Alps and bearing along in its current the granitic detritus annually brought down by the glaciers of Mont Blanc. The Rhone afterwards received a vast contribution of transported matter from the Alps of Dauphiné and the primary and volcanic mountains of central France, and when at length it entered the Mediterranean, it discolors the blue waters of that sea with a whitish sediment for the distance of between 6 and 7 miles, throughout which space the current of fresh water is perceptible. Strabo's description of the delta is so inapplicable to its present configuration as to attest a complete alteration in the physical features of the country since the Augustan age. It appears, however, that the head of the delta, or the point at which it begins to ramify, has remained unaltered since the time of Pliny, for he states that the Rhone divided itself at Arles into 2 arms. This is the case at present. One of the branches, the western, being now called Le Petit Rhône, which is again subdivided before entering the Mediterranean. The advance of the base of the delta in the last 18 centuries is demonstrated by many curious antiquarian monuments. The most striking of these is the great and unnatural detour of the old Roman road from Ugernum to Béziers, Bekere, which went round by Nîmes, Nemausus. It is clear that, when this was first constructed, it was impossible to pass in a direct line, as now, across the delta, and that either the sea or marshes intervened in a track now consisting of terra firma. Astruc also remarks that all the places on low lands lying to the north of the old Roman road between Nîmes and Béziers have names of Celtic origin, evidently given to them by the first inhabitants of the country, whereas the places lying south of that road toward the sea have names of Latin derivation and were clearly founded after the Roman language had been introduced. Another proof also of the great extent of land which has come into existence since the Romans conquered and colonized Gaul is derived from the fact that the Roman writers never mention the thermal waters of Balleruc in the delta, although they were well acquainted with those of Aix, and others still more distant, and attached great importance to them, as they invariably did to all hot springs. The waters of Balleruc, therefore, must have formerly issued under the sea, a common phenomenon on the borders of the Mediterranean, and, on the advance of the delta, they continued to flow out through the new deposits. Among the more direct proofs of the increase of land, we find the Mise described under the appellation of Mesua Collis by Pomponius Mela, and stated by him to be nearly an island, is now far inland. Notre-Dame-de-Port, also, was a harbour in 898, but is now a league from the shore. Psalmody was an island in 815, and is now 2 leagues from the sea. Several old lines of towers and sea marks occur at different distances from the present coast, all indicating the successive retreat of the sea, for each line has in its turn become useless to mariners, which may be well conceived when we state that the Tower of Tignon, erected on the shore so late as the year 1737, is already a mile remote from it. By the confluence of the Rhone and the currents of the Mediterranean, driven by winds from the south, sandbars are often formed across the mouths of the river. By these means, considerable spaces become divided off from the sea, and subsequently from the river also, when it shifts its channels of efflux. As some of these lagoons are subject to the occasional ingress of the river when flooded and of the sea during storms, they are alternately salt and fresh. Others, after being filled with salt water, are often lowered by evaporation till they become more salt than the sea. And it has happened, occasionally, that a considerable precipitate of muriate of soda has taken place in these natural salterns. During the latter part of Napoleon's career, when the excise laws were enforced with extreme rigor, the police was employed to prevent such salt from being used. The fluviatile and marine shells enclosed in these small lakes often live together in brackish water, but the uncongenial nature of the fluid usually produces a dwarfish size, and sometimes gives rise to strange varieties in form and color. Captain Smith, in his survey of the coast of the Mediterranean, found the sea opposite the mouth of the Rhone to deepen gradually from 4 to 40 fathoms, within a distance of 6 or 7 miles, over which the discolored fresh water extends, so that the inclination of the new deposits must be too slight to be appreciable in such an extent of section as a geologist usually obtains in examining ancient formations. When the wind blew from the southwest, the ships employed in the survey were obliged to quit their moorings, and when they returned, the new sand banks in the delta were found covered over with a great abundance of marine shells. By this means we learn how occasional beds of drifting marine shells may become interstratified with the fresh-water strata at a river's mouth. Stony nature of its deposits. That a great proportion, at least, of the new deposit in the delta of the Rhone consists of rock, and not of loose incoherent matter, is perfectly ascertained. In the museum at Montpellier is a cannon taken up from the sea near the mouth of the river, embedded in a crystalline calcareous rock. Large masses, also, are continually taken up of an arenaceous rock, cemented by calcareous matter, including multitudes of broken shells of recent species. The observation lately made on this subject corroborate the former statement of Marsilli, that the earthy deposit of the coast of Languedoc form a stony substance, for which reason he ascribes a certain bituminous, saline, and glutinous nature to the substances brought down with sand by the Rhone. If the number of mineral springs charged with carbonate of lime which fall into the Rhone and its feeders in different parts of France be considered, we shall feel no surprise at the lapidification of the newly deposited sediment in this delta. It should be remembered that the fresh water introduced by rivers, being lighter than the water of the sea, floats over the latter and remains upon the surface for a considerable distance. Consequently, it is exposed to as much evaporation as the waters of a lake, and the area over which the river water is spread at the junction of great rivers and the sea may well be compared, in point of extent, to that of considerable lakes. Now, it is well known that so great is the quantity of water carried off by evaporation in some lakes that it is nearly equal to the water flowing in, and in some inland seas, as the Caspian, it is quite equal. We may, therefore, well suppose that, in cases where a strong current does not interfere, the greater portion not only of the matter held mechanically in suspension, but of that also which is in chemical solution, may be precipitated at no great distance from the shore. When these finer ingredients are extremely small in quantity, they may only suffice to supply crustaceous animals, corals, and marine plants, with the earthy particles necessary for their secretions. But whenever it is in excess, as generally happens if the basin of a river lie partly in a district of active or extinct volcanoes, then will solid deposit be formed, and the shells will at once be included in a rocky mass. Coast of Asia Minor. Example of the advance of the land upon the sea are afforded by the southern coast of Asia Minor. Admiral Sir F. Beaufort has pointed out in his survey the great alterations effected since the time of Strabo, where heavens are filled up, islands join the mainland, and where the whole continent has increased many miles in extent. Strabo himself, on comparing the outline of the coast in his time with its ancient state, was convinced, like our countrymen, that it had gained very considerably upon the sea. The new formed strata of Asia Minor consist of stone, not of loose incoherent materials. Almost all the streamlets and rivers, like many of those in Tuscany and the south of Italy, hold abundance of carbonate of lime in solution, and precipitate travertine, or sometimes bind together the sand and gravel into solid sandstones and conglomerates. Every delta and sandbar thus acquires solidity, which often prevents streams from forcing their way through them, so that their mouths are constantly changing their position. Delta of the Nile. That Egypt was the gift of the Nile was the opinion of her priest before the time of Herodotus, and Rennell observes that the configuration and composition of the lowlands leave no room for doubt that the sea once washed the base of the rocks on which the pyramids of Memphis stand, the present base of which is washed by the inundation of the Nile at an elevation of 70 or 80 feet above the Mediterranean. But when we attempt to carry back our ideas to the remote period when the foundation of the delta was first laid, we are lost in the contemplation of so vast an interval of time. Herodotus observes that the country round Memphis seemed formerly to have been an arm of the sea gradually filled by the Nile, in the same manner as the Mender, Achelous, and other streams had formed deltas. Egypt, therefore, he says, like the Red Sea, was once a long narrow bay, and both gulfs were separated by a small neck of land. If the Nile, he adds, should by any means have an issue into the Arabian Gulf, it might chuck it up with earth in 20,000 or even perhaps in 10,000 years. And why may not the Nile have filled a still greater gulf with mud in the space of time which has passed before our age? The distance between Memphis and the most prominent part of the delta in a straight line north and south is about 100 geographical miles. The length of the base of the delta is more than 200 miles if we follow the coast between the ancient extreme eastern and western arms. But as these are now blocked up, that part only of Lower Egypt which intervenes between the Rosetta and Damietta branches is usually called the delta, the coastline of which is about 90 miles in length. The bed of the river itself, says Sir J. G. Wilkinson, undergoes a gradual increase of elevation varying in different places, and always lessening in proportion as the river approaches the sea. This increase of elevation in perpendicular height is much smaller in Lower than in Upper Egypt, and in the delta it diminishes still more, so that, according to an approximate calculation, the land about Elephantine, or the First Cataract, latitude 24 degrees 5, has been raised 9 feet in 1,700 years. At Thebes, latitude 25 degrees 43, about 7 feet, and at Heliopolis and Cairo, latitude 30 degrees, about 5 feet 10 inches. At Rosetta and the mouth of the Nile, latitude 31 degrees 30, the diminution in the perpendicular thickness of the deposit is lessened in a much greater decreasing ratio than in the straitened valley of Central and Upper Egypt, owing to the great extent, east and west, over which the inundation spreads. For this reason, the alluvial deposit does not cause the delta to protrude rapidly into the sea, although some ancient cities are now a mile or more inland, and the mouth of the Nile, mentioned by the early geographers, have been many of them silted up, and the outline of the coast entirely changed. The bed of the Nile always keeps pace with the general elevation of the soil, and the banks of this river, like those of the Mississippi and its tributaries, are much higher than the flat land at a distance, so that they are seldom covered during the highest inundations. In consequence of the gradual rise of the river's bed, the annual flood is constantly spreading over a wider area, and the alluvial soil encroaches on the desert, covering, to the depth of 6 or 7 feet, the base of statues and temples which the waters never reached 3,000 years ago. Although the sands of the Libyan deserts have in some places been drifted into the valley of the Nile, yet these aggressions, says Wilkinson, are far more than counterbalanced by the fertilizing effect of the water which now reaches farthing lands toward the desert, so that the number of square miles of arable soil is greater at present than at any previous period. Mud of the Nile. On comparing the different analyses which have been published of this mud, it will be found that it contains a large quantity of argillaceous matter, with much peroxide of iron, some carbonate of lime, and a small proportion of carbonate of magnesia. The latest and most careful analysis by M. Lassaigne shows a singularly close resemblance in the proportions of the ingredients of silica, alumina, iron, carbon, lime, and magnesia, and those observed in ordinary mica. But a much larger quantity of calcareous matter is sometimes present. In many places, as at Cairo, where artificial excavations have been made, or where the river has undermined its banks, the mud is seen to be thinly stratified, the upper part of each annual layer consisting of earth of a lighter color than the lower, and the whole separating easily from the deposit of the succeeding year. These annual layers are variable in thickness, but, according to the calculations of Girard and Wilkinson, the mean annual thickness of a layer at Cairo cannot exceed that of a sheet of thin pasteboard, and a stratum of 2 or 3 feet must represent the accumulation of 1,000 years. The depth of the Mediterranean is about 12 fathoms at a small distance from the shore of the delta. It afterwards increases gradually to 50, and then suddenly descends to 380 fathoms, which is, perhaps, the original depth of the sea where it has not been rendered shallower by fluviatile matter. We learn from Lieutenant Newbold that nothing but the finest and lightest ingredients reach the Mediterranean, where he has observed the sea discolored by them to the distance of 40 miles from the shore. The small progress of the delta in the last 2,000 years affords, perhaps, no measure for estimating its rate of growth when it was an inland bay, and had not yet protruded itself beyond the coastline of the Mediterranean. A powerful current now sweeps along the shores of Africa, from the Straits of Gibraltar to the prominent convexity of Egypt, the western side of which is continually the prey of the waves, so that not only are fresh accessions of land checked, but ancient parts of the delta are carried away. By this cause, Canopus and some other towns have been overwhelmed, but to this subject I shall again refer when speaking of tides and currents. End of Chapter 17, Part 2. Recording by Emanuela.
Chapter 18, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Chapter 18, Part 1. Reproductive effects of rivers continued. Deltas formed under the influence of tides. Basin and delta of the Mississippi. Alluvial plain. River banks and bluffs. Curves of the river. Natural rafts and snags. New lakes and effects of earthquakes. Antiquity of the delta. Delta of the Ganges and Brahmaputra. head of the delta and Sunderbans, islands formed and destroyed, crocodiles, amount of fluviatile sediment in the water, artesian boring at Calcutta, proofs of subsidence, age of the delta, convergence of deltas, origin of existing deltas not contemporaneous, grouping of strata and stratification in deltas, conglomerates, constant interchange of land and sea. In the last chapter, several examples were given of the deltas of inland seas, where the influence of the tides is almost imperceptible. We may next consider those marine or oceanic deltas where the tides play an important part in the dispersion of fluviatile sediment, as in the Gulf of Mexico, where they exert a moderate degree of force, and then in the Bay of Bengal, where they are extremely powerful. In regard to estuaries, which Reynolds termed negative deltas, they will be treated of more properly when our attention is specially turned to the operations of tides and currents, chapters 20, 21, and 22. In this case, instead of the land gaining on the sea at the river's mouth, the tides penetrate far inland beyond the general coastline. Basin and delta of the Mississippi. Alluvial plain. The hydrographical basin of the Mississippi displays, on the grandest scale, the action of running water on the surface of a vast continent. This magnificent river rises nearly in the 49th parallel of north latitude and flows to the Gulf of Mexico in the 29th, a course, including its meanders, of more than 3,000 miles. It passes from a cold climate, where the hunter obtains his furs and peltries, traverses the temperate latitudes, and discharges its waters into the sea in the region of rice, the cotton plant, and the sugar cane. From near its mouth at the Balize, a steamboat may ascend for 2,000 miles with scarcely any perceptible difference in the width of the river. Several of its tributaries, the Red River, the Arkansas, the Missouri, the Ohio, and others, would be regarded elsewhere as of the first importance, and taken together are navigable for a distance many times exceeding that of the main stream. No river affords a more striking illustration of the law before mentioned than an augmentation of volume does not occasion a proportional increase of surface, nay, is even sometimes attended with a narrowing of the channel. The Mississippi is half a mile wide at its junction with the Missouri, the latter being also of equal width, yet the united waters have only, from their confluence to the mouth of the Ohio, a medial width of about half a mile. The junction of the Ohio seems also to produce no increase, but rather a decrease of surface. The St. Francis, White, Arkansas, and Red Rivers are also absorbed by the main stream with scarcely any apparent increase of its width, although here and there it expands to a breadth of 1½ or even to 2 miles. On arriving at New Orleans, it is somewhat less than half a mile wide. Its depth there is very variable, the greatest at high water being 168 feet. The mean rate at which the whole body of water flows is variously estimated. According to Mr. Forshee, the mean velocity of the current at the surface somewhat exceeds 2 1/4 miles an hour when the water is at a mean height. For 300 miles above New Orleans, the distance measured by the winding river is about twice as great as the distance in a right line. For the first 100 miles from the mouth, the rate of fall is 1.80 inch per mile, for the second 100, 2 inches, for the third 2.30, for the fourth 2.57. The alluvial plain of the Mississippi begins to be of great width below Cape Girardeau, 50 miles above the junction of the Ohio. At this junction it is about 50 miles broad, south of which it contracts to about 30 miles at Memphis, expands again to 80 miles at the mouth of the White River, and then, after various contractions and expansions, protrudes beyond the general coastline in a large delta about 90 miles in width from northeast to southwest. Mr. Forshee estimates the area of the Great Plain as above defined at 31,200 square miles, with a circumference of about 3,000 miles, exceeding the area of Ireland. If that part of this plain which lies below or to the south of the branching off of the highest arm, called the Atchafalaya, be termed the delta, it constitutes less than half of the whole, being 14,000 square British miles in area. The delta may be said to be bounded on the east, west, and south by the sea, on the north chiefly by the broad valley plain, which entirely resembles it in character as in origin. The east and west boundaries of the alluvial region above the head of the delta consists of cliffs or bluffs, which on the east side of the Mississippi are very abrupt, and are undermined by the river at many points. They consist, from Baton Rouge in Louisiana, where they commence, as far north as the borders of Kentucky, of geological formations newer than the Cretaceous, the lowest being Eocene, and the uppermost consisting of loam, resembling the loess of the Rhine, and containing fresh water and land shells, almost all of existing species. These recent shells are associated with the bones of the mastodon, elephant, tapir, mylodon, horse, ox, and other quadrupeds, most of them of extinct species. I have endeavored to show, in my second visit to the United States, that this extensive formation of loam is either an ancient alluvial plain or a delta of the great river formed originally at a lower level and since upheaved and partially denuded. The Mississippi in that part of its course which is below the mouth of the Ohio frequently washes the eastern bluffs, but never once comes into contact with the western. These are composed of similar formations, but I learned from Mr. Forshee that they rise up more gently from the alluvial plain. It is supposed that the waters are thrown to the eastern side, because all the large tributary rivers entering from the west have filled that side of the Great Valley with their deltas, or with a sloping mass of clay and sand, so that the opposite bluffs are undermined, and the Mississippi is slowly but incessantly advancing eastward. Curves of the Mississippi. The river traverses the plain in a meandering course, describing immense curves. After sweeping round the half of a circle, it is carried in a rapid current diagonally across the ordinary direction of its channel to another curve of similar shape. Opposite to each of these, there is always a sandbar, answering in the convexity of its form to the concavity of the bend, as it is called. The river, by continually wearing these curves deep, returns, like many other streams before described, on its own track, so that a vessel in some places, after sailing for 25 or 30 miles, is brought round again to within a mile of the place whence it started. When the waters approach so near to each other, it often happens at high floods that they burst through the small tongue of land and insulate a portion, rushing through what is called the cut-off, so that vessels may pass from one point to another in half a mile, to a distance which it previously required a voyage of 20 miles to reach. As soon as the river has excavated the new passage, bars of sand and mud are formed at the 2 points of junction with the old bend, which is soon entirely separated from the main river by a continuous mud bank covered with wood. The old bend then becomes a semicircular lake of clear water, inhabited by large garfish, alligators, and wild fowl, which the steamboats have nearly driven away from the main river. A multitude of such crescent-shaped lakes, scattered far and wide over the alluvial plain, the greater number of them to the west, but some of them also eastward of the Mississippi, bear testimony of the extensive wanderings of the great stream in former ages. For the last 200 miles above its mouth, the course of the river is much less winding than above, there being only in the whole of that distance one great curve, that called the English turn, This great straightness of the stream is ascribed by Mr. Forshee to the superior tenacity of the banks, which are more clayey in this region. The Mississippi has been incorrectly described by some of the earlier geographers as a river running along the top of a long hill or mound in a plain. In reality, it runs in a valley, from 100 to 200 or more feet in depth, as A, C, B in Figure 24, its banks forming long strips of land parallel to the course of the main stream and to the swamps G, F, and D, E lying on each side. These extensive morasses, which are commonly well wooded, though often submerged for months continuously, are rarely more than 15 feet below the summit level of the banks. The banks themselves are occasionally overflowed, but are usually above water for a breadth of about 2 miles. They follow all the curves of the great river, and near New Orleans are raised artificially by embankments or levees, A.B. Figure 24, through which the river, when swollen, sometimes cuts a deep channel or crevasse, inundating the adjoining low lands and swamps, and not sparing the lower streets of the great city. The cause of the uniform upward slope of the river bank above the adjoining alluvial plain is this. When the waters charged with sediment pass over the banks in the flood season, their velocity is checked among the herbage and reeds, and they throw down at once the coarser and more sandy matter with which they are charged. But the fine particles of mud are carried farther on, so that at the distance of about 2 miles, a thin film of fine clay only subsides, forming a stiff, unctuous black soil, which gradually envelops the base of trees growing on the borders of the swamps. Waste of the banks. It has been said of a mountain torrent that it lays down what it will remove and removes what it has laid down, and in like manner the Mississippi, by the continual shifting of its course, sweeps away, during a great portion of the year, considerable tracts of alluvium, which were gradually accumulated by the overflow of former years, and the matter now left during the spring floods will be at some future time removed. After the flood season, when the river subsides within its channel, it acts with destructive force upon the alluvial banks, softened and diluted by the recent overflow. Several acres at a time, thickly covered with wood, are precipitated into the stream, and large portions of the islands are frequently swept away. Some years ago, observes Captain Hall, when the Mississippi was regularly surveyed, all its islands were numbered, from the confluence of the Missouri to the sea, but every season makes such revolutions, not only in the number, but in the magnitude and situation of these islands, that this enumeration is now almost obsolete. Sometimes large islands are entirely melted away, at other places they have attached themselves to the main shore, or, which is the more correct statement, the interval has been filled up by myriads of logs cemented together by mud and rubbish. Rafts. One of the most interesting features in the great rivers of this part of America is the frequent accumulation of what are termed rafts, or masses of floating trees, which have been arrested in their progress by snags, islands, shoals, or other obstructions, and made to accumulate so as to form natural bridges, reaching entirely across the stream. One of the largest of these was called the Raft of the Atchafalaya, an arm of the Mississippi, which was certainly at some former time the channel of the Red River, when the latter found its way to the Gulf of Mexico by a separate course. The Atchafalaya being in a direct line with the general direction of the Mississippi, catches a large portion of the timber annually brought down from the north, and the drift trees collected in about 38 years previous to 1816 formed a continuous raft no less than 10 miles in length, 220 yards wide, and 8 feet deep. The whole rose and fell with the water, yet was covered with green bushes and trees, and its surface enlivened in the autumn by a variety of beautiful flowers. It went on increasing till about 1835, when some of the trees upon it had grown to the height of about 60 feet. Steps were taken then by the state of Louisiana to clear away the whole raft and open the navigation, which was effected, not without great labor, in the space of 4 years. The rafts on Red River are equally remarkable. In some parts of its course, cedar trees are heaped up by themselves, and in other places pines. On the rise of the waters in summer, hundreds of these are seen, some with their green leaves still upon them, just as they have fallen from a neighboring bank, others leafless, broken and worn in their passage from a far distant tributary. Wherever they accumulate on the edge of a sandbar, they arrest the current and soon become covered with sediment. On this mud the young willows and the poplars called cottonwood spring up, their boughs still farther retarding the stream, and as the inundation rises, accelerating the deposition of new soil. The bank continuing to enlarge, the channel at length becomes so narrow that a single long tree may reach from side to side, and the remaining space is then soon choked up by a quantity of other timber. Unfortunately for the navigation of the Mississippi, observes Captain Hall, some of the largest trunks, after being cut down from the position on which they grew, get their roots entangled with the bottom of the river, where they remain anchored, as it were, in the mud. The force of the current naturally gives their tops a tendency downwards, and by its flowing past soon strips them of their leaves and branches. These fixtures, called snags or planters, are extremely dangerous to the steam vessels proceeding up the stream, in which they lie like a lance in rest, concealed beneath the water, with their sharp ends pointed directly against the bows of the vessels coming up. For the most part these formidable snags remain so still that they can be detected only by a slight ripple above them, not perceptible to inexperienced eyes. Sometimes, however, they vibrate up and down, alternately showing their heads above the surface and bathing them beneath it. So imminent until lately was the danger caused by these obstructions that almost all the boats on the Mississippi were constructed on a particular plan to guard against fatal accidents, but in the last 10 years, by the aid of the power of steam and the machinery of the snag boat, as it is called, the greater number of these trunks of trees have been drawn out of the mud. The prodigious quantity of wood annually drifted down by the Mississippi and its tributaries is a subject of geological interest, not merely as illustrating the manner in which abundance of vegetable matter becomes, in the ordinary course of nature, embedded in submarine and estuary deposits, but as attesting the constant destruction of soil and transportation of matter to lower levels by the tendency of rivers to shift their courses. Each of these trees must have required many years, some of them centuries, to attain their full size. The soil, therefore, whereon they grew, after remaining undisturbed for long periods, is ultimately torn up and swept away. It is also found in excavating at New Orleans, even at the depth of several yards below the level of the sea, that the soil of the delta contains innumerable trunks of trees, layer above layer, some prostrate as if drifted, others broken off near the bottom, but remaining still erect, and with their roots spreading on all sides, as if in their natural position. In such situations they appeared to me to indicate a sinking of the ground, as the trees must formerly have grown in marshes above the sea level. In the higher parts of the alluvial plain, for many hundred miles above the head of the delta, similar stools and roots of trees are also seen, buried in stiff clay at different levels, one above the other, and exposed to view in the banks at low water. They point clearly to the successive growth of forests in the extensive swamps of the plain, where the ground was slowly raised, year after year, by the mud thrown down during inundations. These roots and stools belong chiefly to the deciduous cypress, Taxodium disticum, and other swamp trees, and they bear testimony to the constant shifting of the course of the great river, which is always excavating land originally formed at some distance from its banks. Formation of lakes in Louisiana. Another striking feature in the basin of the Mississippi, illustrative of the changes now in progress, is the formation by natural causes of great lakes and the drainage of others. These are especially frequent in the basin of the Red River in Louisiana, where the largest of them, called Bistineau, is more than 30 miles long and has a medium depth of from 15 to 20 feet. In the deepest parts are seen numerous cypress trees of all sizes, now dead, and most of them with their tops broken by the wind, yet standing erect under water. This tree resists the action of air and water longer than any other, and, if not submerged throughout the whole year, will retain life for an extraordinary period. Lake Bistineau, as well as Black Lake, Caddo Lake, Spanish Lake, Natchitoches Lake, and many others have been formed, according to Darby, by the gradual elevation of the bed of Red River, in which the alluvial accumulations have been so great as to raise its channel and cause its waters during the flood season to flow up the mouths of many tributaries and to convert parts of their courses into lakes. In the autumn, when the level of Red River is again depressed, the waters rush back and some lakes become grassy meadows with streams meandering through them. Thus, there is a periodical flux and reflux between Red River and some of these basins, which are merely reservoirs, alternately emptied and filled, like our tide estuaries, with this difference that in the one case the land is submerged for several months continuously, and in the other twice in every 24 hours. It has happened in several cases that a raft of timber or a bar has been thrown by Red River across some of the openings of these channels, and then the lakes become, like Bistineau, constant repositories of water. But even in these cases, their level is liable to annual elevation and depression, because the flood of the main river, when at its height, passes over the bar, just as, where sandhills close the entrance of an estuary on the Norfolk or Suffolk coast, the sea, during some high tide or storm, has often breached the barrier and inundated again the interior. I am informed by Mr. Featherstonehaugh that the plains of the Red River and the Arkansas are so low and flat that whenever the Mississippi rises 30 feet above its ordinary level, those great tributaries are made to flow back and inundate a region of vast extent. Both the streams alluded to contain red sediment derived from the decomposition of red porphyry, and since 1833, when there was a great inundation in the Arkansas, an immense swamp has been formed near the Mamel Mountain, comprising 30,000 acres, with here and there large lagoons, where the old bed of the river was situated, in which innumerable trees, for the most part dead, are seen standing, of cypress, cottonwood, of poplar, the triple-thorned acacia, and others which are of great size. Their trunks appear as if painted red for about 15 feet from the ground, at which height a perfectly level line extends through the whole forest, marking the rise of the waters during the last flood. But most probably the causes above assigned for the recent origin of these lakes are not the only ones. Subterranean movements have altered. So lately as the years 1811 and 1812, the relative levels of various parts of the basin of the Mississippi, situated 300 miles northeast of Lake Bistineau. In those years, the Great Valley, from the mouth of the Ohio to that of the St. Francis, including a tract 300 miles in length, and exceeding in area the whole basin of the Thames, was convulsed to such a degree as to create new islands in the river and lakes in the alluvial plain. Some of these were on the left or east bank of the Mississippi, and were 20 miles in extent, as, for example, those named Reelfoot and Obion in Tennessee, formed in the channels or valleys of small streams bearing the same names. But the largest area affected by the great convulsion lies 8 or 10 miles to the westward of the Mississippi, and inland from the town of New Madrid in Missouri. It is called the Sunk Country, and is said to extend along the course of the White Water and its tributaries for a distance of between 70 and 80 miles north and south, and 30 miles or more east and west. Throughout this area, innumerable submerged trees, some standing leafless, others prostrate, are seen, and so great is the extent of lake and marsh that an active trade in the skins of muskrats, mink, otters, and other wild animals is now carried on there. In March 1846, I skirted the borders of the Sunk Country nearest to New Madrid, passing along the Bayou St. John and Little Prairie, where dead trees of various kinds, some erect in the water, others fallen, are strewed in dense masses over the bottom, in the shallows, and near the shore, were conspicuous. I also beheld countless rents in the adjoining dry alluvial plains, caused by the movements of the soil in 1811-1812, and still open, though the rains, frost, and river inundations have greatly diminished their original depth. I observed, moreover, numerous circular cavities called sunk holes, from 10 to 30 yards wide, and 20 feet or more in depth, which interrupt the general level of the plain. These were formed by the spouting out of large quantities of sand and mud during the earthquakes. That the prevailing changes of level in the delta and alluvial plain of the Mississippi have been caused by the subsidence, rather by the upheaval of land, appears to me established by the fact that there are no protuberances of upraised alluvial soil projecting above the level surface of the great plain. It is true that the gradual elevation of that plain by new accessions of matter would tend to efface every inequality derived from this source, but we might certainly have expected to find more broken ground between the opposite bluffs had local upthrows of alluvial strata been of repeated occurrence. End of chapter 18, part 1. Chapter 18, part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Chapter 18, Part 2. Antiquity of the Delta. The vast size of the alluvial plain, both above and below the head of the delta, or the branching off of the uppermost arm of the Atchafalaya, has been already alluded to. Its superficial dimensions, according to Mr. Forshee, exceed 30,000 square miles, nearly half of which belong to the true delta. The deposits consist partly of sand originally formed upon or near the banks of the river and its tributaries, partly of gravel swept down from the main channel, of which the position has continually shifted, and partly of fine mud slowly accumulated in the swamps. The farther we descend the river towards its mouth, the finer becomes the texture of the sediment. The whole alluvial formation, from the base of the delta upwards, slopes with a very gentle inclination, rising about 3 inches in a mile from the level of the sea at the Balize to the height of about 200 feet in a distance of about 800 miles. That a large portion of this fluviatile deposit, together with the fluvio-marine strata now in progress near the Balize, consists of mud and sand with much vegetable matter intermixed, may be inferred from what has been said of the abundance of drift trees flouted down every summer. These are seen matted together into a network around the extensive mud banks at the extreme mouth of the river. Every one acquainted with the geography of Louisiana is aware that the most southern part of the delta forms a long, narrow tongue of land protruding for 50 miles into the Gulf of Mexico, at the end of which are numerous channels of discharge. This singular promontory consists simply of the river and its two low, flat banks covered with reeds, young willows, and poplars. Its appearance answers precisely to that of the banks far in the interior, when nothing appears above water during inundations but the higher part of the sloping glacis or bank. In the one case we have the swamps or an expanse of fresh water with the tops of trees appearing above, in the other the bluish-green surface of the Gulf of Mexico. An opinion has very commonly prevailed that this narrow promontory, the newest product of the river, has gained very rapidly upon the sea since the foundation of New Orleans, but after visiting the Belize in 1846 in company with Dr. Carpenter, and making many inquiries of the pilots, and comparing the present outline of the coast with the excellent Spanish chart published by Charlevoix 120 years before, we came to a different conclusion. The rate of permanent advance of the new land has been very slow, not exceeding perhaps 1 mile in a century. The gain may have been somewhat more rapid in former years, when the new strip of soil projected less far into the Gulf, since it is now much more exposed to the action of a strong marine current. The tides also, when the waters of the river are low, enter into each opening and scour them out, destroying the banks of mud and the sandbars newly formed during the flood season. An observation of Darby in regard to the strata composing part of this delta deserves attention. In the steep banks of the Atchafalaya, before alluded to, the following section, he says, is observable at low water. First, an upper stratum, consisting invariably of bluish clay, common to the banks of the Mississippi. Below this, a stratum of red ochreous earth, peculiar to Red River, under which the blue clay of the Mississippi again appears, and this arrangement is constant, proving, as that geographer remarks, that the waters of the Mississippi and the Red River occupied alternately, at some former periods, considerable tracts below their present point of union. Such alternations are probably common in submarine spaces situated between two converging deltas, for, before the two rivers unite, there must almost always be a certain period when an intermediate tract will by turns be occupied and abandoned by the waters of each stream, since it can rarely happen that the season of highest flood will precisely correspond in each. In the case of the Red River and Mississippi, which carry off the waters from countries placed under widely distant latitudes, an exact coincidence in the time of greatest inundation is very improbable. The antiquity of the delta or length of the period which has been occupied in the deposition of so vast a mass of alluvial matter is a question which may well excite the curiosity of every geologist. Sufficient data have not yet been obtained to afford a full and satisfactory answer to the inquiry, but some approximation may already be made to the minimum of time required. When I visited New Orleans in February 1846, I found that Dr. Riddell had made numerous experiments to ascertain the proportion of sediment contained in the waters of the Mississippi, and he concluded that the mean annual amount of solid matter was to the water as 1 to 1,245 in weight, or about 1 to 3,000 in volume. From the observations of the same gentleman and those of Dr. Carpenter and Mr. Forshee, an eminent engineer, to whom I have before alluded, the average width, depth, and velocity of the Mississippi, and thence the mean annual discharge of water were deduced. I assumed 528 feet, or the tenth of a mile, as the probable thickness of the deposit of mud and sand in the delta, founding my conjecture chiefly on the depth of the Gulf of Mexico, between the southern point of Florida and the Balize, which equals on an average 100 fathoms, and partly, on some borings, 600 feet deep in the delta near Lake Pontchartrain, north of New Orleans, in which the bottom of the alluvial matter is said not to have been reached. The area of the delta being about 13,600 square statute miles, and the quantity of solid matter annually brought down by the river 3,702,758,400 cubic feet, it must have taken 67,000 years for the formation of the whole, and if the alluvial matter of the plain above be 264 feet deep, or half that of the delta, it must have required 33,500 more years for its accumulation, even if its area be estimated as only equal to that of the delta, whereas it is in fact larger. If some deduction be made from the time here stated, in consequence of the effect of the driftwood, which must have aided in filling up more rapidly the space above alluded to, a far more important allowance must be made, on the other hand, for the loss of matter, owing to the finer particles of mud not settling at the mouth of the river, but being swept out far to sea during the predominant action of the tides and the waves in the winter months, when the current of fresh water is feeble. Yet, however, vast the time during which the Mississippi has been transporting its earthy burden to the ocean, the whole period, though far exceeding perhaps 100,000 years, must be insignificant in a geological point of view, since the bluffs or cliffs bounding the Great Valley, and therefore older in date, and which are from 50 to 250 feet in perpendicular height, consist in great part of loam containing land, fluviatile, and lacustrine shells of species still inhabiting the same country. Before we take leave of the great delta, we may derive an instructive lesson from the reflection that the new deposits already formed, or now accumulating, whether marine or freshwater, must greatly resemble in composition, and the general character of their organic remains, many ancient strata which entered largely into the earth's structure. Yet there is no sudden revolution in progress, whether on the land or in the waters, whether in the animate or in the inanimate world. Notwithstanding the excessive destruction of soil and uprooting of trees, the region which yields a never-failing supply of driftwood is densely clothed with noble forests, and is almost unrivaled in its power of supporting animal and vegetable life. In spite of the undermining of many a lofty bluff and the encroachments of the delta on the sea, in spite of the earthquake which rends and fissures the soil, or causes areas more than 60 miles in length to sink down several yards in a few months, the general features of the district remain unaltered, or are merely undergoing a slow and insensible change. Herds of wild deer graze on the pastures, or browse upon the trees, and if they diminish in number it is only where they give way to man and the domestic animals which follow in his train. The bear, the wolf, the fox, the panther, and the wild cat still maintain themselves in the fastnesses of the forests of cypress and gum tree. The raccoon and the opossum are everywhere abundant, while the muskrat, otter, and mink still frequent the rivers and lakes, and a few beavers and buffaloes have not yet been driven from their ancient haunts. The waters teem with alligators, tortoises, and fish, and their surface is covered with millions of migratory waterfowl, which perform their annual voyage between the Canadian lakes and the shores of the Mexican Gulf. The power of man begins to be sensibly felt, and many parts of the wilderness to be replaced by towns, orchards, and gardens. The gilded steamboats, like moving palaces, stem the force of the current, or shoot rapidly down the descending stream through the solitudes of the forests and prairies. Already does the flourishing population of the Great Valley far exceed that of the 13 United States when first they declared their independence. Such is the state of a continent where trees and stones are harried annually by 1,000 torrents from the mountains to the plains, and where sand and finer matter are swept down by a vast current to the sea, together with the wreck of countless forests and the bones of animals which perish in the inundations. When these materials reach the Gulf, they do not render the waters unfit for aquatic animals, but on the contrary, the ocean here swarms with life, as it generally does, where the influx of a great river furnishes a copious supply of organic and mineral matter. Yet many geologists, when they behold the spoils of the land heaped in successive strata, and blended confusedly with the remains of fishes, or interspersed with broken shells and corals, when they see portions of erect trunks of trees, with their roots still retaining their natural position, and one tier of these preserved in a fossil state above another, imagine that they are viewing the signs of a turbulent instead of a tranquil and settled state of the planet. They read in such phenomena the proof of chaotic disorder and reiterated catastrophes, instead of indications of a surface as habitable as the most delicious and fertile districts now tenanted by man. As an example of still larger delta advancing upon the sea in opposition to more powerful tides, I shall next describe that of the Ganges and Brahmaputra, or Burramputta. These, the two principal rivers of India, descend from the highest mountains in the world, and partially mingle their waters in the low plains of Hindustan before reaching the head of the Bay of Bengal. The Brahmaputra, somewhat the larger of the two, formerly passed to the east of Dhaka, even so lately as the beginning of the present century, pouring most of its waters into one of the numerous channels in the delta called the Meghna. By that name the main stream was always spoken of by Rennell and others in their memoirs of this region. But the main trunk now unites with an arm of the Ganges considerably higher up, at a point about 100 miles distant from the sea, and it is constantly, according to Dr. Hooker, working its way westward, having formerly, as may be seen by ancient maps, moved eastward for a long period. The area of the delta of the combined rivers, for it is impossible now to distinguish what belongs to each, is considerably more than double that of the Nile, even if we exclude from the delta a large extent of low, flat alluvial plain, doubtless of fluviatile origin, which stretches more than 100 miles to the hills west of Calcutta (see map at Figure 25), and much farther in the northerly direction beyond the head of the great delta. The head of the delta is that point where the first arm is given off. Above that point a river receives the waters of tributaries flowing from higher levels. Below it, on the contrary, it gives out portions of its waters to lower levels, through channels which flow into adjoining swamps, or which run directly to the sea. The Mississippi, as before described, has a single head, which originated at an unknown period when the Red River joined it. In the great delta of Bengal there may be said to be two heads nearly equidistant from the sea, that of the Ganges (G. map figure 25), about 30 miles below Rajmahal, or 216 statute miles in a direct line from the sea, and that of the Brahmaputra (B.) below Cherrapunji, where the river issues from the Khassia Mountains, a distance of 224 miles from the Bay of Bengal. It will appear by reference to the map that the great body of fresh water derived from the two rivers enters the bay on its eastern side, and that a large part of the delta bordering on the sea is composed of a labyrinth of rivers and creeks, all filled with salt water except those immediately communicating with the Hooghly, or principal arm of the Ganges. This tract alone, known by the name of the Woods, or Sundarbans, more properly Sundarbans, a wilderness infested by tigers and crocodiles, is, according to Rennell, equal in extent to the whole Principality of Wales. On the sea coast there are 8 great openings, each of which has evidently, at some ancient period, served in its turn as the principal channel of discharge. Although the flux and reflux of the tide extend even to the heads of the delta when the rivers are low, yet when they are periodically swollen by tropical rains, their volume and velocity counteract the tidal current, so that, except very near the sea, the ebb and flow become insensible. During the flood season, therefore, the Ganges and Brahmaputra almost assume in their delta the character of rivers entering an inland sea, the movements of the ocean being then subordinate to the force of the rivers, and only slightly disturbing their operations. The great gain of the delta in height and area takes place during the inundations, and during other seasons of the year the ocean makes reprisals, scoring out the channels and sometimes devouring rich alluvial plains. Islands formed and destroyed. Major R. H. Culebrook, in his account of the course of the Ganges, relates examples of the rapid filling up of some of its branches, and the excavation of new channels, where the number of square miles of soil removed in a short time, the column of the earth being 114 feet high, was truly astonishing. 40 square miles, or 25,600 acres, are mentioned as having been carried away in one place in the course of a few years. The immense transportation of earthy matter by the Ganges and Brahmaputra is proved by the great magnitude of the islands formed in their channels during a period far short of that of a man's life. Some of these, many miles in extent, have originated in large sandbanks thrown up round the points at the angular turning of the rivers, and afterwards insulated by breaches of the streams. Others, formed in the main channel, are caused by some obstruction at the bottom. A large tree or a sunken boat is sometimes sufficient to check the current and cause a deposit of sand, which accumulates till it usurps a considerable portion of the channel. The river then undermines its banks on each side, to supply the deficiency of its bed, and the island is afterwards raised by fresh deposits during every flood. In the great gulf below Lakipore, formed by the united waters of the Ganges and Meghna, some of the islands, says Rennell, rival in size and fertility the Isle of Wight. While the river is forming new islands in one part, it is sweeping away old ones in others. Those newly formed are soon overrun with reeds, long grass, the Tamarix indica, and other shrubs, forming impenetrable thickets where the tiger, the rhinoceros, the buffalo, deer, and other wild animals take shelter. It is easy, therefore, to perceive that both animal and vegetable remains may occasionally be precipitated into the flood and become embedded in the sediment which subsides in the delta. 3 or 4 species of crocodile, of 2 distinct subgenera, abound in the Ganges and its tributary and contiguous waters, and Mr. H. T. Culebrook informed me that he had seen both forms in places far inland, many hundred miles from the sea. The Gangetic crocodile, or gavial, incorrect orthography Gariel, is confined to the fresh water, living exclusively on fish, but the commoner kinds, called kumiach and mugar, frequent both fresh and salt, being much larger and fiercer in salt and brackish water. These animals swarm in the brackish water along the line of sandbanks, where the advance of the delta is most rapid. Hundreds of them are seen together in the creeks of the delta, or basking in the sun on the shoals without. They will attack men and cattle, destroying the natives when bathing, and tame and wild animals which come to drink. I have not unfrequently, says Mr. Culebrook, been witness to the horrid spectacle of a floating corpse seized by a crocodile with such avidity that he half emerged above the water with his prey in his mouth. The geologist will not fail to observe how peculiarly the habits and distribution of these saurians expose them to become embedded in the horizontal strata of fine mud, which are annually deposited over many hundred square miles in the Bay of Bengal. The inhabitants of the land which happen to be drowned or thrown into the water are usually devoured by these voracious reptiles, but we may suppose the remains of the saurians themselves to be continually entombed in the new formations. The number also of bodies of the poorer class of Hindus thrown annually into the Ganges is so great that some of their bones or skeletons can hardly fail to be occasionally enveloped in a fluviatile mud. It sometimes happens at the season when the periodical flood is at its height, that a strong gale of wind, conspiring with a high spring tide, checks the descending current of the river and gives rise to most destructive inundations. From this cause, in 1763, the waters at Lakipur rose 6 feet above their ordinary level, and the inhabitants of a considerable district, with their houses and cattle, were totally swept away. The population of all oceanic deltas are particularly exposed to suffer by such catastrophes, recurring at considerable intervals of time, and we may safely assume that such tragical events have happened again and again since the Gangetic delta was inhabited by man. If human experience and forethought cannot always guard against these calamities, still less can the inferior animals avoid them, and the monuments of such disastrous inundations must be looked for in great abundance in strata of all ages, if the surface of our planet has always been governed by the same laws. When we reflect on the general order of tranquillity that reigns in the rich and populous delta of Bengal, notwithstanding the havoc occasionally committed by the depredations of the ocean, we perceive how unnecessary it is to attribute the embedding of successive races of animals in older strata to extraordinary energy in the causes of decay and reproduction in the infancy of our planet, or to those general catastrophes and sudden revolutions so often resorted to. End of Chapter 18, Part 2. Chapter 18, Part 3 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Chapter 18, Part 3. Deposits in the Delta. The quantity of mud held in suspension by the waters of the Ganges and Brahmaputra is found, as might be expected, to exceed that of any of the rivers alluded to in this or the preceding chapters. For, in the first place, their feeders flow from mountains of unrivalled altitude, and do not clear themselves in any lakes, as does the Rhine in the Lake of Constance or the Rhone in that of Geneva. And secondly, their whole course is nearer the equator than that of the Mississippi or any great river, respecting which careful experiments have been made, to determine the quantity of its water and earthy contents. The fall of rain, moreover, as we have before seen, is excessive on the southern flanks of the first range of mountains which rise from the plains of Hindustan, and still more remarkable is the quantity sometimes poured down in one day. See above, page 200. The sea, where the Ganges and Brahmaputra discharge their main stream at the flood season, only recovers its transparency at the distance of from 60 to 100 miles from the delta, and we may take for granted that the current continues to transport the finer particles much farther south than where the surface water first becomes clear. The general slope, therefore, of the new strata must be extremely gentle. According to the best charts, there is a gradual deepening from 4 to about 60 fathoms, as we proceed from the base of the delta to the distance of about 100 miles into the Bay of Bengal. At some few points 70 or even 100 fathoms are obtained at that distance. One remarkable exception, however, occurs to the regularity of the shape of the bottom. Opposite the middle of the delta, at the distance of 30 or 40 miles from the coast, a deep submarine valley occurs, called the Swatch of No Ground, about 15 miles in diameter, where soundings of 180 and even 300 fathoms fail to reach the bottom. This phenomenon is the more extraordinary since the depression runs north to within 5 miles of the line of shoals, and not only do the waters charged with sediment pass over it continually, but during the monsoons the sea, loaded with mud and sand, is beaten back in that direction towards the delta. As the mud is known to extend for 80 miles farther into the Gulf, an enormous thickness of matter must have been deposited in the Swatch. We may conclude, therefore, either that the original depth of this part of the Bay of Bengal was excessive, or that subsidences have occurred in modern times. The latter conjecture is the less improbable, as the whole area of the delta has been convulsed in the historical era by earthquakes, and actual subsidences have taken place in the neighboring coast of Chittagong, while the Swatch lies not far from the volcanic band which connects Sumatra, Barren Island, and Rambri. Opposite the mouth of the Hooghly River, and immediately south to Sogor Island, 4 miles from the nearest land of the delta, a new islet was formed about 20 years ago called Edmondstone Island, on the center of which a beacon was erected as a landmark in 1817. In 1818 the island had become 2 miles long and half a mile broad, and was covered with vegetation and shrubs. Some houses were then built upon it, and in 1820 it was used as a pilot station. The severe gale of 1823 divided it into 2 parts, and so reduced its size as to leave the beacon standing out in the sea, where, after remaining 7 years, it was washed away. The islet in 1836 had been converted by successive storms into a sandbank half a mile long, on which a sea mark was placed. Although there is evidence of gain at some points, the general progress of the coast is very slow, for the tides, when the river water is low, are actively employed in removing alluvial matter. In the Sundarbans, the usual rise and fall of the tides is no more than 8 feet, but on the east side of the delta, Dr. Hooker observed, in the winter of 1851, a rise of from 60 to 80 feet, producing among the islands at the mouth of the Meghna and Feni rivers a lofty wave or bore as they ascend, and causing the river water to be pounded back, and then to sweep down with great violence when the tide ebbs. The bay for 40 miles south of Chittagong is so fresh that neither algae nor mangroves will grow in it. We may therefore conceive how effective may be the current formed by so great a volume of water in dispersing fine mud over a wide area. Its power is sometimes augmented by the agitation of the bay during hurricanes in the month of May. The new superficial strata consists entirely of fine sand and mud. Such at least are the only materials which are exposed to view in regular beds on the banks of the numerous creeks. Neither here or higher up the Ganges could Dr. Hooker discover any land or fresh-water shells in sections of the banks, which in the plains higher up sometimes form cliffs 80 feet in height at low water. In like manner I have stated that I was unable to find any buried shells in the delta of modern river cliffs of the Mississippi. No substance so coarse as gravel occurs in any part of the delta of the Ganges and Brahmaputra, nor nearer the sea than 400 miles. Yet it is remarkable that the boring of an artesian well at Fort William near Calcutta in the years 1835-1840, displayed at the depth of 120 feet clay and sand with pebbles. This boring was carried to a depth of 481 feet below the level of Calcutta, and the geological section obtained in the operation has been recorded with great care. Under the surface soil, at a depth of about 10 feet, they came to a stiff blue clay about 40 feet in thickness, below which was sandy clay, containing in its lower portion abundance of decayed vegetable matter, which at the bottom assumed the character of a stratum of black peat 2 feet thick. This peaty mass was considered as a clear indication, like the dirt bed of Portland, of an ancient terrestrial surface, with a forest or sunderbund vegetation. Logs and branches of a red-colored wood occur both above and immediately below the peat, so little altered that Dr. Wallich was able to identify them with the Sondri tree, Heritiera littoralis, one of the most prevalent forms at the base of the delta. Dr. Falconer tells me that similar peat has been met with at other points round Calcutta at the depth of 9 feet and 25 feet. It appears, therefore, that there has been a sinking down of what was originally land in this region to the amount of 70 feet or more perpendicular, for Calcutta is only a few feet above the level of the sea, and the successive peat beds seem to imply that the subsidence of the ground was gradual or interrupted by several pauses. Below the vegetable mass they entered upon a stratum of yellowish clay about 10 feet thick, containing horizontal layers of kunkar or kankar, a nodular, concretionary, argillaceous limestone, met with abundantly at greater or less depth in all parts of the valley of the Ganges, over many thousand square miles, and always presenting the same characters even at a distance of 1,000 miles north of Calcutta. Some of this kankar is said to be of very recent origin in deposits formed by river inundations near Saharanpur. After penetrating 120 feet, they found loam containing water-worn fragments of mica slate and other kinds of rock, which the current of the Ganges can no longer transport to this region. In the various beds pierced through below, consisting of clay, marl, and friable sandstone, with kankar here and there intermixed, no organic remains of decidedly marine origin were met with. Too positive a conclusion ought not, it is true, to be drawn from such a fact, when we consider the narrow bore of the auger and its effect in crushing shells and bones. Nevertheless, it is worthy of remark that the only fossils obtained in a recognizable state were of a fluviatile or terrestrial character. Thus, at the depth of 350 feet, the bony shell of a tortoise, a Trionyx, a freshwater genus, was found in sand, resembling the living species of Bengal. From the same stratum also they drew up the lower half of the humerus of a ruminant, at first referred to a hyena. It was the size and shape, says Dr. Falconer, of the shoulder bone of the Cervus porcinus, or common hog deer of India. At the depth of 380 feet, clay with fragments of lacustrine shells was incumbent on what appears clearly to have been another dirt bed, or stratum of decayed wood, implying a period of repose of some duration and a forest-covered land, which must have subsided 300 feet to admit of the subsequent superposition of the overlying deposits. It has been conjectured that, at the time when this area supported trees, the land extended much further out into the Bay of Bengal than now, and that in later times the Ganges, while enlarging its delta, has been only recovering lost ground from the sea. At the depth of about 400 feet below the surface, an abrupt change was observed in the character of the strata, which were composed in great part of sand, shingle, and boulders, the only fossils observed being the vertebrae of a crocodile, shell of a Trionyx, and fragments of wood very little altered, and similar to that buried in beds far above. These gravelly beds constituted the bottom of the section at the depth of 481 feet, when the operations were discontinued in consequence of an accident which happened to the auger. The occurrence of pebbles at the depths of 120 and 400 feet implies an important change in the geographical condition of the region around or near Calcutta. The fall of the river or the general slope of the alluvial plain may have been formerly greater, or, before a general and perhaps unequal subsidence, hills once nearer the present base of the delta may have risen several hundred feet, forming islands in the bay, which may have sunk gradually and become buried under fluviatile sediment. Antiquity of the delta. It would be a matter of no small scientific interest if experiments were made to enable us to determine, with some degree of accuracy, the mean quantity of earthy matter discharged annually into the sea by the united waters of the Ganges and Brahmaputra. The Reverend Mr. Everest instituted, in 1831-32, a series of observations on the earthy matter brought down by the Ganges at the Ghazipur, 500 miles from the sea. He found that in 1831 the number of cubic feet of water discharged by the river per second at that place was, during the rains, 4 months, 494,208; during the winter, 5 months, 71,200; during the hot weather, 3 months, 36,330. So that we may state in round numbers that 500,000 cubic feet per second flow down during the 4 months of the flood season, from June to September, and less than 60,000 per second during the remaining 8 months. The average quantity of solid matter suspended in the water during the rains was, by weight, 1/428th part, but as the water is about 1/2 the specific gravity of the dried mud, the solid matter discharged is 1/856th part in bulk, or 577 cubic feet per second. This gives a total of 6,082,041,600 cubic feet for the discharge in the 122 days of the rain. The proportion of sediment in the waters at other seasons was comparatively insignificant, the total amount during the 5 winter months being only 247,881,600 cubic feet, and during the 3 months of hot weather 38,154,240 cubic feet. The total annual discharge then would be 6,368,077,440 cubic feet. This quantity of mud would in 1 year raise a surface of 228.5 square miles, or a square space, each side of which should measure 15 miles, a height of 1 foot. To give some idea of the magnitude of this result, we will assume that the specific gravity of the dried mud is only 1/2 that of granite. It would, however, be more. In that case, the earthy matter discharged in a year would equal 3,184,038,720 cubic feet of granite. Now, about 12.5 cubic feet of granite weighed 1 ton, and it is computed that the Great Pyramid of Egypt, if it were of solid mass of granite, would weigh about 600 million tons. The mass of matter therefore carried down annually would, according to this estimate, more than equal in weight and bulk 42 of the Great Pyramids of Egypt, and that borne down in the 4 months of the rains would equal 40 pyramids. But if, without any conjecture as to what may have been the specific gravity of the mud, we attend merely to the weight of solid matter actually proved by Mr. Everest to have been contained in the water, we find that the number of tons weight which passed down in the 122 days of the rainy season was 339,413,760, which would give the weight of 56 pyramids and a half, and in the whole year 355,361,464 tons, or nearly the weight of 60 pyramids. The base of the Great Pyramid of Egypt covers 11 acres, and its perpendicular height is about 500 feet. It is scarcely possible to present any picture to the mind which will convey an adequate conception of the mighty scale of this operation, so tranquilly and almost insensibly carried on by the Ganges, as it glides through its alluvial plain, even at a distance of 500 miles from the sea. It may, however, be stated that if a fleet of more than 80 Indiamen, each freighted with about 1,400 tons weight of mud, were to sail down the river every hour of every day and night for 4 months continuously, they would only transport from the higher country to the sea a mass of solid matter equal to that borne down by the Ganges, even in this part of its course, in the 4 months of the flood season. Or the exertions of a fleet of about 2,000 such ships, going down daily with the same burden, and discharging it into the Gulf, would be no more than equivalent to the operations of the great river. The most voluminous current of lava which was flowed from Etna within historical times was that of 1669. Ferrara, after correcting Borelli's estimate, calculated the quantity of cubic yards of lava in this current at 140 million. Now this would not equal in bulk 1/5 of the sedimentary matter which is carried down in a single year by the Ganges, past Ghazipur, according to the estimate above explained, so that it would require 5 grand eruptions of Etna to transfer a mass of lava from the subterranean regions to the surface, equal in volume to the mud carried down in 1 year to that place. Captain R. Stacey, of the Bengal Engineers, has remarked to me not only that Ghazipur, where Mr. Everest's observations were made, is 500 miles from the sea, but that the Ganges has not been joined there by its most important feeders. These drain upon the whole 750 miles of the Himalaya, and no more than 150 miles of that mountain chain have sent their contributions to the main trunk at Ghazipur. Below that place, the Ganges is joined by the Gogra, Gunduk, Kosi, and Tista from the north, to say nothing of the Sone flowing from the south, one of the largest of the rivers which rise in the tableland of central India. See map, figure 25. Moreover, the remaining 600 miles of the Himalaya comprise that eastern portion of the basin where the rains are heaviest. The quantity of water therefore carried down to the sea may probably be 4 or 5 times as much as that which passes Ghazipur. The Brahmaputra, according to Major Wilcox, in the month of January, when it is near its minimum, discharges 150,000 cubic feet of water per second at Gwalpara, not many miles above the head of its delta. Taking the proportions observed at Ghazipur at the different seasons as a guide, the probable average discharge of the Brahmaputra for the whole year may be estimated at about the same as that of the Ganges. Assuming this, and secondly, in order to avoid the risk of exaggeration, that the proportion of sediment in their waters is about 1/3 less than Mr. Everest's estimate, the mud borne down to the Bay of Bengal in 1 year would equal 40,000 millions of cubic feet, or between 6 and 7 times as much as that brought down to Ghazipur, according to Mr. Everest's calculations in 1831, and 10 times as much as that conveyed annually by the Mississippi to the Gulf of Mexico. Captain Strachey estimates the annually inundated portion of the delta at 250 miles in length by 80 in breadth, making an area of 20,000 square miles. The space south of this, in the bay, where sediment is thrown down, may be 300 miles from east to west by 150 north to south, or 45,000 square miles, which added to the former gives a surface of 65,000 square miles, over which the sediment is spread out by the two rivers. Suppose then the solid matter to amount to 40,000 millions of cubic feet per annum. The deposit, he observes, must be continued for 45 years and 3/10 to raise the whole area a height of 1 foot, or 13,600 years to raise it 300 feet, and this, as we have seen, is much less than the thickness of the fluviatile strata actually penetrated, and the bottom not reached by the auger at Calcutta. Nevertheless, we can by no means deduce from these data alone what will be the future rate of advance of the delta, nor even predict whether the land will gain on the sea or remain stationary. At the end of 13,000 years, the bay may be less shallow than now, provided a moderate depression, corresponding to that experienced in part of Greenland for many centuries, shall take place. See Chapter 30. A subsidence quite insensible to the inhabitants of Bengal, not exceeding 2 feet 3 inches in a century, would be more than sufficient to counterbalance all the efforts of the two mighty rivers to extend the limits of their delta. We have seen that the artesian borings at Calcutta attest, what the vast depth of the swatch may also in all likelihood indicate, that the antagonist force of subsidence has predominated for ages over the influx of fluviatile mud, preventing it from raising the plains of Bengal or from filling up a larger portion of the bay. End of Chapter 18, Part 3. Chapter 18, Part 4 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Chapter 18, Part 4. Concluding remarks on deltas. Convergence of deltas. If we possessed an accurate series of maps of the Adriatic for many thousand years, our retrospect would without doubt carry us gradually back to the time when the number of rivers descending from the mountains into that gulf by independent deltas was far greater in number. The deltas of the Po and the Adige, for instance, would separate themselves within the recent era, as in all probability would those of the Isonzo and the Tor. If, on the other hand, we speculate on future changes, we may anticipate the period when the number of deltas will greatly diminish, for the Po cannot continue to encroach at the rate of a mile in 100 years, and other rivers to gain as much in 6 or 7 centuries upon the shallow gulf, without new junctions occurring from time to time, so that Eridanus, the king of rivers, will continually boast a greater number of tributaries. The Ganges and the Brahmaputra have perhaps become partially confluent in the same delta within the historical, or at least within the human era, and the date of the junction of the Red River and the Mississippi would, in all likelihood, have been known if America had not been so recently discovered. The union of the Tigris and the Euphrates must undoubtedly have been one of the modern geographical changes of our earth, for Colonel Rawlinson informs me that the delta of those rivers has advanced 2 miles in the last 60 years, and is supposed to have encroached about 40 miles upon the Gulf of Persia in the course of the last 25 centuries. When the deltas of rivers, having many mouths, converge, a partial union at first takes place by the confluence of some one or more of their arms, but it is not until the main trunks are connected above the head of the common delta that a complete intermixture of their joint waters and sediment takes place. The union, therefore, of the Po and Adige, and of the Ganges and Brahmaputra is still incomplete. If we reflect on the geographical extent of surface drained by rivers such as now enter the Bay of Bengal, and then consider how complete the blending together of the greater part of their transported matter has already become, and throughout how vast a delta it is spread by numerous arms, we no longer feel so much surprise at the area occupied by some ancient formations of homogeneous mineral composition, but our surprise will be still farther lessened when we afterwards inquire, Chapter 21, into the action of tides and currents in disseminating sediment. Age of existing deltas. If we could take for granted that the relative level of land and sea had remained stationary ever since all the existing deltas began to be formed, could we assume that their growth commenced at one and the same instant when the present continents acquired their actual shape, we might understand the language of geologists who speak of the epoch of existing continents. They endeavor to calculate the age of deltas from this imaginary fixed period, and they calculate the gain of new land upon the sea at the mouths of the rivers as having begun everywhere simultaneously. But the more we study the history of deltas, the more we become convinced that upward and downward movements of the land and contiguous bed of the sea have exerted, and continue to exert, an influence on the physical geography of many hydrographical basins on a scale comparable in magnitude or importance to the amount of fluviatile deposition effected in an equal lapse of time. In the basin of the Mississippi, for example, proofs both of descending and ascending movements to a vertical amount of several hundred feet can be shown to have taken place since the existing species of land and freshwater shells lived in that region. The deltas also of the Po and Ganges have each, as we have seen, when probed by the Artesian auger, borne testimony to a gradual subsidence of land to the extent of several hundred feet, old terrestrial surfaces, turf, peat, forest land, and dirt beds having been pierced at various depths. The changes of level at the mouth of the Indus in Kutch, and those of New Madrid in the valley of the Mississippi, are equally instructive as demonstrating unceasing fluctuations in the levels of those areas into which running water is transporting sediment. If, therefore, the exact age of all modern deltas could be known, it is scarcely probable that we should find any two of them in the world to have coincided in date, or in the time when their earliest deposits originated. Grouping of strata in deltas. The changes which have taken place in deltas, even within the times of history, may suggest many important considerations in regard to the manner in which subaqueous sediment is distributed. With the exception of some cases hereafter to be noticed, there are some general laws of arrangement which must evidently hold good in almost all the lakes and seas now filling up. If a lake, for example, be encircled on two sides by lofty mountains, receiving from them many rivers and torrents of different sizes, and if it be bounded on the other sides, where the surplus waters issue, by a comparatively low country, it is not difficult to define some of the leading geological features which must characterize the lacustrine formation when this basin shall have been gradually converted into dry land by the influx of sediment. The strata would be divisible into two principal groups, the older comprising those deposits which originated on the side adjoining the mountains, where numerous deltas first began to form, and the newer group, consisting of beds deposited in the more central parts of the basin and towards the side farthest from the mountains. The following characters would form the principal marks of distinction between the strata in each series. The more ancient system would be composed, for the most part, of coarser materials, containing many beds of pebbles and sand, often of great thickness, and sometimes dipping at a considerable angle. These, with associated beds of finer ingredients, would, if traced round the borders of the basin, be seen to vary greatly in color and mineral composition, and would also be very irregular in thickness. The beds, on the contrary, in the newer group, would consist of finer particles, and would be horizontal, or very slightly inclined. Their color and mineral composition would be very homogeneous throughout large areas, and would differ from almost all the separate beds in the older series. The following causes would produce the diversity here alluded to between the two great members of such lacustrine formations. When the rivers and torrents first reach the edge of the lake, the detritus washed down by them from the adjoining heights sinks at once into deep water, all the heavier pebbles and sand subsiding near the shore. The finer mud is carried somewhat farther out, but not to the distance of many miles, for the greater part may be seen, as for example, where the Rhone enters the Lake of Geneva, to fall down in clouds to the bottom, not far from the river's mouth. Thus, alluvial tracts are soon formed at the mouths of every torrent and river, and many of these in the course of ages become of considerable extent. Pebbles and sand are then transported farther from the mountains, but in their passage they decrease in size by attrition, and are in part converted into mud and sand. At length, some of the numerous deltas, which are all directed towards a common center, approach near to each other. Those of adjoining torrents become united, and each is merged in its turn in the delta of the largest river, which advances most rapidly into the lake, and renders all the minor streams, one after the other, its tributaries. The various mineral ingredients of all are thus blended together into one homogeneous mixture, and the sediment is poured out from a common channel into the lake. As the average size of the transported particles decreases, while the force and volume of the main river augments, the newer deposits are diffused continually over a wider area, and are consequently more horizontal than the older. When at first there were many independent deltas near the borders of the basin, their separate deposits differed entirely from each other. One may have been charged, like the Arve when it joins the Rhone, with white sand and sediment derived from granite. Another may have been black, like many streams in the Tyrol, flowing from the waste of decomposing rocks of dark slate. A third may have been colored by ochreous sediment, like the Red River in Louisiana. A fourth, like the Elsa in Tuscany, might have held much carbonate of lime in solution. At first they would each form distinct deposits of sand, gravel, limestone, marl, and other materials, but after their junction new chemical combinations and a distinct color would be the result, and the particles having been conveyed 10, 20, or a greater number of miles over alluvial plains would become finer. In those deltas where the tides and strong marine currents interfere, the above description would only be applicable, with certain modifications. If a series of earthquakes accompany the growth of a delta and change the levels of the land from time to time, as in the region where the Indus now enters the sea, the phenomena will depart still more widely from the ordinary type. If, after a protracted period of rest, a delta sinks down, pebbles may be borne along in shallow water near the foot of the boundary hills, so as to form conglomerates overlying the fine mud previously thrown into deeper water in the same area. Causes of stratification in deltas. The stratified arrangement which is observed to prevail so generally in aqueous deposits is most frequently due to variations in the velocity of running water, which cannot sweep along particles of more than a certain size and weight when moving at a given rate. Hence, as the force of the stream augments or decreases, The materials thrown down in successive layers at particular places are rudely sorted according to their dimensions, form, and specific gravity. Where this cause has not operated, as where sand, mud, and fragments of rock are conveyed by glacier, a confused heap of rubbish devoid of all stratification is produced. Natural divisions are only occasioned in deltas by the interval of time which separates annually the deposition of matter during the periodical rains or melting of snow upon the mountains. The deposit of each year may acquire some degree of consistency before that of the succeeding year is superimposed. A variety of circumstances also give rise annually, or sometimes from day to day, to slight variations in color, fineness of the particles, and other characters, by which alternations of strata distinct in texture and mineral ingredients must be produced. Thus, for example, at one period of the year driftwood may be carried down, and at another mud, as was before stated to be the case in the delta of the Mississippi, or at one time, when the volume and velocity of the stream are greatest, pebbles and sand may be spread over a certain area, over which, when the waters are low, fine matter or chemical precipitates are formed. During inundations, the turbid current of fresh water often repels the sea for many miles, but when the river is low, salt water again occupies the same space. When two deltas are converging, the intermediate space is often, for reasons before explained, alternately the receptacle of different sediments derived from the converging streams. The one is, perhaps, charged with calcareous, the other with argillaceous matter, or one sweeps down sand and pebbles, the other impalpable mud. These differences may be repeated with considerable regularity until a thickness of hundreds of feet of alternating beds is accumulated. The multiplication also of shells and corals in particular spots and for limited periods gives rise occasionally to lines of separation and divides a mass which might otherwise be homogeneous into distinct strata. An examination of the shell marl now forming in the Scotch lakes, or the sediment termed warp, which subsides from the muddy water of the Humber and other rivers, shows that recent deposits are often composed of a great number of extremely thin layers, either even or slightly undulating, and preserving a general parallelism to the planes of stratification. Sometimes, however, the laminae in modern strata are disposed diagonally at a considerable angle, which appears to take place where there are conflicting movements in the waters. In January 1829, I visited, in company with Professor L. A. Necker of Geneva, the confluence of the Rhone and Arve, when those rivers were very low, and were cutting channels through the vast heaps of debris thrown down from the waters of the Arve in the preceding spring. One of the sandbanks which had formed in the spring of 1828, where the opposing currents of the two rivers neutralized each other and caused a retardation in the motion, had been undermined, and the following is an exact representation of the arrangement of laminae exposed into a vertical section. The length of the portion here seen is about 12 feet, and the height 5. The strata AA consist of irregular alternations of pebbles and sand in undulating beds. Below these are seams of very fine sand, BB, some as thin as paper, others about the quarter of an inch thick. The strata CC are composed of layers of fine greenish-gray sand as thin as paper. Some of the inclined beds will be seen to be thicker at their upper, others at their lower extremity, the inclination of some being very considerable. These layers must have accumulated one on the other by lateral opposition, probably when one of the rivers was very gradually increasing or diminishing in velocity, so that the point of greatest retardation caused by their conflicting currents shifted slowly, allowing the sediment to be thrown down in successive layers on a sloping bank. The same phenomenon is exhibited in all their strata of all ages. If the bed of a lake or of the sea be sinking, whether at a uniform or an unequal rate, or oscillating in level during the deposition of sediment, these movements will give rise to a different class of phenomena, as for example, to repeated alternations of shallow water and deep water deposits, each with peculiar organic remains, or to frequent repetitions of similar beds, formed at a uniform depth, and enclosing the same organic remains, and to other results too complicated and varied to admit of enumeration here. Formation of conglomerates. Along the base of the maritime Alps, between Toulon and Genoa, the rivers, with few exceptions, are now forming strata of conglomerate and sand. Their channels are often several miles in breadth, some of them being dry, and the rest easily forded for nearly 8 months in the year, whereas during the melting of the snow they are swollen, and a great transportation of mud and pebbles takes place. In order to keep open the main road from France to Italy, now carried along the sea-coast, it is necessary to remove annually great masses of shingle brought down during the flood season. A portion of the pebbles are seen in some localities, as near Nice, to form beds of shingle along the shore, and the greater part are swept into a deep sea. The small progress made by the deltas of minor rivers on this coast need not surprise us, when we recollect that there is sometimes a depth of 2,000 feet at a few hundred yards from the beach, as near Nice. Similar observations might be made respecting a large proportion of the rivers in Sicily, and among others respecting that which, immediately north of the port of Messina, hurries annually vast masses of granitic pebbles into the sea. Constant interchange of land and sea. I may here conclude my remarks on deltas, observing that, imperfect as is our information of the changes which they have undergone within the last 3,000 years, they are sufficient to show how constant an interchange of sea and land is taking place on the face of our globe. In the Mediterranean alone, many flourishing inland towns, and a still greater number of ports, now stand where the sea rolled its waves since the era of the early civilization of Europe. If we could compare with equal accuracy the ancient and actual state of all the islands and continents, we should probably discover that millions of our race are now supported by lands situated where deep seas prevailed in earlier ages. In many districts not yet occupied by man, land animals and forests now abound where ships once sailed, and, on the other hand, we shall find on inquiry that inroads of the ocean have been no less considerable. When to these revolutions produced by aqueous causes we add analogous changes wrought by igneous agency, we shall perhaps acknowledge the justice of the conclusion of Aristotle, who declared that the whole land and sea on our globe periodically changed places. End of chapter 18, part 4.
Section 43 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 19. Destroying and transporting effects of tides and currents. Difference in the rise of tides. Lagunas and Gulf currents. Velocity of currents. Causes of currents. Action of the sea on the British coast. Shetland Islands. Large blocks removed. Isles reduced to clusters of rocks. Orkney Isles. Waste of east coast of Scotland and east coast of England, waste of the cliffs of Holderness, Norfolk, and Suffolk, sand dunes, how far chronometers, silting up of estuaries, Yarmouth Estuary, Suffolk coast, Dunwich, Essex coast, estuary of the Thames, Goodwin Sands, coast of Kent, formation of the Straits of Dover, south coast of England, Sussex, Hants, Dorset, Portland, origin of the Chesil Bank, Cornwall, coast of Brittany. Although the movements of great bodies of water, termed tides and currents, are in general due to very distinct causes, their effects cannot be studied separately, for they produce by their joint action, aided by that of the waves, those changes which are objects of geological interest. These forces may be viewed in the same manner as we before considered rivers, first as employed in destroying portions of the solid crust of the earth and removing them to other places, secondly as reproductive of new strata. Tides. It would be superfluous at the present day to offer any remarks on the cause of the tides. They are not perceptible in lakes or in most inland seas. In the Mediterranean even, deep and extensive as is that sea, they are scarcely sensible to ordinary observation, their effects being quite subordinate to those of the winds and currents. In some places, however, as in the Straits of Messina, there is an ebb and flow to the amount of 2 feet and upwards. At Naples and at the Euripus of 12 or 13 inches, and at Venice, according to Rennell, of 5 feet. In the Syrtis, also, of the ancients, 2 wide shallow gulfs, which penetrate very far within the northern coast of Africa, between Carthage and Cyrene. The rise is said to exceed 5 feet. In islands remote from any continent, the ebb and flow of the ocean is very slight, as at St. Helena, for example, where it is rarely above 3 feet. In any given line of coast, the tides are greatest in narrow channels, bays, and estuaries, and least in the intervening tracts where the land is prominent. Thus, at the entrance of the estuary of the Thames and Medway, the rise of the spring tides is 18 feet. But when we follow our eastern coast from thence northward towards Lowestoft and Yarmouth, we find a gradual diminution, until at the places last mentioned the highest rise is only 7 or 8 feet. From this point there begins again to be an increase, so that at Cormour, where the coast again retires towards the west, the rise is 16 feet, and towards the extremity of the gulf called the Wash, as at Lynn and in Boston Deeps, it is from 22 to 24 feet, and in some extraordinary cases 26 feet. From thence again there is a decrease towards the north, the elevation at the Spurn Point being from 19 to 20 feet, and at Flamborough Head and the Yorkshire coast from 14 to 16 feet. At Milford Haven in Pembrokeshire, at the mouth of the Bristol Channel, the tides rise 36 feet, and at King Road, near Bristol, 42 feet. At Chepstow on the Wye, a small river which opens into the estuary of the Severn, they reach 50 feet, and sometimes 69, and even 72 feet. A current which sets in on the French coast to the west of Cape La Hague comes pent up by Guernsey, Jersey, and other islands, till the rise of the tide is from 20 to 45 feet, which last height it attains at Jersey, and at St. Malo, a seaport of Brittany. The tides in the basin of Mines, at the head of the Bay of Fundy, in Nova Scotia, rise to the height of 70 feet. There are, however, some coasts where the tides seem to offer an exception to the rule above mentioned, For while there is scarcely any rise in the estuary of the Plata in South America, there is an extremely high tide on the open coast of Patagonia, farther to the south. Yet even in this region the tides reach their greatest elevation, about 50 feet, in the Straits of Magellan, and so far at least they conform to the general rule. Currents. The most extensive and best determined system of currents is that which has its source in the Indian Ocean under the influence of the trade winds, and which, after doubling the Cape of Good Hope, inclines to the northward along the western coast of Africa, then across the Atlantic near the equator, where it is called the equatorial current, and is lost in the Caribbean Sea, yet seems to be again revived in the current which issues from the Gulf of Mexico. From thence it flows rapidly through the Straits of Bahama, taking the name of the Gulf Stream, and passing in a northeasterly direction by the banks of Newfoundland towards the Azores. We learn from the posthumous work of Rennell on this subject that the Lagulas current, so called from the cape and bank of that name, is formed by the junction of two streams flowing from the Indian Ocean, the one from the channel of Mozambique down the southeast coast of Africa, the other from the ocean at large. The collective stream is from 90 to 100 miles in breadth, and runs at the rate of from 2½ to more than 4 miles per hour. It is at length turned westward by the Lagulas bank, which rises from a sea of great depth to within 100 fathoms of the surface. It must therefore be inferred, says Rennell, that the current here is more than 100 fathoms deep. Otherwise the main body of it would pass across the bank, instead of being deflected westward, so as to flow round the Cape of Good Hope. From this cape it flows northward, as before stated, along the western coast of Africa, taking the name of the South Atlantic current. It then enters the Bight or Bay of Benin, and is turned westward, partly by the form of the coast there, and partly perhaps by the Guinea current, which runs from the north into the same great bay. From the center of this bay proceeds the equatorial current, already mentioned, holding a westerly direction across the Atlantic, which it traverses from the coast of Guinea to that of Brazil, flowing afterwards by the shores of Guyana to the West Indies. The breadth of this current varies from 160 to 450 geographical miles, and its velocity is from 25 to 79 miles per day, the mean rate being about 30 miles. The length of its whole course is about 4,000 miles. As it skirts the coast of Guyana, it is increased by the influx of the waters of the Amazon and Orinoco, and by their junction acquires accelerated velocity. After passing the island of Trinidad, it expands and is almost lost in the Caribbean Sea. But there appears to be a general movement of that sea towards the Mexican Gulf, which discharges the most powerful of all currents through the Straits of Florida, where the waters run in the northern part with a velocity of 4 or 5 miles an hour, having a breadth of from 35 to 50 miles. The temperature of the Gulf of Mexico is 86 degrees Fahrenheit in the summer, or 6 degrees higher than that of the ocean in the same parallel, 25 degrees north latitude, and a large proportion of this warmth is retained, even where the stream reaches the 43-degree north latitude. After issuing from the Straits of Florida, the current runs in a northerly direction to Cape Hatteras in North Carolina, about 35 degrees north latitude, where it is more than 70 miles broad, and still moves at the rate of 75 miles per day. In about the 40° north latitude, it is turned more towards the Atlantic by the extensive banks of Nantucket and St. George, which are from 200 to 300 feet beneath the surface of the sea. A clear proof that the current exceeds that depth. On arriving near the Azores, the stream widens and overflows, as it were, forming a large expanse of warm water in the center of the North Atlantic, over a space of 200 or 300 miles from north to south, and having a temperature of from 8° to 10° Fahrenheit above the surrounding ocean. The whole area covered by the Gulf water is estimated by Rennell at 2,000 miles in length and at a mean 350 miles in breadth, an area more extensive than that of the Mediterranean. The warm water has been sometimes known to reach the Bay of Biscay, still retaining 5° of temperature above that of the adjoining ocean, and a branch of the Gulf current occasionally drifts fruits, plants, and wood, the produce of America and the West Indies, to the shores of Ireland and the Hebrides. From the above statements we may understand why Rennell has characterized some of the principal currents as oceanic rivers, which he describes as being from 50 to 250 miles in breadth, and having a rapidity exceeding that of the largest navigable rivers of the continents, and so deep as to be sometimes obstructed and occasionally turned aside by banks, the tops of which do not rise within 40, 50, or even 100 fathoms of the surface of the sea. Greatest velocity of currents. The ordinary velocity of the principal currents of the ocean is from 1 to 3 miles per hour, but when the boundary lands converge, large bodies of water are driven gradually into a narrow space, and then, wanting lateral room, are compelled to raise their level. Whenever this occurs, their velocity is much increased. The current which runs through the race of Alderney, between the island of that name and the mainland, has a velocity of about 8 English miles an hour. Captain Hewitt found that in the Pentland Firth, the stream, in ordinary spring tides, runs 10 miles and a half an hour, and about 13 miles during violent storms. The greatest velocity of the tidal current through the chutes, or New Passage, in the Bristol Channel, is 14 English miles an hour, and Captain King observed in his survey of the Straits of Magellan that the tide ran at the same rate through the first narrows and about 8 geographical miles an hour in other parts of those straits. Causes of currents. That movements of no inconsiderable magnitude should be impressed on an expansive ocean by winds blowing for many months in one direction may easily be conceived, when we observe the effects produced in our own seas by the temporary action of the same cause. It is well known that a strong southwest or northwest wind invariably raises the tides to an unusual height along the west coast of England and in the Channel, and that a northwest wind of any continuance causes the Baltic to rise 2 feet and upwards above its ordinary level. Smeaton ascertained by experiment that in a canal 4 miles in length, the water was kept up 4 inches higher at one end than at the other, merely by the action of the wind along the canal. And Rennell informs us that a large piece of water, 10 miles broad, and generally only 3 feet deep, has, by a strong wind, had its waters driven to one side, and sustained so as to become 6 feet deep, while the windward side was laid dry. As water, therefore, he observes, when pent up so that it cannot escape, acquires a higher level, so in a place where it can escape, the same operation produces a current, and this current will extend to a greater or less distance, according to the force by which it is produced. By the side of the principal oceanic currents, such as the Lagulas and the Gulf Stream, are parallel countercurrents running steadily in an opposite direction. Currents flowing alternately in opposite directions are occasioned by the rise and fall of the tides. The effect of this cause is, as before observed, most striking in estuaries and channels between islands. A third cause of oceanic currents is evaporation by solar heat, of which the great current setting through the Straits of Gibraltar into the Mediterranean is a remarkable example, and will be fully considered in the next chapter. A stream of colder water also flows from the Black Sea into the Mediterranean. It must happen in many other parts of the world that large quantities of water raised from one tract of the ocean by solar heat are carried to some other, where the vapor is condensed and falls in the shape of rain, and this, in flowing back again to restore equilibrium, will cause sensible currents. These considerations naturally lead to the inquiry whether the level of those seas out of which currents flow is higher than that of seas into which they flow. If not, the effect must be immediately equalized by undercurrents or countercurrents. Arago is of opinion that, so far as observations have gone, there are no exact proofs of any such difference of level. It was inferred from the measurements of Monsieur Lepere that the level of the Mediterranean near Alexandria was lower by 26 feet 6 inches than the Red Sea near Suez at low water, and about 30 feet lower than the Red Sea at the same place at high water. But Mr. Robert Stevenson affirms, as the result of a more recent survey, that there is no difference of level between the two seas. It was formerly imagined that there was an equal, if not greater, diversity in the relative levels of the Atlantic and Pacific on the opposite sides of the Isthmus of Panama, but the levelings carried across that isthmus by Captain Lloyd in 1828 to ascertain the relative height of the Pacific Ocean at Panama and of the Atlantic at the mouth of the river Chagres have shown that the difference of mean level between those oceans is not considerable, and contrary to expectation, the difference which does exist is in favor of the greater height of the Pacific. According to this survey, the mean height of the Pacific is 3 feet and a half, or 3.52, above the Atlantic. If we assume the mean level of a sea to coincide with the mean between the extremes of the elevation and depression of the tides. For between the extreme levels of the greatest tides in the Pacific at Panama, there is a difference of 27.44 feet, and at the usual spring tides, 21.22 feet, whereas at Chagres this difference is only 1.16 feet, and is the same at all seasons of the year. The tides, in short, in the Caribbean Sea are scarcely perceptible, not equaling those in some parts of the Mediterranean, whereas the rise is very high in the Bay of Panama, so that the Pacific is at high tide lifted up several feet above the surface of the Gulf of Mexico, and then at low water let down as far below it. But astronomers are agreed that, on mathematical principles, the rise of the tidal wave above the mean level of a particular sea must be greater than the fall below it, and although the difference has been hitherto supposed insufficient to cause an appreciable error, it is nevertheless worthy of observation that the error, such as it may be, would tend to reduce the small difference, now inferred from the observations of Mr. Lloyd, to exist between the levels of the two oceans. There is still another way in which heat and cold must occasion great movements in the ocean, a cause to which perhaps currents are principally due. Whenever the temperature of the surface of the sea is lowered, condensation takes place, and the superficial water, having its specific gravity increased, falls to the bottom, upon which lighter water rises immediately and occupies its place. When this circulation of ascending and descending currents has gone on for a certain time in high latitudes, the inferior parts of the sea are made to consist of colder or heavier fluid than the corresponding depths of the ocean between the tropics. If there be a free communication, if no chain of submarine mountains divide the polar from the equatorial basins, a horizontal movement will arise by the flowing of colder water from the poles to the equator, and there will then be a reflux of warmer superficial water from the equator to the poles. A well-known experiment has been adduced to elucidate this mode of action in explanation of the trade winds. If a long trough, divided in the middle by a sluice or partition, have one end filled with water and the other with quicksilver, both fluids will remain quiet so long as they are divided, but when the sluice is drawn up, the heavier fluid will rush along the bottom of the trough, while the lighter, being displaced, will rise, and flowing in an opposite direction, spread itself at the top. In like manner, the expansion and contraction of sea water by heat and cold have a tendency to set undercurrents in motion from the poles to the equator, and to cause countercurrents at the surface, which are impelled in a direction contrary to that of the prevailing trade winds. The geographical and other circumstances being very complicated, we cannot expect to trace separately the movements due to each cause, but must be prepared for many anomalies, especially as the configuration of the bed of the ocean must often modify and interfere with the course of the inferior currents, as much as the position and form of continents and islands alter the direction of those on the surface. Thus, on sounding at great depths in the Mediterranean, Captains Berard and D'Urville have found that the cold does not increase in a high ratio as in the tropical regions of the ocean, the thermometer remaining fixed at about 55 degrees Fahrenheit between the depths of 1,000 and 6,000 feet. This might have been anticipated, as Captain Smith in his survey had shown that the deepest part of the Straits of Gibraltar is only 1,320 feet, so that a submarine barrier exists there which must prevent the influx of any undercurrent of the ocean cooled by polar ice. Each of the four causes above mentioned, the wind, the tides, evaporation, and the expansion and contraction of water by heat and cold, may be conceived to operate independently of the others, and although the influence of all the rest were annihilated. But there is another cause, the rotation of the earth on its axis, which can only come into play when the waters have already been set in motion by some one or all of the forces above described, and when the direction of the current so raised happens to be from south to north or from north to south. The principle on which this cause operates is probably familiar to the reader, as it has long been recognized in the case of the trade winds. Without enlarging, therefore, on the theory, it will be sufficient to offer an example of the mode of action alluded to. When a current flows from the Cape of Good Hope towards the Gulf of Guinea, it consists of a mass of water, which, on doubling the Cape in latitude 35 degrees, has a rotatory velocity of about 800 miles an hour. But when it reaches the line where it turns westward, it has arrived at a parallel where the surface of the earth is whirled round at the rate of 1,000 miles an hour, or about 200 miles faster. If this great mass of water was transferred suddenly from the higher to the lower latitude, the deficiency of its rotatory motion relatively to the land and water with which it would come into juxtaposition would be such as to cause an apparent motion of the most rapid kind, of no less than 200 miles an hour, from east to west. In the case of such a sudden transfer, the eastern coast of America, being carried round in an opposite direction, might strike against a large body of water with tremendous violence, and a considerable part of the continent might be submerged. This disturbance does not occur because the water of the stream, as it advances gradually into new zones of the sea, which are moving more rapidly, acquires by friction an accelerated velocity. Yet as this motion is not imparted instantaneously, the fluid is unable to keep up with the full speed of the new surface over which it is successively brought. Hence, to borrow the language of Herschel, when he speaks of the trade winds, it lags or hangs back in a direction opposite to the earth's rotation, that is, from east to west. And thus a current which would have run simply towards the north, but for the rotation, may acquire a relative direction towards the west. We may next consider a case where the circumstances are the converse of the above. The Gulf Stream, flowing from about latitude 20 degrees, is at first impressed with a velocity of rotation of about 940 miles an hour, and runs to the latitude 40 degrees, where the earth revolves only at the rate of 766 miles, or 174 miles slower. In this case, a relative motion of an opposite kind may result, and the current may retain an excess of rotatory velocity, tending continually to deflect it westward. Polar currents, therefore, or those flowing from high to low latitudes, are driven towards the eastern shores of continents, while tropical currents flowing towards the poles are directed against their western shores. Thus it will be seen that currents depend, like the tides, on no temporary or accidental circumstances, but on the laws which preside over the motions of the heavenly bodies. But although the sum of their influence in altering the surface of the earth may be very constant throughout successive epochs, yet the points where these operations are displayed in fullest energy shift perpetually. The height to which the tides rise, and the violence and velocity of currents, depend in a great measure on the actual configuration of the land, the contour of a long line of continental or insular coast, the depth and breadth of channels, the peculiar form of the bottom of seas, in a word, on a combination of circumstances which are made to vary continually by many igneous and aqueous causes, and amongst the rest by the tides and currents themselves. Although these agents, therefore, of decay and reproduction are local in reference to periods of short duration, such as those which history embraces, they are nevertheless universal, if we extend our views to a sufficient lapse of ages. End of chapter 19, part 1. Section 44 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles LYELL. Chapter 19, Part 2. Destroying and Transporting Power of Currents. After these preliminary remarks on the nature and causes of currents, their velocity and direction, we may next consider their action on the solid materials of the earth. We shall find that their efforts are, in many respects, strictly analogous to those of rivers. I have already treated in the 3rd chapter of the manner in which currents sometimes combine with ice, in carrying mud, pebbles, and large fragments of rock to great distances. Their operations are more concealed from our view than those of rivers, but extend over wider areas, and are therefore of more geological importance. West of the British coasts, Shetland Islands. If we follow the eastern and southern shores of the British Islands from our Ultima Thule in Shetland to the Land's End in Cornwall, we shall find evidence of a series of changes since the historical era, very illustrative of the kind and degree of force exerted by tides and currents cooperating with the waves of the sea. In this survey, we shall have an opportunity of tracing their joint power on islands, promontories, bays, and estuaries, on bold, lofty cliffs, as well as on low shores, and on every description of rock and soil, from granite to blown sand. The northernmost group of the British Islands, the Shetland, are composed of a great variety of rocks, including granite, gneiss, mica slate, serpentine, greenstone, and many others, with some secondary rocks, chiefly sandstone and conglomerate. These islands are exposed continually to the uncontrolled violence of the Atlantic, for no land intervenes between their western shores and America. The prevalence, therefore, of strong westerly gales causes the waves to be sometimes driven with irresistible force upon the coast, while there is also a current setting from the north. The spray of the sea aids the decomposition of the rocks and prepares them to be breached by the mechanical force of the waves. Steep cliffs are hollowed out into deep caves and lofty arches, and almost every promontory ends in a cluster of rocks imitating the forms of columns, pinnacles, and obelisks. Drifting of large masses of rock. Modern observations show that the reduction of continuous tracts to such insular masses is a process in which nature is still actively engaged. The Isle of Stenness, says Dr. Hibbert, presents a scene of unequal desolation. In stormy winters, huge blocks of stone are overturned or are removed from their native beds and hurried up a slight acclivity to a distance almost incredible. In the winter of 1802, a tabular-shaped mass, 8 feet 2 inches by 7 feet and 5 feet 1 inch thick, was dislodged from its bed and removed to a distance of from 80 to 90 feet. I measured the recent bed from which a block had been carried away the preceding winter, A.D. 1818, and found it to be 17 feet and a half by 7 feet, and the depth 2 feet 8 inches. The removed mass had been borne to a distance of 30 feet when it was shivered into 13 or more lesser fragments, some of which were carried still farther, from 30 to 120 feet. A block 9 feet 2 inches by 6 feet and a half, and 4 feet thick, was hurried up the acclivity to a distance of 150 feet. At North Maven, also, angular blocks of stone have been removed in a similar manner to considerable distances by the waves of the sea, some of which are represented in the annexed figure. Effects of lightning. In addition to numerous examples of masses detached and driven by the waves, tides, and currents from their place, some remarkable effects of lightning are recorded in these isles. At Funsey, in Fetlar, about the middle of the last century, a rock of mica schist, 105 feet long, 10 feet broad, and in some places 4 feet thick, was in an instant torn by a flash of lightning from its bed, and broken into 3 large and several smaller fragments. One of these, 26 feet long, 10 feet broad, and 4 feet thick, was simply turned over. The second, which was 28 feet long, 17 broad, and 5 feet in thickness, was hurled across a high point to the distance of 50 yards. Another broken mass, about 40 feet long, was thrown still farther, but in the same direction, quite into the sea. There were also many smaller fragments scattered up and down. When we thus see electricity cooperating with the violent movements of the ocean, in heaping up piles of shattered rock on dry land and beneath the waters, we cannot but admit that a region which shall be the theatre, for myriads of ages, of the action of such disturbing causes, might present at some future period, if upraised far above the bosom of the deep, a scene of havoc and ruin that may compare with any now found by the geologist on the surface of our continents. In some of the Shetland Isles, as on the west of Michael Row, dikes or veins of soft granite have mouldered away, while the matrix in which they were enclosed, being of the same substance but of a firmer texture, has remained unaltered. Thus long narrow ravines, sometimes 20 feet wide, are laid open, and often give access to the waves. After describing some huge cavernous apertures into which the sea flows for 250 feet in Rowness, Dr. Hibbert, writing in 1822, enumerates other ravages of the ocean. A mass of rock, the average dimensions of which may perhaps be rated at 12 or 13 feet square, and 4½ or 5 in thickness, was first moved from its bed, about 50 years ago, to a distance of 30 feet, and has since been twice turned over. Passage forced by the sea through porphyritic rocks. But the most sublime scene is where a mural pile of porphyry, escaping the process of disintegration that is devastating the coast, appears to have been left as a sort of rampart against the inroads of the ocean. The Atlantic, when provoked by wintry gales, batters against it with all the force of real artillery, the waves having, in their repeated assaults, forced themselves an entrance. This breach, named the Grind of the Navire, is widened every winter by the overwhelming surge that, finding a passage through it, separates large stones from its sides, and forces them to a distance of no less than 180 feet. In 2 or 3 spots, the fragments which have been detached are brought together in immense heaps that appear as an accumulation of cubical masses, the product of some quarry. It is evident from this example that although the greater indestructibility of some rocks may enable them to withstand for a longer time the action of the elements, yet they cannot permanently resist. There are localities in Shetland in which rocks of almost every variety of mineral composition are suffering disintegration. Thus the sea makes great inroads on the clay slate of Fitful Head, on the Serpentine, of the Voord Hill in Fettler, and on the mica schist of the Bay of Trieste, on the east coast of the same island, which decomposes into angular blocks. The quartz rock on the east of Walls, and the gneiss and mica schist of Garthness suffer the same fate. Destruction of islands. Such devastation cannot be incessantly committed for thousands of years without dividing islands, until they become at last mere clusters of rocks, the last shreds of masses once continuous. To this state many appear to have been reduced, and innumerable fantastic forms are assumed by rocks adjoining these islands, to which the name of drongs is applied, as it is to those of similar shape in Faroe. The granite rocks between Papa Stour and Hilswick Ness afford an example. A still more singular cluster of rocks is seen to the south of Hilswick Ness, which presents a variety of forms as viewed from different points, and has often been likened to a small fleet of vessels with spread sails. We may imagine that in the course of time Hilswick Ness itself may present a similar wreck from the unequal decomposition of the rocks whereof it is composed, consisting of gneiss and mica schist, traversed in all directions by veins of feldspar porphyry. Midway between the groups of Shetland and Orkney is Fair Island, said to be composed of sandstone with high perpendicular cliffs. The current runs with such velocity that during a calm, and when there is no swell, the rocks on its shores are white with the foam of the sea driven against them. The Orkneys, if carefully examined, would probably illustrate our present topic as much as the Shetland group. The northeast promontory of Sanda, one of these islands, has been cut off in modern times by the sea, so that it became what is now called Start Island, where a lighthouse was erected in 1807, since which time the new strait has grown broader. East coast of Scotland. To pass over to the mainland of Scotland, we find that in Inverness shire there have been inroads of the sea at Fort George and others in Morayshire, which have swept away the old town of Findhorn. On the coast of Kincardineshire, an illustration was afforded at the close of the last century of the effect of promontories in protecting a line of low shore. The village of Mathers, 2 miles south of Johnshaven, was built on an ancient shingle beach, protected by a projecting ledge of limestone rock. This was quarried for lime to such an extent that the sea broke through, and in 1795 carried away the whole village in one night, and penetrated 150 yards inland, where it has maintained its ground ever since, the new village having been built farther inland on the new shore. In the Bay of Montrose we find the North Esk and the South Esk rivers pouring annually into the sea large quantities of sand and pebbles, yet they have formed no deltas, for the waves, aided by the current, setting across their mouths, sweep away all the materials. Considerable beds of shingle, brought down by the North Esk, are seen along the beach. Proceeding southwards, we learn that at Arbroath, in Fortshire, which stands on a rock of red sandstone, gardens and houses have been carried away since the commencement of the present century by encroachments of the sea. It had become necessary before 1828 to remove the lighthouses at the mouth of the estuary of the Tay, in the same county, at Button Ness, which were built on a tract of blown sand, the sea having encroached for 3/4 of a mile. Forces of waves and currents in estuaries. The combined power which waves and currents can exert in estuaries, a term which I confine to bays entered both by rivers and the tides of the sea, was remarkably exhibited during the building of the Bell Rock Lighthouse off the mouth of the Tay. The Bell Rock is a sunken reef consisting of red sandstone, being from 12 to 16 feet under the surface at high water and about 12 miles from the mainland. At the distance of 100 yards, there is a depth in all directions of 2 or 3 fathoms at low water. In 1807, during the erection of the lighthouse, 6 large blocks of granite, which had been landed on the reef, were removed by the force of the sea and thrown over a rising ledge to the distance of 12 or 15 paces, and an anchor weighing about 22 hundredweight was thrown up upon the rock. Mr. Stevenson informs us, moreover, that drift stones measuring upwards of 30 cubic feet, or more than 2 tons weight, have, during storms, been often thrown upon the rock from the deep water. Submarine forests. Among the proofs that the sea has encroached on the land bordering the estuary of the Tay, Dr. Fleming has mentioned a submarine forest which has been traced for several miles along the northern shore of the county of Fife. But subsequent surveys seem to have shown that the bed of peat containing tree roots, leaves, and branches, now occurring at a lower level than the Tay, must have come into its present position by a general sinking of the ground on which the forest grew. The peat bed alluded to is not confined, says Dr. Buist, to the present channel of the Tay, but extends far beyond it, and is covered by stratified clay from 15 to 25 feet in thickness, in the midst of which, in some places, is a bed full of seashells. Recent discoveries having established the fact that upward and downward movements have affected our island since the general coastline had nearly acquired its present shape, we must hesitate before we attribute any given change to a single cause, such as the local encroachment of the sea upon low land. On the coast of Fife, at St. Andrews, a tract of land said to have intervened between the castle of Cardinal Beaton and the sea has been entirely swept away, as were the last remains of the Priory of Crail in the same county in 1803. On both sides of the Frith of Forth, land has been consumed, at North Berwick in particular, and at Newhaven, where an arsenal and dock, built in the reign of James IV in the 15th century, has been overflowed. East coast of England. If we now proceed to the English coast, we find records of numerous lands having been destroyed in Northumberland, as those near Bamborough and Holy Island, and at Tynemouth Castle, which now overhangs the sea, although formerly separated from it by a strip of land. At Hartlepool and several other parts of the coast of Durham, composed of magnesian limestone, the sea has made considerable inroads. Coast of Yorkshire. Almost the whole coast of Yorkshire, from the mouth of the Tees to that of the Humber, is in a state of gradual dilapidation. That part of the cliffs which consist of lias, the oolite series, and chalk, decays slowly. They present abrupt and naked precipices, often 300 feet in height, and it is only at a few points that the grassy covering of the sloping talus marks a temporary relaxation of the erosive action of the sea. The chalk cliffs are worn into caves and needles in the projecting headland of Flamborough, where they are decomposed by the salt spray, and slowly crumble away. But the waste is most rapid between that promontory and Spurn Point, or the coast of Holderness, as it is called, a tract consisting of beds of clay, gravel, sand, and chalk rubble. The irregular intermixture of the argillaceous beds causes many springs to be thrown out, and this facilitates the undermining process, the waves beating against them, and a strong current setting chiefly from the north. The wasteful action is very conspicuous at Dimlington Height, the loftiest point in Holderness, where the beacon stands on a cliff 146 feet above high water, the whole being composed of clay, with pebbles scattered through it. For many years, says Professor Phillips, the rate at which the cliffs recede from Bridlington to Spurn, a distance of 36 miles, has been found by measurement to equal on an average 2 1/4 yards annually, which upon 36 miles of coast would amount to about 30 acres a year. At this rate, the coast, the mean height of which above the sea is about 40 feet, has lost 1 mile in breadth since the Norman conquest, and more than 2 miles since the occupation of York, Eboracum, by the Romans. The extent of this denudation, as estimated by the number of cubic feet of matter removed annually, will be again spoken of in Chapter 22. In the old maps of Yorkshire we find spots, now sandbanks in the sea, marked as the ancient sites of the towns and villages of Auburn, Hartburn, and Hyde. Of Hyde, says Pennant, only the tradition is left, and near the village of Hornsey, a street called Hornsey Beck has long since been swallowed. Althorn and its church have also been in great part destroyed, and the village of Kilsney, but these places are now removed farther inland. The annual rate of encroachment at Althorn for several years preceding 1830 is stated to have averaged about 4 yards. Not unreasonable fears are entertained that at some future time the Spurn Point will become an island, and that the ocean, entering into the estuary of the Humber, will cause great devastation. Pennant, after speaking of the silting up of some ancient ports in that estuary, observes, but in return the sea has made most ample reprisals. The site, and even the very names of several places, once towns of note upon the Humber, are now only recorded in history, and Ravenspur was at one time a rival to Hull, and a port so very considerable in 1332 that Edward Balliol and the confederated English barons sailed from hence to invade Scotland, and Henry IV in 1399 made choice of this port to land at, to effect the deposal of Richard II. Yet the whole of this has long since been devoured by the merciless ocean. Extensive sands, dry at low water, are to be seen in their stead. Pennant describes Spurn Head as a promontory in the form of a sickle, and says the land, for some miles to the north, was perpetually preyed on by the fury of the German Sea, which devours whole acres at a time, and exposes on the shores considerable quantities of beautiful amber. Lincolnshire. The maritime district of Lincolnshire consists chiefly of lands that lie below the level of the sea, being protected by embankments. Some of the fens were embanked and drained by the Romans, but after their departure the sea returned, and large tracts were covered with beds of silt, containing marine shells, now again converted into productive lands. Many dreadful catastrophes are recorded by incursions of the sea, whereby several parishes have been at different times overwhelmed. End of chapter 19, part 2. Section 45 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 19, Part 3. Norfolk. The decay of the cliffs of Norfolk and Suffolk is incessant. At Hunstanton, on the north, the undermining of the lower arenaceous beds at the foot of the cliff causes masses of red and white chalk to be precipitated from above. Between Hunstanton and Weybourne, low hills or dunes of blown sand are formed along the shore from 50 to 60 feet high. They are composed of dry sand bound in a compact mass by the long creeping roots of the plant called marum, Arundo aranea. Such is the present set of the tides that the harbours of clay, wells, and other places are securely defended by these barriers, affording a clear proof that it is not the strength of the material at particular points that determines whether the sea shall be progressive or stationary, but the general contour of the coast. The waves constantly undermine the low chalk cliffs covered with sand and clay between Weybourne and Sheringham, a certain portion of them being annually removed. At the latter town I ascertained in 1829 some facts which throw light on the rate at which the sea gains upon the land. It was computed, when the present inn was built in 1805, that it would require 70 years for the sea to reach the spot, the mean loss of land being calculated from previous observations to be somewhat less than 1 yard annually. The distance between the house and the sea was 50 yards, but no allowance was made for the slope of the ground being from the sea, in consequence of which the waste was naturally accelerated every year as the cliff grew lower, there being at each succeeding period less matter to remove when portions of equal area fell down. Between the years 1824 and 1829, no less than 17 yards were swept away, and only a small garden was then left between the building and the sea. There was in 1829 a depth of 20 feet, sufficient to float a frigate, at one point in the harbour of that port, where only 48 years before there stood a cliff 50 feet high, and houses upon it. If once in half a century an equal amount of change were produced suddenly by the momentary shock of an earthquake, history would be filled with records of such wonderful revolutions of the earth's surface. But if the conversion of high land into deep sea be gradual, it excites only local attention. The flagstaff of the preventive service station on the south side of this harbour was thrice removed inland between the years 1814 and 1829, in consequence of the advance of the sea. Farther to the south we find cliffs composed, like those of Holderness before mentioned, of alternating strata of blue clay, gravel, loam, and fine sand. Although they sometimes exceed 300 feet in height, the havoc made on the coast is most formidable. The whole site of ancient Cromer now forms part of the German Ocean, the inhabitants having gradually retreated inland to their present situation, from whence the sea still threatens to dislodge them. In the winter of 1825, a fallen mass was precipitated from near the lighthouse, which covered 12 acres, extending far into the sea, the cliffs being 250 feet in height. The undermining by springs has sometimes caused large portions of the upper part of the cliffs, with houses still standing upon them, to give way, so that it is impossible, by erecting breakwaters at the base of the cliffs, permanently to ward off the danger. On the same coast, says Mr. R. C. Taylor, the ancient villages of Shipton, Wimpwell, and Eccles have disappeared, several manors and large portions of neighbouring parishes having, piece after piece, been swallowed up, nor has there been any intermission from time immemorial in the ravages of the sea along a line of coast 20 miles in length in which these places stood. Of Eccles, however, a monument still remains in the rained tower of the old church, which is half buried in the dunes of sand within a few paces, 60, of the sea beach. So early as 1605, the inhabitants petitioned James I for a reduction of taxes, as 300 acres of land and all their houses, save 14, had then been destroyed by the sea. Not one half that number of acres now remains in the parish, and hills of blown sand now occupy the site of the houses, which were still extant in 1605. When I visited the spot in 1839, the sea was fast encroaching on the sand hills, and had laid open on the beach the foundations of a house 14 yards square, the upper part of which had evidently been pulled down before it had been buried under sand. The body of the church has also been long buried, but the tower still remains visible. M. E. de Beaumont has suggested that sand dunes in Holland and other countries may serve as natural chronometers, by which the date of the existing continents may be ascertained. The sands, he says, are continually blown inland by the force of the winds, and by observing the rate of their march, we may calculate the period when the movement commenced. But the example just given will satisfy every geologist that we cannot ascertain the starting point of dunes, all coasts being liable to waste, and the shores of the Low Countries in particular being not only exposed to inroads of the sea, but, as Monsieur de Beaumont himself has well shown, having even in historical times undergone a change of level. The dunes may indeed in some cases be made use of as chronometers, to enable us to assign a minimum of antiquity to existing coastlines, but this test must be applied with great caution, so variable is the rate at which the sands may advance into the interior. Hills of blown sand between Eccles and Winterton have barred up and excluded the tide for many hundred years from the mouths of several small estuaries, but there are records of 9 breaches from 20 to 120 yards wide having been made through these, by which immense damage was done to the low grounds in the interior. A few miles south of Happisburgh also are hills of blown sand, which extend to Yarmouth. These dunes afford a temporary protection to the coast, and an inland cliff about a mile long at Winterton shows clearly that at that point the sea must have penetrated formerly farther than at present. Silting up of estuaries. At Yarmouth the sea has not advanced upon the sands in the slightest degree since the reign of Elizabeth. In the time of the Saxons, a great estuary extended as far as Norwich, which city is represented, even in the 13th and 14th centuries, as situated on the banks of an arm of the sea. The sands whereon Yarmouth is built first became firm and habitable ground about the year 1008, from which time a line of dunes has gradually increased in height and breadth, stretching across the whole entrance of the ancient estuary, and obstructing the ingress of the tides so completely that they are only admitted by the narrow passage which the river keeps open, and which has gradually shifted several miles to the south. The ordinary tides at the river's mouth rise, at present, only to the height of 3 or 4 feet, the spring tides to about 8 or 9. By the exclusion of the sea, thousands of acres in the interior have become cultivated lands, and exclusive of smaller pools, upwards of 60 freshwater lakes have been formed, varying in depth from 15 to 30 feet, and in extent from 1 acre to 1,200. The Yare and other rivers frequently communicate with these sheets of water, and thus they are liable to be filled up gradually with lacustrine and fluviatile deposits, and to be converted into land covered with forests. Yet it must not be imagined that the acquisition of new land fit for cultivation in Norfolk and Suffolk indicates any permanent growth of the eastern limits of our island to compensate its reiterated losses. No delta can form on such a shore. Immediately off Yarmouth, and parallel to the shore, is a great range of sandbanks, the shape of which varies slowly from year to year, and often suddenly after great storms. Captain Hewitt, R.N., found in these banks in 1836 a broad channel 65 feet deep, where there was only a depth of 4 feet during a prior survey in 1822. The sea had evacuated to the depth of 60 feet in the course of 14 years, or perhaps a shorter period. The new channel thus formed serves at present, 1838, for the entrance of ships into Yarmouth roads, and the magnitude of this change shows how easily a new set of the waves and currents might endanger the submergence of the land gained within the ancient estuary of the Yare. That great bank should be thrown across the mouths of estuaries on our eastern coast, where there is not a large body of river water to maintain an open channel, is perfectly intelligible when we bear in mind that the marine current sweeping along the coast is charged with the materials of wasting cliffs, and ready to form a bar anywhere the instant its course is interrupted or checked by any opposing stream. The mouth of the Yare has been, within the last 5 centuries, diverted about 4 miles to the south. In like manner, it is evident that at some remote period the river Ald entered the sea at Aldborough, until its ancient outlet was barred up and at length transferred to a point no less than 10 miles distant to the southwest. In this case, ridges of sand and shingle, like those of Lowestoft Ness, which will be described by and by, have been thrown up between the river and the sea, and an ancient sea cliff is to be seen now inland. It may be asked why the rivers on our east coast are always deflected southwards, although the tidal current flows alternately from the south and north. The cause is to be found in the superior force of what is commonly called the flood tide from the north, a tidal wave derived from the Atlantic, a small part of which passes eastward up the English Channel and through the Straits of Dover, and then northwards, while the principal body of water, moving much more rapidly in a more open sea on the western side of Britain, first passes the Orkneys, and then turning, flows down between Norway and Scotland, and sweeps with great velocity along our eastern coast. It is well known that the highest tides on this coast are occasioned by a powerful northwest wind, which raises the eastern part of the Atlantic and causes it to pour a greater volume of water into the German Ocean. This circumstance of a violent offshore wind being attended with a rise of the waters instead of a general retreat of the sea naturally excites the wonder of the inhabitants of our coast. In many districts they look with confidence for a rich harvest of that valuable manure, the seaweed, when the northwesterly gales prevail, and are rarely disappointed. Coast of Suffolk. The cliffs of Suffolk, to which we next proceed, are somewhat less elevated than those of Norfolk, but composed of similar alternations of clay, sand, and gravel. From Gorleston in Suffolk to within a few miles north of Lowestoft, the cliffs are slowly undermined. Near the last mentioned town there is an island cliff about 60 feet high, the sloping talus of which is covered with turf and heath. Between the cliff and the sea is a low flat tract of sand called the Ness, nearly 3 miles long, and for the most part out of reach of the highest tides. The point of the Ness projects from the base of the original cliff to the distance of 660 yards. This accession of land, says Mr. Taylor, has been effected at distinct and distant intervals by the influence of currents running between the land and a shoal about a mile off Lowestoft, called the Holm Sand. The lines of growth in the Ness are indicated by a series of concentric ridges or embankments enclosing limited areas, and several of these ridges have been formed within the observation of persons now living. A rampart of heavy materials is first thrown up to an unusual altitude by some extraordinary tide, attended with a violent gale. Subsequent tides extend the base of this high bank of shingle, and the interstices are then filled with sand blown from the beach. The arundo and other marine plants by degrees obtain a footing, and creeping along the ridge give solidity to the mass, and form in some cases a matted covering of turf. Meanwhile, another mound is forming externally, which by the like process rises and gives protection to the first. If the sea forces its way through one of the external and incomplete mounds, the breach is soon repaired. After a while, the marine plants within the areas enclosed by these embankments are succeeded by a better species of herbage, affording good pasturage, and the sands become sufficiently firm to support buildings. Destruction of Dunwich by the sea. Of the gradual destruction of Dunwich, once the most considerable seaport on this coast, we have many authentic records. Gardner, in his history of that borough, published in 1754, shows by reference to documents beginning with Domesday Book that the cliffs at Dunwich, Southwold, Eastern, and Pakefield have been always subject to wear away. At Dunwich, in particular, 2 tracts of land which had been taxed in the 11th century in the time of King Edward the Confessor are mentioned in the Conqueror's survey, made but a few years afterwards, as having been devoured by the sea. The losses at a subsequent period of a monastery, at another of several churches, afterwards of the old port, then of 400 houses at once, of the church at St. Leonard, the high road, town hall, jail, and many other buildings are mentioned, with the dates when they perished. It is stated that in the 16th century not 1/4 of the town was left standing. Yet the inhabitants retreating inland, the name was preserved, as has been the case with many other ports when their ancient site has been blotted out. There is, however, a church of considerable antiquity still standing, the last of 12 mentioned in some records. In 1740, the laying open of the churchyard of St. Nicholas and St. Francis in the sea cliffs is well described by Gardner, with the coffins and skeletons exposed to view, some lying on the beach, and rocked in cradle of the rude imperious surge. Of these cemeteries no remains can now be seen. Ray also says that ancient writings make mention of a wood 1.5 miles to the east of Dunwich, the site of which must at present be so far within the sea. This city, once so flourishing and populous, is now a small village with about 20 houses and 100 inhabitants. There is an old tradition that the tailors sat in their shops at Dunwich and saw the ships in Yarmouth Bay. But when we consider how far the coast at Lowestoft Ness projects between these places, we cannot give credit to the tale, which nevertheless proves how much the inroads of the sea in times of old had prompted men of lively imagination to indulge their taste for the marvellous. Gardner's description of the cemeteries laid open by the waves reminds us of the scene which has been so well depicted by Bewick, and of which numerous points on the same coast might have suggested the idea. On the verge of a cliff, which the sea has undermined, are represented the unshaken tower and western end of an abbey. The eastern aisle is gone, and the pillars of the cloister are soon to follow. The waves have almost isolated the promontory and invaded the cemetery, where they have made sport with the mortal relics, and thrown up a skull upon the beach. In the foreground is seen a broken tombstone, erected as its legend tells, to perpetuate the memory of one whose name is obliterated, as is that of the county for which he was custos rotulorum. A cormorant is perched on the monument, defiling it, as if to remind some moralizer like Hamlet of the base uses to which things sacred may be turned. Had this excellent artist desired to satirize certain popular theories of geology, he might have inscribed the stone to the memory of some philosopher who taught the permanency of existing continents, the era of repose, the impotence of modern causes. The incursions of the sea at Aldborough were formerly very destructive, and this borough is known to have been once situated a quarter of a mile east of the present shore. The inhabitants continued to build farther inland till they arrived at the extremity of their property, and then the town decayed greatly. But two sandbanks thrown up at a short distance now afford a temporary safeguard to the coast. Between these banks and the present shore, where the current now flows, the sea is 24 feet deep on the spot where the town formerly stood. Essex. Harwich is said to have owed its rise to the destruction of Orwell, a town which stood on the spot now called the West Rocks, and was overwhelmed by an inroad of the sea since the conquest. Apprehensions have been entertained that the isthmus on which Harwich stands may at no remote period become an island, for the sea may be expected to make a breach near Lower Dover Court, where Beacon Cliff is composed of horizontal beds of London clay containing septaria. It had wasted away considerably between the years 1829 and 1838, at both which periods I examined this coast. In that short interval, several gardens and many houses had been swept into the sea, and in April 1838 a whole street was threatened with destruction. The advance of the sea is much accelerated by the traffic carried on in septaria, which are shipped off for cement as fast as they fall down upon the beach. These stones, if allowed to remain in heaps on the shore, would break the force of the waves and retard the conversion of the peninsula into an island, an event which might be followed by the destruction of the town of Harwich. Captain Washington, R.N., ascertained in 1847 that Beacon Cliff, above mentioned, which is about 50 feet high, had given way at the rate of 40 feet in 47 years between 1709 and 1756, 80 feet between 1756 and 1804, and 350 feet between the latter period and 1841, showing a rapidly accelerated rate of destruction. Among other losses, it is recorded that since the year 1807, a field called the Vicar's Field, which belonged to the living of Harwich, has been overwhelmed, and in the year 1820 there was a considerable space between the battery at Harwich, built in the beginning of the present century, and the sea. Part of the fortification had been swept away in 1829, and the rest then overhung the water. At Walton Naze, in the same county, the cliffs, composed of London clay, capped by the shelly sands of the crag, reached the height of about 100 feet, and are annually undermined by the waves. The old churchyard of Walton has been washed away, and the cliffs to the south are constantly disappearing. Kent, Isle of Sheppey. On the coast bounding the estuary of the Thames, there are numerous examples both of the gain and loss of land. The Isle of Sheppey, which is now about 6 miles long by 4 in breadth, is composed of London clay. The cliffs on the north, which are from 60 to 80 feet high, decay rapidly, 50 acres having been lost in 20 years, between 1810 and 1830. The church at Minster, now near the coast, is said to have been in the middle of the island in 1780, and if the present rate of destruction should continue, we might calculate the period, and that not a very remote one, when the whole island will be annihilated. On the coast of the mainland, to the east of Sheppey, is Herne Bay, a place still retaining the name of a bay, although it is no longer appropriate, as the waves and currents have swept away the ancient headlands. There was formerly a small promontory in the line of the shoals, where the present pier is built, by which the larger bay was divided into two, called the Upper and Lower. Still further east stands the church of Reculver, upon a cliff composed of clay and sand, about 25 feet high. Reculver, Regulvium, was an important military station in the time of the Romans, and appears, from Leland's account, to have been, so late as Henry VIII's reign, nearly 1 mile distant from the sea. In the Gentleman's Magazine there is a view of it, taken in 1781, which still represents a considerable space as intervening between the north wall of the churchyard and the cliff. Some time before the year 1780, the waves had reached the site of the ancient Roman camp or fortification, the walls of which had continued for several years after they were undermined to overhang the sea, being firmly cemented into one mass. They were 80 yards nearer the sea than the church, and they are spoken of in the Topographica Britannica in the year 1780 as having recently fallen down. In 1804, part of the churchyard, with some adjoining houses, was washed away, and the ancient church, with its 2 spires, was dismantled and abandoned as a place of worship, but kept in repair as a landmark well known to mariners. I visited the spot in June 1851, and saw human bones and part of a wooden coffin projecting from the cliff near the top. The whole building would probably have been swept away long ere this, had not the force of the waves been checked by an artificial causeway of stones and large wooden piles driven into the sands on the beach to break the force of the waves. End of chapter 19, part 3. Section 46 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 19, Part 4. Isle of Thanet. The Isle of Thanet was, in the time of the Romans, separated from the rest of Kent by a navigable channel through which the Roman fleets sailed on their way to and from London. Bede describes this small estuary as being, in the beginning of the 8th century, 3 furlongs in breadth, and it is supposed that it began to grow shallow about the period of the Norman conquest. It was so far silted up in the year 1485 that an act was then obtained to build a bridge across it, and it has since become marshland with small streams running through it. On the coast, Bedlam Farm, belonging to the hospital of that name, lost 8 acres in the 20 years preceding 1830, the land being composed of chalk from 40 to 50 feet above the level of the sea. It has been computed that the average waste of the cliff between the North Foreland and the Reculvers, a distance of about 11 miles, is not less than 2 feet per annum. The chalk cliffs on the south of Thanet, between Ramsgate and Pegwell Bay, have on an average lost 3 feet per annum for the last 10 years, preceding 1830. Goodwin Sands. The Goodwin Sands lie opposite this part of the Kentish coast. They are about 10 miles in length, and are in some parts 3, and in others 7 miles distant from the shore, and for a certain space are laid bare at low water. That they are a remnant of land, and not a mere accumulation of sea sand, as Rennell imagined, may be presumed from the fact that, when the erection of a lighthouse on this shoal was in contemplation by the Trinity Board in the year 1817, it was found by borings that the bank consisted of 15 feet of sand resting on blue clay, and by subsequent borings the subjacent chalk has been reached. An obscure tradition has come down to us that the estates of Earl Goodwin, the father of Harold, who died in the year 1053, were situated here, and some have conjectured that they were overwhelmed by the flood mentioned in the Saxon Chronicle, sub anno 1099. The last remains of an island consisting, like Sheppey, of clay, may perhaps have been carried away about that time. There are other records of waste in the county of Kent, as at Deal and at Dover, where Shakespeare's cliff, composed entirely of chalk, has suffered greatly, and continually diminishes in height, the slope of the hill being towards the land. There was an immense landslip from this cliff in 1810, by which Dover was shaken as if by an earthquake, and a still greater one in 1772. We may suppose, therefore, that the view from the top of the precipice in the year 1600, when the tragedy of King Lear was written, was more fearful and dizzy than it is now. The best antiquarian authorities are agreed that Dover harbour was formerly an estuary, the sea flowing up a valley between the chalk hills. The remains found in different excavations confirm the description of the spot given by Caesar and Antoninus, and there is clear historical evidence to prove that at an early period there was no shingle at all at Dover. Straits of Dover. In proceeding from the northern parts of the German Ocean towards the Straits of Dover, the water becomes gradually more shallow, so that, in the distance of about 200 leagues, we pass from a depth of 120 to that of 58, 38, 18, and even less than 2 fathoms. The shallowest part follows a line drawn between Romney Marsh and Boulogne. From this point, the English Channel again deepens progressively as we proceed westward, so that the Straits of Dover may be said to part 2 seas. Whether England was formerly united with France has often been a favourite subject of speculation. So early as 1605, our countryman Verstegan, in his Antiquities of the English Nation, observed that many preceding writers had maintained this opinion, but without supporting it by any weighty reasons. He accordingly endeavours himself to confirm it by various arguments, the principal of which are, first, the proximity and identity of the composition of the opposite cliffs and shores of Albion and Gallia, which, whether flat and sandy or steep and chalky, correspond exactly with each other. Secondly, the occurrence of a submarine ridge called Our Lady's Sand, extending from shore to shore at no great depth, and which, from its composition, appears to be the original basis of the isthmus. Thirdly, the identity of the noxious animals in France and England, which could neither have swum across nor have been introduced by man. Thus no one, he says, would have imported wolves. Therefore these wicked beasts did of themselves pass over. He supposes the ancient isthmus to have been about 6 English miles in breadth, composed entirely of chalk and flint, and in some places of no great height above the sea level. The operation of the waves and tides, he says, would have been more powerful when the straits were narrower, and even now they are destroying cliffs composed of similar materials. He suggests the possible cooperation of earthquakes, and when we consider how many submarine forests skirt the southern and eastern shores of England, and that there are raised beaches at many points above the sea level, containing fossil shells of recent species, it seems reasonable to suppose that such upward now in progress in Sweden and Greenland may have greatly assisted the denuding force of the ocean stream. Folkestone. At Folkestone the sea undermines the chalk and subjacent strata. About the year 1716 there was a remarkable sinking of a tract of land near the sea, so that houses became visible from certain points at sea, and from particular spots on the sea cliffs, from whence they could not be seen previously. In the description of this subsidence in the Phil Tran 1716, it is said that the land consisted of a solid stony mass, chalk, resting on wet clay, galt, so that it slid forwards towards the sea, just as a ship is launched on tallowed planks. It is also stated that within the memory of persons then living, the cliff there had been washed away to the extent of 10 rods. Encroachments of the sea at Hythe are also on record, but between this point and Rye there has been a gain of land within the times of history. The rich level tract called Romney Marsh, or Dungeness, about 10 miles in width and 5 in breadth, and formed of silt, having received great accession. It has been necessary, however, to protect it from the sea, from the earliest periods, by embankments, the towns of Lydd and Romney being the only parts of the marsh above the level of the highest tides. Mr. Redman has cited numerous old charts and trustworthy authorities to prove that the average annual increase of the promontory of shingle called Dungeness amounted for 2 centuries, previous to 1844, to nearly 6 yards. Its progress, however, has fluctuated during that period, for between 1689 and 1794, a term of 105 years, the rate was as much as 8 1/4 yards per annum. It is ascertained that the shingle is derived from the westward. Whether the pebbles are stopped by the meeting of the tide from the north, flowing through the Straits of Dover, with that which comes up the channel from the west, as was formerly held, or by the check given to the tidal current by the waters of the Rother, as some maintain, is still a disputed question. Rye, situated to the south of Romney Marsh, was once destroyed by the sea, but it is now 2 miles distant from it. The neighbouring town of Winchelsea was destroyed in the reign of Edward I. The mouth of the Rother stopped up, and the river diverted into another channel. In its old bed, an ancient vessel, apparently a Dutch merchantman, was found about the year 1824. It was built entirely of oak and much blackened. Large quantities of hazelnuts, peat, and wood are found in digging in Romney Marsh. South coast of England. Westward of Hastings or of St. Leonard's, the shoreline has been giving way as far as Pevensey Bay, where formerly there existed a haven now entirely blocked up by shingle. The degradation has equalled for a series of years 7 feet per annum in some places, and several Martello towers had in consequence, before 1851, been removed by the ordnance. At the promontory of Beachy Head, a mass of chalk 300 feet in length and from 70 to 80 in breadth fell in the year 1813 with a tremendous crash, and similar slips have since been frequent. About a mile to the west of the town of Newhaven, the remains of an ancient entrenchment are seen on the brow of Castle Hill. This earthwork, supposed to be Roman, was evidently once of considerable extent and of an oval form, but the greater part has been cut away by the sea. The cliffs which are undermined here are high, more than 100 feet of chalk being covered by tertiary clay and sand, from 60 to 70 feet in thickness. In a few centuries, the last vestiges of the plastic clay formation on the southern borders of the chalk of the South Downs on this coast will probably be annihilated, and future geologists will learn, from historical documents, the ancient geographical boundaries of this group of strata in that direction. On the opposite side of the estuary of the Ouse, on the east of New Haven harbour, a bed of shingle composed of chalk flints derived from the waste of the adjoining cliffs had accumulated at Seaford for several centuries. In the great storm of November 1824, this bank was entirely swept away and the town of Seaford inundated. Another great beach of shingle is now forming from fresh materials. The whole coast of Sussex has been incessantly encroached upon by the sea from time immemorial, and although sudden inundations only, which overwhelmed fertile or inhabited tracts, are noticed in history, the records attest an extraordinary amount of loss. During a period of no more than 80 years, there are notices of about 20 inroads in which tracts of land of from 20 to 400 acres in extent were overwhelmed at once, the value of the tithes being mentioned in the Taxatio Ecclesiastica. In the reign of Elizabeth, the town of Brighton was situated on that tract where the chain pier now extends into the sea. In the year 1665, 22 tenements had been destroyed under the cliff. At that period there still remained under the cliff 113 tenements, the whole of which were overwhelmed in 1703 and 1705. No traces of the ancient town are now perceptible, yet there is evidence that the sea has merely resumed its ancient position at the base of the cliffs, the site of the whole town having been merely a beach abandoned by the ocean for ages. Hampshire, Isle of Wight. It would be endless to allude to all the localities on the Sussex and Hampshire coasts where the land has given way, but I may point out the relation which the geological structure of the Isle of Wight bears to its present shape, as attesting that the coast owes its outline to the continued action of the sea. Through the middle of the island runs a high ridge of chalk strata in a vertical position and in a direction east and west. This chalk forms the projecting promontory of Culver Cliff on the east and of the Needles on the west, while Sandown Bay on the one side and Compton Bay on the other have been hollowed out of the softer sands and argillaceous strata, which are inferior in geological position to the chalk. The same phenomena are repeated in the Isle of Purbeck, where the line of vertical chalk forms the projecting promontory of Handfast Point, and Swanage Bay marks the deep excavation made by the waves in the softer strata, corresponding to those of Sandown Bay. Hurst Castle Bank, progressive motion of sea beaches. Although the loose pebbles and grains of sand composing any given line of sea beach are carried sometimes one way, sometimes another, they have, nevertheless, an ultimate motion in one particular direction. Their progress, for example, on the south coast of England is from west to east, which is owing partly to the action of the waves driven eastwards by the prevailing wind, and partly to the current or the motion of the general body of water caused by the tides and winds. The force of the waves gives motion to pebbles which the velocity of the currents alone would be unable to carry forwards. But as the pebbles are finally reduced to sand or mud by continual attrition, they are brought within the influence of a current, and this cause must determine the course which the main body of matter derived from wasting cliffs will eventually take. It appears from the observations of Mr. Palmer and others that if a pier or groin be erected anywhere on our southern or southeastern coast to stop the progress of the beach, a heap of shingle soon collects on the western side of such artificial barriers. The pebbles continue to accumulate till they rise as high as the pier or groin, after which they pour over in great numbers during heavy gales. The western entrance of the channel, called the Solent, is crossed for more than 2/3 of its width by the shingle bank of Hurst Castle, which is about 2 miles long, 70 yards broad, and 12 feet high, presenting an inclined plane to the west. This singular bar consists of a bed of rounded chalk flints, resting on a submarine argillaceous base. The flints and a few other pebbles intermixed are derived from the waste of Hordwell and other cliffs to the westward, where tertiary strata, capped with a covering of broken chalk flints from 5 to 50 feet thick, are rapidly undermined. In the great storm of November 1824, this bank of shingle was moved bodily forwards for 40 yards towards the northeast, and certain piles, which served to mark the boundaries of 2 manors, were found after the storm on the opposite side of the bar. At the same time, many acres of pasture land were covered by shingle on the farm of Westover, near Lymington. But the bar was soon restored in its old position by pebbles drifted from the west, and it appears from ancient maps that it has preserved the same general outline and position for centuries. Mr. Austin remarks that, as a general rule, it is only when high tides concur with a gale of wind that the sea reaches the base of cliffs so as to undermine them and throw down earth and stone. But the waves are perpetually employed in abrading and fashioning the materials already strewed over the beach. Much of the gravel and shingle is always travelling up and down between high water mark and a slight depth below the level of the lowest tides, and occasionally the materials are swept away and carried into deeper water. Owing to these movements, every portion of our southern coast may be seen at one time or other in the condition of bare rock. yet other beds of sand and shingle soon collect, and although composed of new materials, invariably exhibit on the same spots precisely similar characters. The cliffs between Hurst Shingle Bar and Christchurch are undermined continually, the sea having often encroached for a series of years at the rate of a yard annually. Within the memory of persons now living, it has been necessary thrice to remove the coast road farther inland. The tradition, therefore, is probably true that the church of Hordwell was once in the middle of that parish, although now, 1830, very near the sea. The promontory of Christchurch Head gives way slowly. It is the only point between Lymington and Poole Harbour in Dorsetshire where any hard stony masses occur in the cliffs. 5 layers of large ferruginous concretions, somewhat like the septaria of the London clay, have occasioned a resistance at this point, to which we may ascribe this headland. In the meantime, the waves have cut deeply into the soft sands and loam of Poole Bay, and after severe frosts, great landslips take place, which by degrees become enlarged into narrow ravines, or chines, as they are called, with vertical sides. One of these chines, near Boscombe, has been deepened 20 feet within a few years. At the head of each there is a spring, the waters of which have been chiefly instrumental in producing these narrow excavations, which are sometimes from 100 to 150 feet deep. Isle of Portland. The peninsulas of Purbeck and Portland are continually wasting away. In the latter, the soft argillaceous substratum, Kimmeridge clay, hastens the dilapidation of the superincumbent mass of limestone. In 1655, the cliffs adjoining the principal quarries in Portland gave way to the extent of 100 yards and fell into the sea, and in December 1734, a slide to the extent of 150 yards occurred on the east side of the isle, by which several skeletons buried between slabs of stone were discovered. But a much more memorable occurrence of this nature in 1792, occasioned probably by the undermining of the cliffs, is thus described in Hutchins' History of Dorsetshire. Early in the morning the road was observed to crack. This continued increasing, and before 2 o'clock the ground had sunk several feet, and was in one continued motion, but attended with no other noise than what was occasioned by the separation of the roots and brambles, and now and then of falling rock. At night it seemed to stop a little, but soon moved again, and before morning the ground from the top of the cliff to the water side had sunk in some places 50 feet perpendicular. The extent of ground that moved was about 1.25 miles from north to south, and 600 yards from east to west. Formation of the Chesil Bank. Portland is connected with the mainland by the Chesil Bank, a ridge of shingle about 17 miles in length, and in most places nearly 1/4 mile in breadth. The pebbles forming this immense barrier are chiefly siliceous, all loosely thrown together, and rising to the height of from 20 to 30 feet above the ordinary high water mark, and at the southeastern end, which is nearest the Isle of Portland, where the pebbles are largest, 40 feet. The fundamental rocks whereon the shingle rests are found at the depth of a few yards only below the level of the sea. The formation of that part of the bar which attaches Portland to the mainland may have been due to an original shoal or reef, or to the set of the tides in the narrow channel, by which the course of the pebbles, which are always coming from the west, has been arrested. It is a singular fact that, throughout the Chesil Bank, The pebbles increase gradually in size as we proceed southeastward, or as we go farther from the quarter which supplied them. Had the case been reversed, we should naturally have attributed the circumstance to the constant wearing down of the pebbles by friction, as they are rolled along a beach 17 miles in length. But the true explanation of the phenomenon is doubtless this: the tidal current runs strongest from west to east, and its power is greater in the more open channel or farther from the land. In other words, its force increases southwards, and as the direction of the bank is from northwest to southeast, the size of the masses coming from the westward and thrown ashore must always be largest where the motion of the water is most violent. Colonel Reed states that all calcareous stones rolled along from the west are soon ground into sand, and in this form they pass round Portland Island. The storm of 1824 burst over the Chesil bank with great fury, and the village of Chesilton, built upon its southern extremity, was overwhelmed, with many of the inhabitants. The same storm carried away part of the breakwater at Plymouth, and huge masses of rock, from 2 to 5 tons in weight, were lifted from the bottom of the weather side and rolled fairly to the top of the pile. One block of limestone, weighing 7 tons, was washed round the western extremity of the breakwater and carried 150 feet. The propelling power is derived in these cases from the breaking of the waves, which run fastest in shallow water, and for a short space far exceed the most rapid currents in swiftness. It was in the same month, and also during a spring tide, that a great flood is mentioned on the coasts of England in the year 1099. Florence of Worcester says, on the 3rd day of the Nones of November 1099, the sea came out upon the shore, and buried towns and men very many, and oxen and sheep innumerable. We also read in the Saxon Chronicle for the year 1099, this year eke on St. Martin's Mass Day, the 11th of November, sprung up so much of the sea flood, and so mickle harm did, as no man minded that it ever afore did. And there was the ilk day a new moon. South of the Bill, or southern point of Portland, is a remarkable shoal in the channel at the depth of 7 fathoms, called the Shambles, consisting entirely of rolled and broken shells of Purpura, Lapillus, Mytilus, Edulis, and other species now living. This mass of light materials is always in motion, varying in height from day to day, and yet the shoals remains constant. End of chapter 19, section 4. Section 47 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 19, Part 5. Dorsetshire, Devonshire. At Lyme Regis in Dorsetshire, the church cliffs, as they are called, consisting of lias about 100 feet in height, gradually fell away at the rate of 1 yard a year from 1800 to 1829. An extraordinary landslip occurred on the 24th of December, 1839, on the coast between Lyme Regis and Axmouth, which has been described by the Reverend W.D. Conybeare, to whose kindness I am indebted for the accompanying section. The tract of downs ranging there along the coast is capped by chalk, which rests on sandstone, alternating with chert, beneath which is more than 100 feet of loose sand, with concretions at the bottom, and belonging to the green sand formation. the whole of the above masses reposing on retentive beds of clay belonging to the lias, which shelves towards the sea. Numerous springs issuing from the loosed sand have gradually removed portions of it, and thus undermined the superstratum, so as to have caused subsidences at former times, and to have produced a line of undercliff. In 1839, an excessively wet season had saturated all the rocks with moisture, so as to increase the weight of the incumbent mass, from which the support had already been withdrawn by the action of springs. Thus the superstrata were precipitated into hollows prepared for them, and the adjacent masses of partially undermined rock, to which the movement was communicated, were made to slide down on a slippery basis of watery sand towards the sea. These causes gave rise to a convulsion, which began on the morning of the 24th of December with a crashing noise, and on the evening of the same day fissures were seen opening in the ground, and the walls of tenements rending and sinking, until a deep chasm or ravine was formed, extending nearly 3/4 of a mile in length, with a depth of from 100 to 150 feet, and a breadth exceeding 240 feet. At the bottom of this deep gulf lie fragments of the original surface, thrown together in the wildest confusion. In consequence of lateral movements, the tract intervening between the new fissure and the sea, including the ancient undercliff, was fractured, and the whole line of sea cliff carried bodily forwards for many yards. A remarkable pyramidal crag off Culverhole Point, which lately formed a distinguishing landmark, has sunk from a height of about 70 to 20 feet, and the main cliff, before more than 50 feet distant from this insulated crag, is now brought almost close to it. This motion of the sea cliff has produced a farther effect, which may rank among the most striking phenomena of this catastrophe. The lateral pressure of the descending rocks has urged the neighbouring strata, extending beneath the shingle of the shore, by their state of unnatural condensation, to burst upwards in a line parallel to the coast. Thus an elevated ridge, more than a mile in length, and rising more than 40 feet, covered by a confused assemblage of broken strata and immense blocks of rock, invested with seaweed and corallines, and scattered over with shells and starfish and other productions of the deep, forms an extended reef in front of the present range of cliffs. A full account of this remarkable landslip, with a plan, sections, and many fine illustrative drawings, was published by Messrs. Conybeare and Buckland. Cornwall. Near Penzance in Cornwall there is a projecting tongue of land called the Green, formed of granitic sand, from which more than 30 acres of pasture land have been gradually swept away in the course of the last 2 or 3 centuries. It is also said that St. Michael's Mount, now an insular rock, was formerly situated in a wood several miles from the sea, and its old Cornish name, Caraclaus, in Cowes, signifies, according to Carew, the hoar rock in the wood. Between the mount and Newlyn there is seen under the sand black vegetable mould full of hazelnuts, and the branches, leaves, roots, and trunks of forest trees, all of indigenous species. This stratum has been traced seaward as far as the ebb permits, and many proofs of a submerged vegetable accumulation, with stumps of trees in the position in which they grew, have been traced, says Sir Henry de la Beche, round the shores of Devon, Cornwall, and western Somerset. The facts not only indicate a change in the relative level of the sea and land, since the species of animals and plants were the same as those now living in this district, But what is very remarkable, there seems evidence of the submergence having been effected, in part at least, since the country was inhabited by man. A submarine forest occurring at the mouth of the Parrett in Somersetshire, on the south side of the Bristol Channel, was described by Mr. L. Horner in 1815, and its position attributed to subsidence. A bed of peat is there seen below the level of the sea, and the trunks of large trees, such as the oak and yew, having their roots still diverging as they grew, and fixed in blue clay. Tradition of loss of land in Cornwall. The oldest historians mention a tradition in Cornwall of the submersion of the Lyoness, a country said to have stretched from the Land's End to the Scilly Islands. The tract, if it existed, must have been 30 miles in length, and perhaps 10 in breadth. The land now remaining on either side is from 200 to 300 feet high, the intervening sea about 300 feet deep. Although there is no authentic evidence for this romantic tale, it probably originated in some former inroads of the Atlantic, accompanying, perhaps, a subsidence of land on this coast. West coast of England. Having now brought together an ample body of proofs of the destructive operations of the waves, tides, and currents on our eastern and southern shores, it will be unnecessary to enter into details of changes on the western coast, for they present merely a repetition of the same phenomena, and in general on an inferior scale. On the borders of the estuary of the Severn, the flats of Somersetshire and Gloucestershire have received enormous accessions, while on the other hand, the coast of Cheshire, between the rivers Mersey and Dee, has lost, since the year 1764, many hundred yards, and some affirm more than half a mile, by the advance of the sea upon the abrupt cliffs of red clay and marls. Within the period above mentioned, several lighthouses have been successively abandoned. There are traditions in Pembrokeshire and Cardiganshire of far greater losses of territory than that which the Lyoness tale of Cornwall pretends to commemorate. They are all important, as demonstrating that the earliest inhabitants were familiar with the phenomenon of incursions of the sea. Loss of land on the coast of France. The French coast, particularly that of Brittany, where the tides rise to an extraordinary height, is the constant prey of the waves. In the 9th century, many villages and woods are reported to have been carried away, the coast undergoing great change, whereby the hill of St. Michael was detached from the mainland. The parish of Bourneuf and several others in that neighbourhood were overflowed in the year 1500. In 1735, during a great storm, the ruins of Palnell were seen uncovered in the sea. End of chapter 19, part 5.
Chapter 20 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Chapter 20. Action of Tides and Currents. Continued. Inroads of the sea at the mouths of the Rhine in Holland. Changes in the arms of the Rhine. Proofs of subsidence of land. Estuary of the Biesbosso formed in 1421. Zuiderzee in the 13th century. Islands destroyed. Delta of the Eames converted into a bay. Estuary of the Dollard formed. Encroachment of the sea on the coast of Schleswig, on shores of North America. Tidal wave called the Boar. Influence of tides and currents on the mean level of seas. Action of currents in inland lakes and seas. Baltic, Cimbrian deluge, Straits of Gibraltar, no undercurrent there. Whether salt is precipitated in the Mediterranean, waste of shores of Mediterranean. Inroads of the sea at the mouths of the Rhine. The line of British coast, considered in the preceding chapter, offered no example of the conflict of two great antagonistic forces. The influx, on the one hand, of a river draining a large continent, and on the other, the action of the waves, tides, and currents of the ocean. But when we pass over by the Straits of Dover to the continent and proceed northeastwards, we find an admirable illustration of such a contest, where the ocean and the Rhine are opposed to each other, each disputing the ground now occupied by Holland, the one striving to shape out an estuary, the other to form a delta. There was evidently a period when the river obtained the ascendancy, when the shape and perhaps the relative level of the coast and set of the tides were very different. But for the last 2,000 years, during which man has witnessed and actively participated in the struggle, the result has been in favor of the ocean, the area of the whole territory having become more and more circumscribed, natural and artificial barriers having given way, one after the other, and many 100,000 human beings having perished in the waves. Changes in the arms of the Rhine. The Rhine, after flowing from the Grisson Alps, copiously charged with sediment, first purifies itself in the Lake of Constance, where a large delta is formed. Then, swelled by the Aar and numerous other tributaries, it flows for more than 600 miles towards the north, when, entering a low tract, it divides into two arms about 10 miles northeast of Cleves, a point which must therefore be considered the head of its delta. In speaking of the delta, I do not mean to assume that all that part of Holland which is comprised within the several arms of the Rhine can be called a delta in the strictest sense of the term, because some portion of the country thus circumscribed, as for example a part of Gelderland and Utrecht, consists of strata which may have been deposited in the sea before the Rhine existed. These older tracts may either have been raised like the Ulla Bund and Kutsch, during the period when the sediment of the Rhine was converting a part of the sea into land, or they may have constituted islands previously. The dark tint between Antwerp and Newport represents part of the Netherlands which was land in the time of the Romans, then overflowed by the sea before and during the 5th century, and afterwards reconverted into land. When the river divides north of Cleves, the left arm takes the name of the Waal, and the right, retaining that of the Rhine, is connected a little further to the north by an artificial canal with the river Yssel. The Rhine, then flowing westward, divides again southeast of Utrecht, and from this point it takes the name of the Lek, a name which was given to distinguish it from the northern arm, called the Old Rhine, which was sanded up until the year 1825, when a channel was cut for it, by which it now enters the sea at Katwijk. It is common in all great deltas that the principal channels of discharge should shift from time to time, but in Holland so many magnificent canals have been constructed and have so diverted from time to time the course of the waters, that the geographical changes in this delta are endless, and their history, since the Roman era, forms a complicated topic of antiquarian research. The present head of the delta is about 40 geographical miles from the nearest part of the gulf called the Zuider Zee, and more than twice that distance from the general coastline. The present head of the delta of the Nile is about 80 or 90 geographical miles from the sea, that of the Ganges, as before stated, 220, and that of the Mississippi about 180, reckoning from the point where the Atchafalaya branches off, to the extremity of the new tongue of land in the Gulf of Mexico. But the comparative distance between the heads of deltas and the sea affords no positive data for estimating the relative magnitude of the alluvial tracts formed by their respective rivers, for the ramifications depend on many varying and temporary circumstances, and the area over which they extend does not hold any constant proportion to the volume of water in the river. The Rhine, therefore, has at present 3 mouths. About 2/3 of its waters flow to the sea by the Waal, and the remainder is carried partly to the Zuider Zee by the Yssel, and partly to the ocean by the Lek. As the whole coast to the south, as far as Ostend, and on the north to the entrance of the Baltic, has, with few exceptions, from time immemorial yielded to the force of the waves, it is evident that the common delta of the Rhine, Meuse, and Scheldt, for these 3 rivers may all be considered as discharging their waters into the same part of the sea, would, if its advance had not been checked, have become extremely prominent, and even if it had remained stationary, would long ere this have projected far beyond the rounded outline of the coast, like that strip of land already described at the mouth of the Mississippi. But we find, on the contrary, that the islands which skirt the coast have not only lessened in size, but in number also, while great bays have been formed in the interior by incursions of the sea. In order to explain the incessant advance of the ocean on the shores and inland country of Holland, Monsieur Elie de Beaumont has suggested that there is in all probability been a general depression or sinking of the land below its former level over a wide area. Such a change of level would enable the sea to break through the ancient line of sandbanks and islands which protected the coast, would lead to the enlargement of bays, the formation of new estuaries, and ultimately to the entire submergence of land. These views appear to be supported by the fact that several peat mosses of freshwater origin now occur under the level of the sea, especially on the site of the Zuider Zee and Lake Flavo, presently to be mentioned. Several excavations also made for wells at Utrecht, Amsterdam, and Rotterdam have proved that below the level of the ocean the soil near the coast consists of alternations of sand with marine shells and beds of peat and clay, which have been traced to the depth of 50 feet and upwards. I have said that the coast to the south as far as Ostend has given way. This statement may at first seem opposed to the fact that the tract between Antwerp and Newport, shaded black in the annexed map of Figure 38, although now dry land and supporting a large population, has within the historical period been covered with the sea. This region, however, consisted, in the time of the Romans, of woods, marshes, and peat mosses, protected from the ocean by a chain of sandy dunes, which were afterwards broken through during storms, especially in the 5th century. The waters of the sea during these eruptions threw down upon the barren peat a horizontal bed of fertile clay, which is in some places 3 yards thick, full of recent shells and works of art. The inhabitants, by the aid of embankments and the sand dunes of the coast, have succeeded, although not without frequent disasters, in defending the soil thus raised by the marine deposit. Inroads of the sea in Holland. If we pass to the northward of the territory just alluded to, and cross the Scheldt, we find that between the 14th and 18th centuries parts of the islands of Walcheren and Beveland were swept away, and several populous districts of Cadsand, losses which far more than counterbalance the gain of land caused by the sanding up of some pre-existing creeks. In 1658, the island Orisont was annihilated. One of the most memorable inroads of the sea occurred in 1421, when the tide, pouring into the mouth of the united Meuse and Waal, burst through a dam in the district between Dort and Gertrudenberg, and overflowed 72 villages, forming a large sheet of water called the Bies Bosch. See map, figure 38. 35 of the villages were irretrievably lost, and no vestige, even of their ruins, was afterwards seen. The rest were redeemed, and the site of the others, though still very generally represented on maps as an estuary, has in fact been gradually filled up by alluvial deposits, and had become in 1835, as I was informed by Professor Moll, an immense plain, yielding abundant crops of hay, though still uninhabited. To the north of the Meuse is a long line of shore, covered with sand dunes, where great encroachments have taken place from time to time, in consequence chiefly of the prevalence of southeasterly winds, which blow down the sands toward the sea. The church of Scheveningen, not far from The Hague, was once in the middle of the village, and now stands on the shore, half the place having been overwhelmed by the waves in 1570. Catwick, once far from the sea, is now upon the shore, 2 of its streets having been overflowed, and land torn away to the extent of 200 yards in 1719. It is only by the aid of embankments that Peyton and several other places further north have been defended against the sea. Formation of the Zuider Zee and Straits of Staveren. Still more important are the changes which have taken place on the coast, opposite the right arm of the Rhine or the Yssel, where the ocean has burst through a large isthmus and entered the inland Lake Flavo, which in ancient times was, according to Pomponius Mela, formed by the overflowing of the Rhine over certain lowlands. It appears that in the time of Tacitus there were several lakes on the present site of the Zuider Zee, between Friesland and Holland. The successive inroads by which these and a great part of the adjoining territory were transformed into a great gulf began about the commencement, and were completed toward the close of the 13th century. Alting gives the following relation of the occurrence, drawn from manuscript documents of contemporary inhabitants of the neighboring provinces. In the year 1205, the island now called Wieringen, to the south of the Texel, was still a part of the mainland, but during several high floods, of which the dates are given, ending in December 1251, it was separated from the continent. By subsequent incursions, the sea consumed great parts of the rich and populous isthmus, a low tract which stretched on the north of Lake Flavo, between Staveren in Friesland and Medemblik in Holland, till at length a breach was completed about the year 1282 and afterwards widened. Great destruction of land took place when the sea first broke in, and many towns were swept away. But there was afterwards a reaction to a certain extent, large tracts, at first submerged, having been gradually redeemed. The new straits south of Staveren are more than half the width of those of Dover, but are very shallow, the greatest depth not exceeding 2 or 3 fathoms. The new bay is of a somewhat circular form, and between 30 and 40 miles in diameter. How much of this space may formerly have been occupied by Lake Flavo is unknown. Destruction of islands. A series of islands stretching from the Texel to the mouths of the Weser and Elbe are probably the last relics of a tract once continuous. They have greatly diminished in size, and have lost about a third of their number since the time of Pliny, for that naturalist counted 23 islands between Texel and Eider, whereas now there are only 16, including Heligoland and Newark. The island of Heligoland, at the mouth of the Elbe, consists of a rock of red marl of the Kuiper formation of the Germans, and is bounded by perpendicular red cliffs about 200 feet high. Although according to some accounts it has been greatly reduced in size since the year 800, Mr. Wiebel assures us that the ancient map by Meyer cannot be depended upon, and that the island, according to the description still extant by Adam of Bremen, was not much larger than now in the time of Charlemagne. On comparing the map made in the year 1793 by the Danish engineer Vassel, the average encroachment of the sea on the cliffs between that period and the year 1848, or about half a century, did not amount to more than 3 feet. On the other hand, some few islands have extended their bounds in one direction or became connected with others by the sanding up of channels. But even these, like Juist, have generally given way as much on the north towards the sea as they have gained on the south or land side. The Dollard formed. While the delta of the Rhine has suffered so materially from the movements of the ocean, it can hardly be supposed that minor rivers on the same coast should have been permitted to extend their deltas. It appears that in the time of the Romans there was an alluvial plain of great fertility, where the Ems entered the sea by 3 arms. This low country stretched between Groningen and Friesland, and sent out a peninsula to the northeast towards Emden. A flood in 1277 first destroyed part of the peninsula. Other inundations followed at different periods throughout the 15th century. In 1507, a part only of Torum, a considerable town, remained standing, and in spite of the erection of dams, the remainder of that place, together with market towns, villages, and monasteries, to the number of 50, were finally overwhelmed. The new gulf, which was called the Dollard, although small in comparison to the Zuider Zee, occupied no less than 6 square miles at first, but part of this space was in the course of the 2 following centuries again redeemed from the sea. The small bay of Lebucht, farther north, was formed in a similar manner in the 13th century, and the bay of Harlbucht in the middle of the 16th. Both of these have since been partially reconverted into dry land. Another new estuary called the Gulf of Jade, near the mouth of the Weser, scarcely inferior in size to the Dollard, has been gradually hollowed out since the year 1016, between which era and 1651 a space of about 4 square miles has been added to the sea. The rivulet which now enters this inlet is very small, but Ahrens conjectures that an arm of the Weser had once an outlet in that direction. Coast of Schleswig. Farther north, we find so many records of waste on the western coast of Schleswig as to lead us to anticipate that at no distant period in the history of the physical geography of Europe, Jutland may become an island, and the ocean may obtain a more direct entrance into the Baltic. Indeed, the temporary insulation of the northern extremity of Jutland has been effected no less than 4 times within the records of history, the ocean having as often made a breach through the bar of sand which usually excludes it from the Lim Fjord. This long frith is 120 miles in length, including its wingdings, and communicates at its eastern end with the Baltic. The last eruption of salt water happened in 1824, and the fjord was still open in 1837, when some vessels of 30 tons burden passed through. The marsh islands between the rivers Elbe and Eider are mere banks, like the lands formed of the Warp and the Humber, protected by dikes. Some of them, after having been inhabited with security for more than 10 centuries, have been suddenly overwhelmed. In this manner, in 1216, no less than 10,000 of the inhabitants of Eiderstede and Dithmarsh perished, and on the 11th of October, 1634, the islands and the whole coast, as far as Jutland, suffered by a dreadful deluge. Destruction of North Strand by the sea. North Strand, up to the year 1240, was, with the islands of Sylt and Fur, so nearly connected with the mainland as to appear a peninsula, and was called North Friesland, a highly cultivated and populous district. It measured from 9 to 11 geographical miles from north to south, and 6 to 8 from east to west. In the above-mentioned year, it was torn asunder from the continent, and in part overwhelmed. The Isle of North Strand, thus formed, was towards the end of the 16th century only 4 geographical miles in circumference, and was still celebrated for its cultivation and numerous population. After many losses, it still contained 9,000 inhabitants. At last, in the year 1634, on the evening of the 11th of October, a flood passed over the whole island, whereby 1,300 houses, with many churches, were lost. 50,000 head of cattle perished, and above 6,000 men. 3 small islets, one of them still called North Strand, alone remained, which are now continually wasting. The redundancy of river water in the Baltic, especially during the melting of ice and snow in spring, causes in general an outward current through the channel called the Kattegat. But after a continuance of northwesterly gales, especially during the height of the spring tides, the Atlantic rises, and, pouring a flood of water into the Baltic, commits dreadful devastations on the isles of the Danish archipelago. This current even acts, though with diminished force, as far eastward as the vicinity of Danzig. Accounts written during the last 10 centuries attest the wearing down of promontories on the Danish coast, the deepening of gulfs, the severing of peninsulas from the mainland, and the waste of islands, while in several cases marshland, defended for centuries by dikes, has at last been overflowed and thousands of the inhabitants whelmed in the waves. Thus the island Barsow on the coast of Schleswig has lost year after year an acre at a time, and the island Alsen suffers in like manner. Cimbrian deluge. As we have already seen that during the flood before mentioned, 6,000 men and 50,000 head of cattle perished on North Strand on the western coast of Jutland, we are all well prepared to find that this peninsula, Cimbrica Chersonisus of the ancients, has from a remote period been the theater of like catastrophes. Accordingly, Strabo records a story, although he treats it as an incredible fiction, that during a high tide the ocean rose upon this coast so rapidly that men on horseback were scarcely able to escape. Florus, alluding to the same tradition, says, Cimbri tutani atque tigerini, ab extremis Galilae profugi, cum terras iurum inundasit oceanus, novis sedes toto orbe querebant. This event, commonly called the Cimbrian deluge, is supposed to have happened about 3 centuries before the Christian era, but it is not improbable that the principal catastrophe was preceded and followed by many devastations, like those experienced in modern times on the islands and shores of Jutland, and such calamities may well be conceived to have forced on the migration of some maritime tribes. Inroads of the sea on the eastern shores of North America. After so many authentic details respecting the destruction of the coast in parts of Europe best known, it will be unnecessary to multiply examples of 332 analogous changes in more distant regions of the world. It must not, however, be imagined that our own seas form any exception to the general rule. Thus, for example, if we pass over to the eastern coast of North America, where the tides rise in the Bay of Fundy to great elevation, we find many facts attesting the incessant demolition of land. Cliffs, often several hundred feet high, composed of sandstone, red marl, and other rocks, which border that bay and its numerous estuaries, are perpetually undermined. The ruins of these cliffs are gradually carried in the form of mud, sand, and large boulders into the Atlantic by powerful currents, aided at certain seasons by drift ice, which form along the coast and freezes round large stones. At Cape May, on the north side of Delaware Bay in the United States, the encroachment of the sea was shown by observations made consecutively for 16 years from 1804 to 1820, to average about 9 feet a year. And at Sullivan's Island, which lies on the north side of the entrance of the harbor of Charleston in South Carolina, the sea carried away 1/4 of a mile of land in 3 years, ending in 1786. Tidal wave called the Bore. Before concluding my remarks on the actions of the tides, I must not omit to mention the wave called the Bore, which is sometimes produced in a river where a large body of water is made to rise suddenly, in consequence of the contraction of the channel. This wave terminates abruptly on the inland side, because the quantity of water contained in it is so great, and its motion so rapid, that time is not allowed for the surface of the river to be immediately raised by means of transmitted pressure. A tide wave thus rendered abrupt has a close analogy, observes Mr. Whewell, to the waves which curl over and break on a shelving shore. The bore which enters the Severn, where the phenomenon is of almost daily occurrence, is sometimes 9 feet high, and at spring tides rushes up the estuary with extraordinary rapidity. The finest example which I have seen of this wave was at Nova Scotia, where the tide is said to rise in some places 70 feet perpendicular, and to be the highest in the world. In the large estuary of the Shubenacadie, which connects with another estuary called the Basin of Mines, itself an embranchment of the Bay of Fundy, a vast body of water comes rushing up with a roaring noise into a long, narrow channel, and while it is ascending has all the appearance of pouring down a slope as steep as that of the celebrated rapids of the St. Lawrence. In picturesque effect, however, it bears no comparison, for instead of the transparent green water and snow-white foam of the St. Lawrence, the whole current of the Shubenacadie is turbid and densely charged with red mud. The same phenomenon is frequently witnessed in the principal branches of the Ganges, and in the Meghna, as before mentioned on page 279. In the Hooghly, says Rennell, the bore commences at Hooghly Point, the place where the river first contracts itself, and is perceptible above Hooghly town, and so quick is its motion that it hardly employs 4 hours in traveling from one to the other, though the distance is nearly 70 miles. At Calcutta it sometimes occasions an instantaneous rise of 5 feet, and both here and in every other part of its track the boats, on its approach, immediately quit to shore, and make for safety to the middle of the river. In the channels between the islands and the mouth of the Meghna, the height of the bore is said to exceed 12 feet, and is so terrific in its appearance and dangerous in its consequences that no boat will venture to pass at spring tide. These waves may sometimes cause inundations, undermine cliffs, and still more frequently sweep away trees and land animals from low shores. so that they may be carried down and ultimately embedded in fluviatile or submarine deposits. In such large bodies of water as the North American lakes, the continuance of a strong wind in one direction often causes the elevation of the water, and its accumulation on the leeward side. And while the equilibrium is restoring itself, powerful currents are occasioned. In October 1833, a strong current in Lake Erie, caused partly by the set of the waters towards the outlet of the lake and partly by the prevailing wind, burst a passage through the extensive peninsula called Long Point, and soon excavated a channel more than 9 feet deep and 900 feet wide. Its width and depth have since increased, and a new and costly pier has been erected, for it is hoped that this event will permanently improve the navigation of Lake Erie for steamboats. On the opposite or southern coast of this lake, in front of the town of Cleveland, the degradation of the cliffs have been so rapid for several years preceding a survey made in 1837 as to threaten many towns with demolition. In the Black Sea also, although free from tides, we learn from Pallas that there is a sufficiently strong current to undermine the cliffs in many parts, and particularly in the Crimea. Straits of Gibraltar. It is well known that a powerful current sets constantly from the Atlantic into the Mediterranean, and its influence extends along the whole southern borders of that sea, and even to the shores of Asia Minor. Captain Smith found during his survey that the central current ran constantly at the rate of from 3 to 6 miles an hour eastward into the Mediterranean, the body of water being 3 miles and a half wide. But there are also 2 lateral currents, one on the European and one on the African side, each of them about 2 miles and a half broad, and flowing at about the same rate as the central stream. These lateral currents ebb and flow with the tide, setting alternately into the Mediterranean and into the Atlantic. The excess of water constantly flowing in is very great, and there is only one cause to which this can be attributed: the loss of water in the Mediterranean by evaporation. That the level of this sea should be considerably depressed by this cause is quite conceivable, since we know that the winds blowing from the shores of Africa are hot and dry, and hygrometrical experiments recently made in Malta and other places show that the mean quantity of moisture in the air investing the Mediterranean is equal only to 1/2 of that in the atmosphere of England. The temperature also of the great inland sea is upon an average higher by 3½ degrees of Fahrenheit than the eastern part of the Atlantic Ocean in the same latitude, which must greatly promote its evaporation. The Black Sea being situated in a higher latitude, and being the receptacle of rivers flowing from the north, is much colder, and its expenditure far less. Accordingly, it does not draw any supply from the Mediterranean, but, on the contrary, contributes to it by a current flowing outwards, for the most part of the year, through the Dardanelles. The discharge, however, at the Bosphorus is so small, when compared to the volume of water carried in by rivers, as to imply a great amount of evaporation in the Black Sea. Whether salt be precipitated in the Mediterranean. It is, however, objected that evaporation carries away only fresh water, and that the current from the Atlantic is continually bringing in salt water. Why, then, do not the component parts of the waters of the Mediterranean vary? Or how can they remain so nearly the same as those of the ocean? Some have imagined that the excess of salt might be carried away by an undercurrent running in a contrary direction to the superior, and this hypothesis appeared to receive confirmation from a late discovery that the water taken up about 50 miles within the straits from a depth of 670 fathoms contained a quantity of salt 4 times greater than the water on the surface. Dr. Wollaston, who analyzed this water obtained by Captain Smith, truly inferred that an undercurrent of such denser water flowing outward, if of equal breadth and depth with the current near the surface, would carry out as much salt below as is brought in above, although it moved with less than 1/4 part of the velocity, and would thus prevent a perpetual increase of saltiness in the Mediterranean beyond that existing in the Atlantic. It was also remarked by others that the result would be the same if the swiftness being equal, the inferior current had only 1/4 of the volume of the superior. At the same time, there appeared reason to conclude that this great specific gravity was only acquired by water at immense depths, for 2 specimens of the water taken within the Mediterranean at the distance of some 100 miles from the straits and at depths of 400 and even 450 fathoms were found by Dr. Wollaston not to exceed in density that of many ordinary samples of seawater. Such being the case, we can now prove that the vast amount of salt brought into the Mediterranean does not pass out again by the straits, for it appears by Captain Smith's soundings, which Dr. Wollaston had not seen, that between the Capes of Trafalgar and Spartel, which are 22 miles apart, and where the straits are shallowest, the deepest part, which is on the side of Cape Spartel, is only 220 fathoms. It is therefore evident that if water sinks in certain parts of the Mediterranean, in consequence of the increase of its specific gravity to greater depths than 220 fathoms, it can never flow out again into the Atlantic, since it must be stopped by the submarine barrier which crosses the shallowest part of the Straits of Gibraltar. The idea of the existence of a countercurrent at a certain depth first originated in the following circumstances. Monsieur de Viègle, commander of a privateer called the Phoenix of Marseilles, gave chase to a Dutch merchant ship near Quetta Point, and coming up with her in the middle of the gut between Tarifa and Tangier, gave her one broadside, which directly sunk her. A few days after, the sunken ship with her cargo of brandy and oil was cast ashore near Tangier, which is at least 4 leagues to the westward of the place where she went down, and to which she must have floated in a direction contrary to the course of the central current. This fact, however, affords no evidence of an undercurrent, because the ship, when it approached the coast, would necessarily be within the influence of a lateral current, which, running westward twice every 24 hours, might have brought back the vessel to Tangier. What then becomes of the excess of salt? For this is an inquiry of the highest geological interest. The Rhone, the Po, the Nile, and many hundred minor streams and springs pour annually into the Mediterranean large quantities of carbonate of lime, together with iron, magnesia, silica, alumina, sulfur, and other mineral ingredients in a state of chemical solution. To explain why the influx of this matter does not alter the composition of the sea has never been regarded as a difficulty, for it is known that calcareous rocks are forming in the delta of the Rhone, in the Adriatic, on the coast of Asia Minor, and in other localities. Precipitation is acknowledged to be the means whereby the surplus mineral matter is disposed of, after the consumption of a certain portion in the secretions of testacea, zoophytes, and other marine animals. But before muriate of soda can in like manner be precipitated, the whole Mediterranean ought, according to the received principles of chemistry, to become as much saturated with salt as Lake Aral, the Dead Sea, or the brine springs of Cheshire. It is undoubtedly true, in regard to small bodies of water, that every particle must be fully saturated with muriate of soda before a single crystal of salt can be formed. Such is probably the case in all natural salterns. Such, for example, as those described by travelers as occurring on the western borders of the Black Sea, where extensive marshes are said to be covered by thin films of salt, after a rapid evaporation of seawater. The salt étangs of the Rhone, where salt has sometimes been precipitated in considerable abundance, have been already mentioned. In regard to the depth of the Mediterranean, it appears that between Gibraltar and Ceuta, Captain Smith sounded to the enormous depth of 950 fathoms, and found there a gravelly bottom, with fragments of broken shells. Saussure sounded to the depth of 2,000 feet, within a few yards of the shore at Nice, and M. Birard has lately fathomed to the depth of more than 6,000 feet in several places without reaching the bottom. The central abysses, therefore, of this sea are in all likelihood at least as deep as the Alps are high, and as at the depth of 700 fathoms only, water has been found to contain a proportion of salt 4 times greater than that at the surface, we may presume that the excess of salt may be much greater at the depth of 2 or 3 miles. After evaporation, the surface becomes impregnated with a slight excess of salt, and its specific gravity being thus increased, it instantly falls to the bottom, while lighter water rises to the top, or flows in laterally, being always supplied by rivers and the current from the Atlantic. The heavier fluid, when it arrives at the bottom, cannot stop, if it can gain access to any lower part of the bed of the sea not previously occupied by water of the same density. How far this accumulation of brine can extend before the inferior strata of water will part with any of their salt, and what difference in such a chemical process the immense pressure of the incumbent ocean, or the escape of heated vapors, thermal springs, or submarine volcanic eruptions might occasion, are questions which cannot be answered in the present state of science. The Straits of Gibraltar are said to become gradually wider by the wearing down of the cliffs on each side at many points, and the current sets along the coast of Africa, so as to cause considerable inroads in various parts, particularly near Carthage. Near the canopic mouth of the Nile at Aboukir, the coast was greatly devastated in the year 1784, when a small island was nearly consumed. By a series of similar operations, the old site of the cities of Necropolis, Taposiris, Parva, and Canopus have become a sandbank. End of chapter 22.
Section 49 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles LYELL. Chapter 21. Reproductive Effects of Tides and Currents. Estuaries, how formed. Silting up of estuaries does not compensate the loss of land on the borders of the ocean. Bed of the German Ocean. Composition and extent of its sandbanks. Strata deposited by currents in the English Channel. On the shores of the Mediterranean. At the mouths of the Amazon, Orinoco, and Mississippi. Wide area over which strata may be formed by this cause. From the facts enumerated in the last chapter, it appears that on the borders of the ocean, currents and tides, cooperating with the waves of the sea are most powerful instruments in the destruction and transportation of rocks, and as numerous tributaries discharge their alluvial burden into the channel of one great river, so we find that many rivers deliver their earthly contents to one marine current, to be borne by it to a distance, and deposited in some deep receptacle of the ocean. The current, besides receiving this tribute of sedimentary matter from streams draining the land, acts also itself on the coast, as does a river on the cliffs which bound a valley. Yet the waste of cliffs by marine currents constitutes, on the whole, a very insignificant portion of the denudation annually effected by aqueous causes, as I shall point out in the sequel of this chapter. In inland seas where the tides are insensible, or on those parts of the borders of the ocean where they are feeble, it is scarcely possible to prevent a harbour at a river's mouth from silting up, for a bar of sand or mud is formed at points where the velocity of the turbid river is checked by the sea, or where the river and a marine current neutralize each other's force. For the current, as we have seen, may, like the river, hold in suspension a large quantity of sediment, or cooperating with the waves may cause the progressive motion of a shingle beach in one direction. I have already alluded to the erection of piers and groins at certain places on our southern coast to arrest the course of the shingle and sand. The immediate effect of these temporary obstacles is to cause a great accumulation of pebbles on one side of the barrier, after which the beach still moves on round the end of the pier at a greater distance from the land. This system, however, is often attended with a serious evil, for during storms the waves throw suddenly into the harbour the vast heap of pebbles which have collected for years behind the groin or pier, as happened during a great gale, January 1839, at Dover. The formation and keeping open of large estuaries are due to the combined influence of tidal currents and rivers, for when the tide rises, a large body of water suddenly enters the mouth of the river, where, becoming confined within narrower bounds, while its momentum is not destroyed, it is urged on, and having to pass through a contracted channel, rises and runs with increased velocity, just as a stream, when it reaches the arch of a bridge scarcely large enough to give passage to its waters, rushes with a steep fall through the arch. During the ascent of the tide, a body of fresh water, flowing down in an opposite direction from the higher country, is arrested in its course for several hours, and thus a large lake of fresh and brackish water is accumulated, which, when the sea ebbs, is let loose, as on the removal of an artificial sluice or dam. By the force of this retiring water, the alluvial sediment both of the river and of the sea is swept away and transported to such a distance from the mouth of the estuary that a small part only can return with the next tide. It sometimes happens that during a violent storm a large bar of sand is suddenly made to shift its position, so as to prevent the free influx of the tides or efflux of river water. Thus, about the year 1500, the sands at Bayonne were suddenly thrown across the mouth of the Adour. That river, flowing back upon itself, soon forced a passage to the northward along the sandy plain of Cap Breton, till at last it reached the sea at Boucau, at the distance of 7 leagues from the point where it had formerly entered. It was not till the year 1579 that the celebrated architect Louis Defoe undertook, at the desire of Henry III, to reopen the ancient channel, which he at last effected with great difficulty. In the estuary of the Thames at London and in the Gironde, the tide rises only for 5 hours and ebbs 7, and in all estuaries the water requires a longer time to run down than up, so that the preponderating force is always in the direction which tends to keep open a deep and broad passage. But for reasons already explained, there is naturally a tendency in all estuaries to silt up partially, since eddies and backwaters and points where opposing streams meet are very numerous and constantly change their position. Many writers have declared that the gain on our eastern coast since the earliest periods of history has more than counterbalanced the loss, but they have been at no pains to calculate the amount of loss, and have often forgotten that, while the new acquisitions are manifest, there are rarely any natural monuments to attest the former existence of the land that has been carried away. They have also taken into their account those tracts artificially recovered, which are often of great agricultural importance, and may remain secure, perhaps, for thousands of years, but which are only a few feet above the mean level of the sea, and are therefore exposed to be overflowed again by a small proportion of the force required to move cliffs of considerable height on our shores. If it were true that the area of land annually abandoned by the sea in estuaries were equal to that invaded by it, there would still be no compensation in kind. The tidal current which flows out from the northwest and bears against the eastern coast of England transports, as we have seen, materials of various kinds. Aided by the waves, it undermines and sweeps away the granite, gneiss, trap rocks, and sandstone of Shetland, and removes the gravel and loam of the cliffs of Holderness, Norfolk, and Suffolk, which are between 20 and 300 feet in height, and which waste at various rates of from 1 foot to 6 yards annually. It also bears away, in cooperation with the Thames and the tides, the strata of London clay on the coast of Essex and Sheppey. The sea at the same time consumes the chalk with its flints for many miles continuously on the shores of Kent and Sussex, commits annual ravages on the freshwater beds, capped by a thick covering of chalk flint gravel in Hampshire, and continually saps the foundations of the Portland limestone. It receives, besides, during the rainy months, large supplies of pebbles, sand, and mud, which numerous streams from the Grampians, Cheviots, and other chains send down to the sea. To what regions, then, is all this matter consigned? It is not retained in mechanical suspension by the waters of the ocean, nor does it mix with them in a state of chemical solution. It is deposited somewhere, yet certainly not in the immediate neighbourhood of our shores, for in that case there would soon be a cessation of the encroachment of the sea, and large tracts of low land, like Romney Marsh, would almost everywhere encircle our island. As there is now a depth of water exceeding 30 feet in some spots where towns like Dunwich flourished but a few centuries ago, it is clear that the current not only carries far away the materials of the wasted cliffs, but is capable also of excavating the bed of the sea to a certain moderate depth. So great is the quantity of matter held in suspension by the tidal current on our shores, that the waters are in some places artificially introduced into certain lands below the level of the sea, and by repeating this operation, which is called warping, for 2 or 3 years, considerable tracts have been raised in the estuary of the Humber to the height of about 6 feet. If a current charged with such materials meets with deep depressions in the bed of the ocean, it must often fill them up, just as a river, when it meets with a lake in its course, fills it gradually with sediment. I have said that the action of the waves and currents on sea cliffs, or their power to remove matter from above to below the sea level, is insignificant in comparison with the power of rivers to perform the same task. As an illustration, we may take the coast of Holderness, described in the last chapter. It is composed, as we have seen, of very destructible materials, is 36 miles long, and its average height may be taken at 40 feet. As it has wasted away at the rate of 2 1/4 yards annually for a long period, it will be found on calculation that the quantity of matter thrown down into the sea every year and removed by the current amounts to 51,321,600 cubic feet. It has been shown that the united Ganges and Brahmaputra carry down to the Bay of Bengal 40 billion of cubic feet of solid matter every year, so that their transporting power is no less than 780 times greater than that of the sea on the coast above mentioned, and in order to produce a result equal to that of the 2 Indian rivers, we must have a line of wasting coast like that of Holderness, nearly 28,000 miles in length, or longer than the entire circumference of the globe by above 3,000 miles. The reason of so great a difference in the results may be understood when we reflect that the operations of the ocean are limited to a single line of cliff surrounding a large area, whereas great rivers with their tributaries and the mountain torrents which flow into them act simultaneously on a length of bank almost indefinite. Nevertheless, we are by no means entitled to infer that the denuding force of the great ocean is a geological cause of small efficacy, or inferior to that of rivers. Its chief influence is exerted at moderate depths below the surface, on all those areas which are slowly rising, or are attempting, as it were, to rise above the sea. From data hitherto obtained respecting subterranean movements, we can scarcely speculate on an average rate of upheaval of more than 2 or 3 feet in a century. An elevation to this amount is taking place in Scandinavia, and probably in many submarine areas as vast as those which we know to be sinking, from the proofs derived from circular lagoon islands or coral atolls. Suppose strata as indestructible as those of the Wealden, or the Lower and Upper Cretaceous Formation, or the tertiary deposits of the British Isles to be thus slowly upheaved. How readily might they all be swept away by waves and currents in an open sea! How entirely might each stratum disappear as it was brought up successively and exposed to the breakers! Shoals of wide extent might be produced, but it is difficult to conceive how any continent could ever be formed under such circumstances, were it not indeed for the hardness and toughness of the crystalline and volcanic rocks, which are often capable of resisting the action of the waves. Few lands might ever emerge from the midst of an open sea. Supposed filling up of the German Ocean. The German Ocean is deepest on the Norwegian side, where the soundings give 190 fathoms, but the mean depth of the whole basin may be stated at no more than 31 fathoms. The bed of this sea is traversed by several enormous banks, the greatest of which is the Dogger Bank, extending for upwards of 354 miles from north to south. The whole superficies of these shoals is equal to about 1/3 of the whole extent of England and Scotland. The average height of the banks measures, according to Mr. Stevenson, about 78 feet, the upper portion of them consisting of fine and coarse siliceous sand, mixed with comminuted corals and shells. It had been supposed that these vast submarine hills were made up bodily of loose materials supplied from the waste of the English, Dutch, and other coasts, but the survey of the North Sea, conducted by Captain Hewitt, affords ground for suspecting this opinion to be erroneous. If such immense mounds of sand and mud had been accumulated under the influence of currents, the same causes ought nearly to have reduced to one level the entire bottom of the German Ocean, instead of which some long narrow ravines are found to intersect the banks. One of these varies from 17 to 44 fathoms in depth, and has very precipitous sides. In one part, called the Inner Silver Pits, it is 55 fathoms deep. The shallowest parts of the Dogger Bank were found to be 42 feet under water, except in one place where the wreck of a ship had caused a shoal. Such uniformity in the minimum depth of water seems to imply that the currents, which vary in their velocity from a mile to 2 miles and a half per hour, have power to prevent the accumulation of drift matter in places of less depth. Strata deposited by currents. It appears extraordinary that in some tracts of the sea adjoining the coast of England, where we know that currents are not only sweeping along rocky masses, thrown down from time to time from the high cliffs, but also occasionally scooping out channels in the regular strata, there should exist fragile shells and tender zoophytes in abundance, which live uninjured by these violent movements. The ocean, however, is in this respect a counterpart of the land, and as on the continents rivers may undermine their banks, uproot trees, and roll along sand and gravel, while their waters are inhabited by testacea and fish, and their alluvial plains are adorned with rich vegetation and forests, so the sea may be traversed by rapid currents, and its bed may here and there suffer great local derangement, without any interruption of the general order and tranquillity. It has been ascertained by soundings in all parts of the world that where new deposits are taking place in the sea, coarse sand and small pebbles commonly occur near the shore, while further from land and in deeper water, finer sand and broken shells are spread out over the bottom. Still farther out, the finest mud and ooze are alone met with. Mr. Austen observes that this rule holds good in every part of the English Channel examined by him. He also informs us that where the tidal current runs rapidly in what are called races, where surface undulations are perceived in the calmest weather, over deep banks, the discoloration of the water does not arise from the power of such a current to disturb the bottom at a depth of 40 or 80 fathoms, as some have supposed. In these cases, a column of water, sometimes 500 feet in height, is moving onwards with the tide clear and transparent above, while the lower portion holds fine sediment in suspension, a fact ascertained by soundings, when suddenly it impinges upon a bank, and its height is reduced to 300 feet. It is thus made to boil up and flow off at the surface, a process which forces up the lower strata of water charged with fine particles of mud, which in their passage from the coast had gradually sunk to a depth of 300 feet or more. One important character in the formations produced by currents is the immense extent over which they may be the means of diffusing homogeneous mixtures, for these are often coextensive with a great line of coast, and by comparison with their deposits, the deltas of rivers must shrink into significance. In the Mediterranean, the same current which is rapidly destroying many parts of the African coast between the Straits of Gibraltar and the Nile checks also the growth of the delta of the Nile, and drifts the sediment of that great river to the eastward. To this source may be attributed the rapid accretions of land on parts of the Syrian shores where rivers do not enter. Among the greatest deposits now in progress, and of which the distribution is chiefly determined by currents, we may class those between the mouths of the Amazon and the southern coast of North America. Captain Sabine found that the equatorial current before mentioned was running with the rapidity of 4 miles an hour where it crosses the stream of the Amazon, which river preserves part of its original impulse, and has its waters not wholly mingled with those of the ocean at the distance of 300 miles from its mouth. The sediment of the Amazon is thus constantly carried to the northwest, as far as to the mouths of the Orinoco, and an immense tract of swamp is formed along the coast of Guyana, with a long range of muddy shoals bordering the marshes and becoming converted into land. The sediment of the Orinoco is partly detained and settles near its mouth, causing the shores of Trinidad to extend rapidly, and is partly swept away into the Caribbean Sea by the Guiana current. According to Humboldt, much sediment is carried again out of the Caribbean Sea into the Gulf of Mexico. It should not be overlooked that marine currents, even on coasts where there are no large rivers, may still be the agents of spreading not only sand and pebbles, but the finest mud, far and wide over the bottom of the ocean. For several thousand miles along the western coast of South America, comprising the larger parts of Peru and Chile, there is a perpetual rolling of shingle along the shore, part of which, as Mr. Darwin has shown, are incessantly reduced to the finest mud by the waves, and swept into the depths of the Pacific by the tides and currents. The same author, however, has remarked that, notwithstanding the great force of the waves on that shore, all rocks 60 feet under water are covered by seaweed, showing that the bed of the sea is not denuded at that depth, the effects of the winds being comparatively superficial. In regard to the distribution of sediment by currents, it may be observed that the rate of subsidence of the finer mud carried down by every great river into the ocean, or of that caused by the rolling of the waves upon a shore, must be extremely slow. For the more minute the separate particles of mud, the slower will they sink to the bottom, and the sooner will they acquire what is called their terminal velocity. It is well known that a solid body, descending through a resisting medium, falls by the force of gravity, which is constant, but its motion is resisted by the medium more and more as its velocity increases, until the resistance becomes sufficient to counteract the farther increase of velocity. For example, a leaden ball, 1 inch diameter, falling through air of density as at the earth's surface, will never acquire greater velocity than 260 feet per second, and in water its greatest velocity will be 8 feet 6 inches per second. If the diameter of the ball were 1/100th of an inch, the terminal velocities in air would be 26 feet, and in water 0.86 of a foot per second. Now, every chemist is familiar with the fact that minute particles descend with extreme slowness through water, the extent of their surface being very great in proportion to their weight, and the resistance of the fluid depending on the amount of surface. A precipitate of sulfate of baryta, for example, will sometimes require more than 5 or 6 hours to subside 1 inch, while oxalate and phosphate of lime require nearly an hour to subside about 1.5 inches and 2 inches respectively, so exceedingly small are the particles of which these substances consist. When we recollect that the depth of the ocean is supposed frequently to exceed 3 miles, and that currents run through different parts of that ocean at the rate of 4 miles an hour, and when at the same time we consider that some fine mud carried away from the mouths of rivers and from sea beaches, where there is a heavy surf, as well as the impalpable powder showered down by volcanoes, may subside at the rate of only 1 inch per hour, we shall be prepared to find examples of the transportation of sediment over areas of indefinite extent. It is not uncommon for the emery powder used in polishing glass to take more than an hour to sink 1 foot. Suppose mud composed of coarser particles to fall at the rate of 2 feet per hour, and these to be discharged into that part of the Gulf Stream which preserves a mean velocity of 3 miles an hour for a distance of 2,000 miles. In 28 days, these particles will be carried 2,016 miles and will have fallen only to a depth of 224 fathoms. In this example, however, it is assumed that the current retains its superficial velocity at the depth of 224 fathoms, for which we have as yet no data, although we have seen that the motion of a current may continue at the depth of 100 fathoms. Experiments should be made to ascertain the rate of currents at considerable distances from the surface, and the time taken by the finest sediment to settle in seawater of a given depth, and then the geologist may determine the area over which homogeneous mixtures may be simultaneously distributed in certain seas. End of chapter 21.
Chapter 22, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melchior Raywood. Principles of Geology by Charles LYELL. Section number 50. Chapter 22. Igneous Causes. Changes of the inorganic world. Continued. Igneous causes. Division of the subject. Distinct volcanic regions. Region of the Andes system of volcanoes extending from the Aleutian Isles to Molucca and Sunda Islands. Polynesian archipelago. Volcanic region extending from Central Asia to the Azores. Tradition of deluges on the shores of the Bosphorus, Hellespont, and Grecin Isles. Periodical alternation of earthquakes in Syria and southern Italy western limits of the European region. earthquakes rarer and more feeble as we recede from the centers of volcanic action, extinct volcanoes not to be included in lines of active vents. We have hitherto considered the changes wrought since the times of history and tradition by the continued action of aqueous causes on the Earth's surface, and we have next to examine those resulting from igneous agency. As the rivers and springs on the land, and the tides and currents in the sea, have with some slight modifications been fixed and constant to certain localities from the earliest periods of which we have any records, so the volcano and the earthquake have, with few exceptions, continued, during the same lapse of time, to disturb the same regions. But as there are signs on almost every part of our continent of great power having been exerted by running water on the surface of the land, and by waves, tides, and currents on cliffs bordering the sea, where in modern times no rivers have excavated, and no waves or tidal currents undermined, so we find signs of volcanic vents and violent subterranean movements, in places where the action of fire or internal heat has long been dormant. We can explain why the intensity of the force of aqueous causes should be developed in succession in different districts. Currents, for example, tides and the waves of the sea cannot destroy coasts, shape out or split up estuaries, break through isthmuses and annihilate islands, form shoals in one place and remove them from another, without the direction and the position of their destroying and transporting power becoming transferred to new localities. Neither can the relative levels of the Earth's crusts above and beneath the waters vary from time to time, as they are admitted to have varied at former periods, as it will be demonstrated that they still do, without the continents being, in the course of ages, modified and even entirely altered in their external configuration. Such events must clearly be accompanied by a complete change in the volume, velocity, and direction of the streams and land floods to which certain regions give passage. That we should find, therefore, cliffs where the sea once committed ravages, and from which it has now retired, estuaries where the high tides once rose, but which are now dried up, valleys hollowed out by water where no streams now flow, is no more than we should expect. These and similar phenomena are the necessary consequences of physical causes now in operation. And if there be no instability in the laws of nature, similar fluctuations must recur again and again in time to come. But however natural it may be that the force of running water in numerous valleys, and of tides and currents in many tracts of the sea, should now be spent, it is by no means so easy to explain why the violence of the earthquake and the fire of the volcano should also have become locally extinct at successive periods. We can look back to the time when the marine strata, whereon the great mass of Etna rests, had no existence, and that the time is extremely modern in the Earth's history. This alone affords ground for anticipating that the eruptions of Etna will one day cease. Nec gae surferis ardet fornacibus, Etna, ignea semper erit, nece enim fuit ignea semper. Ovid, Metam, lib 15-340, are the memorable words which were put into the mouth of Pythagoras by the Roman poet, and they are followed by speculations as to the cause of volcanic vents shifting their positions. Whatever doubts the philosopher expresses as to the nature of these causes, it is assumed as incontrovertible that the points of eruption will hereafter vary, because they have formerly done so. A principle of reasoning which I have endeavoured to show in former chapters has been too much set at naught by some of the earlier schools of geology, which refused to conclude that the great revolutions in the Earth's surface are now in progress, or that they will take place hereafter, because they have often been repeated in former ages. Division of the subject. Volcanic action may be defined to be the influence exerted by the heated interior of the Earth on its external covering. If we adopt this definition without connecting it, as Humboldt has done, with the theory of circular refrigeration or the cooling down of an original heated and fluid nucleus. We may then class under a general head all the subterranean phenomena, whether of volcanoes or earthquakes, and those insensible movements of the land, by which, as will appear afterwards, large districts may be depressed or elevated, without convulsions. According to this view, I shall consider first the volcano, secondly, the earthquake, thirdly, the rising or sinking of the land in countries where there are no volcanoes or earthquakes, fourthly, the probable causes of the changes which result from subterranean agency. It is a very general opinion that earthquakes and volcanoes have a common origin, for both are confined to certain regions, although the subterranean movements are least violent in the immediate proximity of volcanic vents, especially where the discharge of aeriform fluids and melted rock is made constantly from the same crater. But as there are particular regions to which both points of the eruption and the movements of great earthquakes are confined, I shall begin by tracing out the geographical boundaries of some of these, that the reader may be aware of the magnificent scale on which the agency of subterranean fire is now simultaneously developed. Over the whole of the vast tracts alluded to, active volcanic vents are distributed at intervals, and most commonly arranged in a linear direction. Throughout the intermediate spaces, there is often abundant evidence that the subterranean fire is at work continuously, for the ground is convulsed from time to time by earthquakes. Gaseous vapors, especially carbonic acid gas, are disengaged plentifully from the soil. Springs often issue at a very high temperature, and their waters are usually impregnated with the same mineral matters as are discharged by volcanoes during eruptions. Volcanic regions, region of the Andes. One of these great regions, that of the Andes of South America, is one of the best defined, extending from the southward of Chile to the northward of Quito, from about latitude 43 degrees south to about 2 degrees north of the equator. In this range, however, comprehending 45 degrees of latitude, there is an alternation, on a grand scale, of districts of active with those of extinct volcanoes, or which, if not spent, have at least been dormant for the last 3 centuries. How long an interval of rest may entitle us to consider a volcano as entirely extinct is not easily determined, but we know that in Ischia there is intervened between 2 consecutive eruptions a pause of 17 centuries, and the discovery of America is an event far too recent a date to allow us to even conjecture with the different portions of the Andes, nearly the whole of which are subject to earthquakes, may not experience alternately a cessation and renewal of eruptions. The first line of active vents which have been seen in eruption in the Andes extends from latitude 43 degrees 28 minutes south, or from Yantales, opposite the Isle of Chiloé, to Coquimbo, in latitude 30 degrees south. To these 13 degrees of latitude succeed more than 8 degrees in which no recent volcanic eruptions have been observed. We then come to the volcanoes of Bolivia and Peru, reaching 6 degrees from south to north, or from latitude 21 degrees south to latitude 15 degrees south. Between the Peruvian volcanoes and those of Quito, another space intervenes of no less than 14 degrees of latitude, said to be free from volcanic action so far as yet known. The volcanoes of Quito then succeed, beginning about 100 geographical miles south of the equator, and continuing for about 130 miles north of the line, when then occurs another undisturbed interval of more than 6 degrees of latitude, after which we arrive at the volcanoes of Guatemala or Central America, north of the Isthmus of Panama. Having thus traced out the line from south to north, I may first state, in regard to the numerous vents of Chile, that the volcanoes of Yantales and Osorno were in eruption during the great earthquake of 1835, at the same moment that the land was shaken in Chiloé and in some parts of the Chilean coast permanently upheaved, whilst at Juan Fernandez, at the distance of no less than 720 geographical miles from Yantanes, an eruption took place beneath the sea. Some of the volcanoes of Chile are of great height, as that of the Antuco, in latitude 37 degrees 40 minutes south, the summit of which is at least 16,000 feet above the sea. From the flanks of this volcano at a great height, immense currents of lava have issued, one of which flowed in the year 1828. This event is said to be an exception in the general rule, few volcanoes in the Andes, and none of those in Quito, having been seen in modern times to pour out lava, but having merely ejected vapor or scoriae. Both the basaltic or augitic lavas and those of the feldspathic class occur in Chile and other parts of the Andes, but the volcanic rocks of the feldspathic family are said by von Buch to be generally not trachyte, but a rock which has been called andesite, or a mixture of augite and albite. The last mentioned mineral contains soda instead of the potash formed in common feldspar. The volcano of Rancagua, latitude 34 degrees 15 minutes south, is said to be always throwing out ashes and vapors like stromboli, a proof of the permanently heated state of certain parts of the interior of the earth below. A year rarely passes in Chile without some slight shocks of earthquakes, and in certain districts not a month. Those shocks which come from the side of the ocean are the most violent, and the same is said to be the case in Peru. The town of Copiapo was laid waste by this terrible scourge in the years 1773, 1796, and 1819, or in both cases after regular intervals of 23 years. There have, however, been other shocks in that country in the periods intervening between the dates above mentioned, although probably all less severe, at least on the exact same side of Copiapo. The evidence against a regular occurrence of volcanic convulsions at stated periods is so strong, as a general fact, that we must be on our guard against attaching too much importance to a few striking but probably accidental coincidences. Among these last might be adduced the case of Lima, violently shaken by an earthquake on the 17th of June, 1578, and again on the very same day, 1678, or the eruptions of Coseguina in the years 1709 and 1809, which are the only two recorded of that volcano previous to that of 1835. Of the permanent upheaval of land after earthquakes in Chile, I shall have occasion to speak in the next chapter, where it will also be seen that great shocks often coincide with eruptions, either submarine or from the cones of the Andes, showing the identity of the force which elevates continents with that which causes volcanic outbursts. The space between Chile and Peru, in which no volcanic action has been observed, is 160 nautical leagues from south to north. It is, however, as von Buch observes, that part of the Andes which is least known, being thinly peopled, and in some parts entirely desert. The volcanoes of Peru rise from a lofty platform to vast heights above the level of the sea, from 17,000 to 20,000 feet. The lava which has issued from Viejo, latitude 16 degrees 55 minutes south, accompanied by a pumice, is composed of a mixture of crystals of albitic feldspar, hornblende, and mica, a rock which has been considered as one of the varieties of andesite. Some tremendous earthquakes which have visited Peru in modern times will be mentioned in a subsequent chapter. The volcanoes of Quito, occurring between the 2nd degree of south and the 3rd degree of north latitude, rise to vast elevations above the sea, many of them being between 14,000 and 18,000 feet high. The Indians of Licar have a tradition that the mountain called L'Altar or Capac Urcu, which means the chief, was once the highest of those near the equator, being higher than Chimborazo. But in the reign of Winia Abomatha, Before the discovery of America, a prodigious eruption took place, which lasted 8 years and broke it down. The fragments of trachyte, says Monsieur Boussingault, which once formed the conical summit of the celebrated mountain, are at this day spread over the plain. Cotopaxi is the most lofty of all the South African volcanoes which have been in a state of activity in modern times, its height being 18,858 feet, and its eruptions have been more frequent and destructive than those of any other mountain. It is a perfect cone, usually covered with an enormous bed of snow, which has, however, been sometimes melted suddenly during an eruption, as in January 1803, for example, when the snows were dissolved in one night. Deluges are often caused in the Andes by the liquefaction of great masses of snow, and sometimes by the rending open during earthquakes of subterranean cavities filled with water. In these inundations, fine volcanic sand, loose stones, and other materials which the water meets with in its descent are swept away, and a vast quantity of mud, called moya, is thus formed and carried down into the lower regions. Mud derived from this source descended in 1797 from the sides of Tunguagua in Quito, and filled valleys 1,000 feet wide to the depth of 600 feet, damming up rivers and causing lakes. In these currents and lakes of moya, thousands of small fish are sometimes enveloped, which, according to Humboldt, have lived and multiplied in subterranean cavities. So a great quantity of these fish were ejected from the volcano of Imbaburu in 1691. That fevers which prevailed at the period were attributed to the effluvia arising from the putrid animal matter. In Quito, many important revolutions in the physical features of the country are said to have resulted within the memory of man from the earthquakes by which it has been convulsed. Monsieur Boussingault declares his belief that if a full register had been kept of all the convulsions experienced here and in other populous districts of the Andes, it would be found that the trembling of the earth had been incessant. The frequency of the movement, he thinks, is not due to volcanic explosions, but to the continual falling in of masses of rock which have been fractured and upheaved in solid form at a comparatively recent epoch. But a longer series of observations will be requisite to confirm this opinion. According to the same author, the height of several mountains of the Andes has diminished in modern times. The great crest of Cordillera of the Andes is depressed at the Isthmus of Panama to a height of about 1,000 feet and at the lowest point of separation between the two seas near the Gulf of San Miguel to 150 feet. What some geographers regard as a continuation of that chain in Central America lies to the east of a series of volcanoes, many of which are active in the provinces of Pastor, Popayan, and Guatemala. Coseguina, on the south side of the Gulf of Fonseca, was in eruption in January 1835, and some of its ashes fell at Truxillo on the shores of the Gulf of Mexico. What is still more remarkable, on the same day at Kingston in Jamaica, the same shower of ashes fell, having been carried by an upper countercurrent against the regular east wind, which was then blowing. Kingston is about 700 miles distant from Coseguina, and these ashes must have been more than 4 days in the air, having travelled 170 miles a day. 8 leagues to the southward of the crater, the ashes covered the ground to the depth of 3.5 yards, destroying the woods and dwellings. Thousands of cattle perished, their bodies being in many instances one mass of scorched flesh. Deer and other wild animals sought the towns for protection. Many birds and quadrupeds were found suffocated in the ashes, and the neighbouring streams were strewed with dead fish. Such facts throw light on geological monuments, for in the ashes thrown out at remote periods from the volcanoes of Auvergne, now extinct, we find the bones and skeletons of lost species of quadrupeds. Mexico. The great volcanic chain, after having thus pursued its course for several thousand miles from south to north, sends off a branch in a new direction in Mexico, in the parallel of the city of that name, and it prolonged in a great platform between the 18th and 22nd degrees of north latitude. 5 active volcanoes transverse Mexico from west to east: Tuxtla, Orizaba, Popocatépetl, Jolulio, and Colima. Jolulio, which is in the center of the great platform, is no less than 120 miles from the nearest ocean, an important circumstance, showing that the proximity of the sea is not a necessary condition, although certainly a very general characteristic of the position of active volcanoes. The extraordinary eruption of this mountain in 1759 will be described in the sequel. If the line which connects these 5 vents be prolonged in a westerly direction, it cuts the volcanic group of islands called the Isles of Revillagigedo. To the north of Mexico, there are said to be 3, or according to some 5 volcanoes in the peninsula of California, and a volcano is reported to have been in eruption in the northwest coast of America, near the Columbia River, latitude 45 degrees 37 minutes north. West Indies. To return to the Andes of Quito, Von Buch inclines to the belief that if we were better acquainted with the region to the east of Magdalena, and with New Granada and the Caracas, we might find the volcanic chain of the Andes to be connected with that of the West Indian or Caribbee Islands. The truth of this conjecture has almost been set at rest by the eruption, in 1848, of the volcano of Zamba in New Granada at the mouth of the river Magdalena. Of the West Indian Islands there are 2 parallel series, the one to the west, which are all volcanic, and which rise to the height of several thousand feet. The others to the east, for the most part composed of calcareous rocks and very low. In the former or volcanic series are Grenada, St. Vincent, St. Lucia, Martinique, Dominica, Guadeloupe, Montserrat, Nevis, and St. Eustace. In the calcareous chain are Tobago, Barbados, Marigalante, Grande Terre, Destigare, Antigua, Barbadua, St. Bartholomew, and St. Martin. The most considerable eruptions in modern times have been those of St. Vincent. Great earthquakes have agitated St. Domenico, as will be seen in the 29th chapter. I have before mentioned, page 270, the violent earthquake which in 1812 convulsed the valley of Mississippi at New Madrid, for the space of 300 miles in length, of which more will be said in the 27th chapter. This happened exactly at the same time as the great earthquake of Caracas, so that it is possible that these 2 points are part of one subterranean volcanic region. The island of Jamaica, or the tract of the contiguous sea, has often experienced tremendous shocks, and these are frequent along the line extending from Jamaica to San Domingo and Puerto Rico. Thus it will be seen that without taking account of the West Indian and Mexican branches, a linear train of volcanoes and tracts shaken by earthquakes may be traced from the island of Chiloe and opposite coast to Mexico, or even perhaps to the mouth of the Columbian River, a distance upon the whole as great from the pole to the equator. In regard to the western limits of the region, they lie deep beneath the waves of the Pacific, and must continue unknown to us. On the east they are not prolonged, except where they include the West Indian Islands to a great distance, for there seems to be no indications of volcanic disturbances in Buenos Aires, Brazil, and the United States of North America. End of chapter 22, part 1. Recording by Melchior, Raywood.